avis, personne ne va s'asseoir ici. Okay, so let me welcome you all for this workshop, which is organized by Jean-Paul in honor of Jean-Paul Laumond. Holding this event here is particularly significant because Jean-Paul is the one who, as a professor for 1 year at the Collège de France, introduced robotics here 10 years ago. I mean, as you know, Jean-Paul was a wonderful man. He was an incredible scientist, recognized worldwide for his many contributions in non-holomic control of robots, path planning, and humanoid robotics. But Jean-Paul was also a fantastic teacher who transmitted his vision to his students and to a very large public. And it is in his beautiful inaugural conference here at the Collège de France for his course that he gave for 1 year that I can only recommend you to hear on the Collège website. He gave a profound perspective on robotics through its history, major scientific challenges, and social impact. But there is a red line in his presentation that gave a constant tension in the way he viewed his own research between doing as an engineer to create robotic systems that works and understanding as a scientist who's searching for basic principle. This tension and equilibrium is, I believe, a signature of Jean-Paul. He was an engineer who created many robotic systems and an entrepreneur who created his company KineoCam, but at the same time, he was a deep scientist building mathematical models, collaborating with researchers in neurosciences, humanities, and social sciences. It is his longtime collaborator and friend, Alain Berthoz, who introduced him at the Collège de France. And I would like to read here the message that Alain sent us. Jean-Paul was a man of immense culture and of creativity that was matched only by his marvelous modesty, his generosity, and his kindness. I had the privilege of learning a lot from him. During more than 20 years of collaboration between his team in Toulouse and our laboratory here at the Collège de France, we studied the laws and principles of human locomotion. He was at the origin of very powerful paradigms inspired by the double concern of a rigorous mathematical theory on the geometry of trajectories, for example, and the need for experimentation to verify the hypothesis that the theory proposed. His smiling, always friendly gaze, his intellectual and personal generosity, his attachment and his solidity in friendship and in his region of Collège, his ability and his confidence to motivate young people to develop their talents will be terribly missed. We are deprived of a beautiful spirit and a real friend. Let me add to the word of Alain that I think that this workshop, with the participation of you all, his friends, collaborators, is really a beautiful way to preserve his souvenir as a friend and as a wonderful scientist. Thanks.
Thank you, Stéphane, for these very kind words. So I'm Jean-Paul. I've been co-organizing this workshop with PRAIRIE-PSAI. I just want to say a few words. You probably will want to use the Wi-Fi. I mean, most people do nowadays. So the network is public _CDF, and the password is extern CDF789. I have a mask on. I will remove it when I give a talk, but there is the pandemic is going back up, so you do whatever you want, but it may get crowded here. I encourage you to wear the mask as you sit, of course, not when you are giving a talk. There are wipes here, and I encourage you as well to wipe the microphone, so I don't want anybody to get sick during the workshop. That would be nice. So last thing, I wanted to thank a couple of people. So I want first to thank the Free Institute PRAIRIE, LAS CNRS, and Collège de France for supporting the workshop. Also want to thank Paul Jacobs, who was a PhD student of John Kenny and a postdoc of Jean-Paul, and then went on to have a great career as well in industry and with Qualcomm, and he's at the US Academy of Engineering now, and he has helped sponsored personally the workshop, so I think this should be acknowledged. And I want to thank Professor Stéphane Mallat and Professor Alain Berthoz for making this workshop possible. And also I want to thank very strongly Marilyn Mestron de Rennes, without whom this thing would have never happened. So thanks to all, and of course to all of our speakers who come from North America, Europe, and Japan. And now, without further delay, we are going to start the first session, and Nick Simeon is going to chair it. Thank you very much. For presentations, just put your USB-C thing there.
So, good morning and welcome to this first session. So I am Thierry Siméon and also a CNRS researcher at LAS, where Jean-Paul spent most of his career. And I got the chance to collaborate with him and to share the same office during more than 10 years with collaboration in particular on the techniques, motion planning techniques that led to the creation of the spin-off Kineo. So thank to Stéphane for his very nice introduction on Jean-Paul's career. And as all young researcher he mentored, I learned a lot from the interaction with him, and also remembers his enthusiasm and the pleasure it was to work with him. So it's a great honor, but also some emotion to be here and share this session at this workshop. Now back to the first session. So we have 4 talks. The 2 first one will correspond to early work of Jean-Paul on non-autonomic motion planning for a wheeled robot, which was pioneering work done in the 80s that was instrumental in establishing non-autonomy in the motion planning and robotics literature. And the two next talk so correspond to more recent research for self-driving cars, so stable, safe driving cars, and also for advanced locomotion for legged robots. The first talk now is given by my colleague and friend Philippe Swear, who is also a researcher at LAS and the head of the robotic department. Philippe was actually one of the first PhD students of Jean-Paul, and his early contribution concerned motion planning and control for wheeled robots, also aerial robots and surface motion, and interdisciplinary research at the interface of, between robotics and neuroscience. He contributed with Jean-Paul to the creation in 2006 of the Gepetto team, specialized in, as you know, in motion of humanoid robots and anthropomorphic systems, and he led the teams 9 years until 2 years ago. His current research interests include the humanoid legged robots control and modeling and analysis of human motion. But in this first talk, Philippe will tell us the old story of the adventure of optimal paths in for non-autonomic wheel robots.
Thank you, Nick. It's a pleasure for me to have all there. We cannot talk about Jean-Paul without talking about mathematics. So I go back to the early 90s to a work he loved a lot, on which we worked together during my PhD, which is about the shortest path of non-autonomic vehicles. So today, in the Gepetto team, when we are producing complex motions for these complex robots, anytime we solve an optimization problem. We have powerful software for that, and so we optimize complex cost functions under many constraints, and it works. So what I want to talk about is an pioneering work where we were trying to solve analytically some optimal control problem, but for simplest systems that anyway had some very hard difficulties. So I want to talk about the car-like robot, or others call it the Unicycle, which is characterized by the fact that he can not slide, he can roll without slipping, so he's constrained to move tangentially to its main axis. And also there is a constraint on the turning radius, so the radius should be greater than a given threshold, let's say 1. So this problem was introduced by Dubins in 1957, considering only forward motion. So in this case, the velocity is constant, so the control set is this line. And he proved that paths are made up with arcs of circle of minimum turning radius and line segments. And he demonstrated that it's sufficient to look into this kind of family with two path types, circle, 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 or circle, segment, circle. And here you have information about the path length that should be within a certain interval. Later, Regenschep solved this problem, but allowing backward motion. So in that case, the control set is no more convex, and it's the beginning of difficulty. And he didn't prove the existence of optimal path, and he demonstrated that in that case, it's sufficient to look into this family. So all the arguments that were used by this researcher to solve this problem were kind of ad hoc arguments. So what we try to do is to formulate it as an optimal control problem. And this was a friendly, collaborative competition between 3 teams. One at Rutgers University, Hector Sussman, very strong researcher in optimal control. The team of Jean-Daniel Boissonnat in RIAS of Sophia Antipolis. And at LAS, we were not specialists of optimal control, but we started to work on this problem. So you have the system described by an ordinary differential equation, and given 2 points, you want, if exist, to find a point that steers the representative point between these 2 configurations. And to do that, you want to minimize the cost functional, And in that case, we consider that this is the time, but as we are moving at constant velocity, then it's the same as minimizing the length. So when we want to solve this kind of problem, we know that we have to construct an Hamiltonian, which is the scalar product between the adjoint vector and the dynamics of the system. And we have this differential equation that should verify the adjoint vector. So a necessary condition given by the maximum principle is to optimize, is to find a control that optimizes this scalar product and give a positive value. So we can write the system as a linear combination of functions depending on the control, and this function will determine the optimal behavior, because either they are they vanish only at isolated points, so we have what we call band control, maximum or minimum, or we have singular control that vanish on the whole interval, and in that case it's not easy to find the solution. We have to find upper degree conditions. Okay, so the existence, I told, is a very difficult problem. In the case of systems that are linear in the control, like this one, there exists some theorem. But as I told, this set is not convex. And as it's not convex, we cannot apply them. So the decision was to work on the convexified Regency problem and try to solve the problem for it and see what happens. Then we can write the systems in terms of two vector fields. Here it's moving straight in the theta direction. Here you turn on the spot. And then combining them by doing maneuvers, then you can move sideways as you do with your car. And this is what expresses the Lie bracket of vector fields. So the Hamiltonian can be written this way, where you make appear the switching functions. And using this relation, we can express it under a canonical form. So once the system, is under this canonical form, then we want to optimize it, and that a set of solutions, a set of conditions can be deduced from the maximum principle. I don't go into details. So, for instance, there is no abnormal extremal. The both switching functions cannot have a common zero, and either the zero of the first cost function are all isolated, or the cost function vanishes all along the trajectory. So based on that, we deduce that there are two kinds of trajectory, taper with a finite number of switches on the linear velocity, and the other one that is the singular one, where you can have many switches, but you turn always in the same direction. So we studied each type. So in this case, we can integrate the adjoint equation. So as we see that the Hamiltonian doesn't depend on x and y, then we can conclude that those two first components are constant. For the third one, the derivative is with respect to theta. Then we can integrate this, we can take the derivative with respect to this value, and we make a pair y dot and x dot, so we can integrate, we are lucky, we can integrate this equation, and we obtain the expression of an affine expression. So this is the expression of a line. So we know that this cost function will vanish on a line. And then we can prove, in fact, that we will have inflection points or line segments on the middle line, and we will have the cusp points perpendicularly on the two other lines. So this is a very strong condition given by the maximum principle. Concerning the other path type, then in this case, it's singular, and we can prove that it's locally degenerated. So if we have a time interval that is smaller than pi, then any kind of concatenation of circle is always optimal, because you integrate. Yes. Okay, sorry. So because we integrate the angular velocity that is equal to 1, so it's a degenerated problem. And here, Hector Sussman proved, using very clever arguments for optimal control theory, that we can reduce the family to those two path types. So L means left turn, and right means right turn, and this is because you go forward and backward. Okay, so now we go to a sufficient family, but this is for the convexified resolution problem, recall. But we can consider that all the trajectory that we obtain are in fact for maximal or minimal velocity. So in fact, they are solution of the Riemann-Shape problem, and then they are admissible for our problem, and they provide a sufficient solution for the Riemann-Shape problem, and they guarantee the existence. So we prove the existence a posteriori. So the maximum principle is not sufficient. It's a local optimization of a scalar product. So to conclude, we have to have some geometric reasoning. And what helped us is the symmetries. For instance, if you are in the plane of the vehicle's motion, if this trajectory is optimal, then you can draw another one that is isometric to the first one, and that should be optimal as well. And a more difficult symmetry to find was that if you consider, because this is a three-dimensional problem, you have the x, y as the first two coordinates, and the third one is theta. So in horizontal plane of constant value of theta, then if you have a trajectory that is optimal, then you will construct three others that are optimal at the same time. And also you can anytime construct the name of the trajectory and find them automatically. Okay, so when this lane is depending on the orientation in this analytical expression. And when this value goes to pi, then both symmetry can commute. And then if you have a trajectory, for instance, this one turning left, then you can anytime construct an isometric one turning in the opposite direction. So we use that to demonstrate that along a trajectory, if the variation is greater than pi, then we can always replace a part of the trajectory by an equivalent one, and then following the blue, or following first the part red and then the blue, is equivalent. But in that case, you see that you have an inflection point here and a line segment, and they do not belong to the same line. So it's not optimal. So we can reject and refine the trajectories. So this is the reasoning. And then it's sufficient to look for solution in R2 times minus pi pi. Based on that, we constructed the synthesis. It means that for each path types, we consider path type that were in one of the quadrants defined by the two symmetry lines. For each path type, we integrated this expression, considering the limits on the parameters, and we obtained some volume, and you can have cross sections in for each value of theta. And we did that for all the domains. And so in the first quadrant, you can see that you have a partition. It's good. So it's almost done, but not. Because if you consider the symmetry, then you will have a lot of overlapping. Then we had to find a lot of arguments from geometry to refine this result. And the reasoning, for instance, is consider that this blue trajectory is a candidate for optimality. Then when it crosses the symmetry line, then we know that we can replace this last portion blue by this red one. But again, you will have a point of inflection here, and if you draw a line, it's not perpendicular to the cusp. So it's not optimal. And then going so on, we solve totally the synthesis of optimal path for the Riemann-Shape problem. So this is horizontal planes between minus pi and pi, and in each plane, we have this construction of the synthesis. Okay, so it's very interesting to look at the wavefront a posteriori, because now we can construct them by considering what we obtained in the first quadrant. Then we have different wavefront, and we see that they intersect. So the principle of the maximum principle, we never solve that because it's local. And so you have some parts of the space where you have more than one solution that are equivalent. This is what we call the cut locus, and this is represented, for instance, in a certain horizontal plane. Based on that, then we study the metric, that is produced by this construction. And this metric is a very powerful tool for building algorithm amidst obstacles for having a non-holonomic distance. Okay, so once we solve this Riemann problem, then we go back to the Dubin's problem, and we say, okay, we solve for the complex problem, then for Dubin's it will be simple, but because it's only go forwards. But it's wrong, because as it doesn't go backwards, then you lose some symmetries. So you add more and more complexity in the problem, and we found some solution based on continuity and so on. And finally, we solve this problem as well for Dubin's. So it provides a complete knowledge of the optimal path for reaching the origin point. A very interesting result is that for Dubin's problem, the path length, the optimal path length, is no more a continuous function of the state. Here, the two circles are the minimal turning radius. Suppose you start from here. Then it's very difficult, it's very easy to go forward. Remember that you cannot go backwards, okay? So, in fact, if you want to go inside this region, it's very long, and so we will have some discontinuity on those black circles. So, it's very particular result for the Dubin's problem. Then, a posteriori, I'm sorry, based on good advice of Hector Sussman, we try to find another proof by, instead of using the necessary condition of the maximum principle, to use sufficient conditions. Suppose you have the construction of the synthesis, and you want to prove that it is optimal. Then there exists some theorem, and there is a very nice one by Boltiansky, one of the co-authors of the maximum principle, which demonstrated that if you have some regularity conditions on the system dynamics, the structure of the partition, for instance, when we switch from a domain to another one, we cross some kind of cells, we follow others, we have some regularity in terms of the dimension, and there is a set where you can have more than one solution, the one we described. Then if you have the continuity of the cost functional, that is a very important condition, then in that case, you can prove that all the trajectories in your synthesis are optimal. And we were able to apply that to the Riemann-shape synthesis and provide a proof a posteriori. But for Dubin's, it was not possible because we know that the path length is no more continuous. So it was not possible to use it. But in that case, there are authors that have been working on trying to find less restrictive sufficient conditions that still apply to find the optimal structure. Okay, so this was Riemann-shape. I want to talk about two other problems on which Jean-Paul worked. The first one is the model of Hilbert. Hilbert was the mobile robot built at La CNRS in 1977. And this robot is driven by two wheels that are independently controlled. So you have the velocity of the right wheel, velocity of the left wheel, and then this is the linear velocity. And we control in acceleration. So it should be smoother, the result. And in that case, a result where Paul Jacobs was the first author was to demonstrate that there are there was no singular extremal and two kinds of bang-bang trajectory. The first one is a clotoid. We know that it's a very important curve when we want to smooth the transition between the line segment and a circle, and also an involute of circle. So based on that, they were not able to bound the number of switches and to go further in the characterization of optimal paths. There were some attempts, one by Rester and Pair in '94, that use a numerical approach to try to prove that with 4 switches you can reach any configuration, but no proof of optimality. And later, a result by Marc Renaud and Jean-Yves Fourquet was to demonstrate that, in fact, with 4 switches, there are some regions where you are not optimal. So it's still an open problem. Another problem we consider was to smooth the Dubin's problem. So as you see here, we just add an integrator on the velocity. We do not control in velocity, but we control in acceleration with the acceleration within a certain compact set. And in that case, we want also to find the minimum time trajectories. In that case, it's quite easy to prove that either you have bang-bang trajectory that are clothoid, or you have line segments. So it sounds the good solution, because you can have now a smooth transition between the line and the curve. But if you continue to look at the equation, then you can prove this very strange result. That is, if you have a concatenation between a line segment and a clothoid, then there will be an accumulation of switching point, which is known as a Fuller phenomenon. And then we cannot conclude. So it was a very difficult question. We discussed a lot with that with Hector Sussman without finding the solution. The reasoning is based on computing the time derivative of this function up to order 4. And Hector Sussman demonstrated that in some cases, extremals involving an infinite number of shattering can be optimal. So still another problem here too. Okay, I was very fast, I'm sorry, but I wanted to tell you all that. And this is a memory of the promotion project that was held by Jean-Paul Laumond. And you can see a lot of guys that are in this room today. You have Alessandro De Luca here. You have Antonio Bicchi, and Goldberg, Mercury, so, and Jean-Paul here. So, and Hector Sussman, that was a very good partner, a very nice person. Okay, thank you.
Thank you, Philippe, for this workshop and explanation of the math that synthesis of evidential optimal path in creative problems. We have time perhaps only for a short question or for questions.
Yes.
I just wanted to make a very brief comment. I was reading a recent interview. I just wanted to make a brief comment. It's wonderful to see you give an overview of these things, this research that I really love. And in a recent interview that Jean-Paul gave, he was asked to mention the 3 or 4 biggest highlights of his career, and he mentioned that one of those moments was when you showed him those curves for the first time, and he saw that. He was so delighted. So anyway, it's very nice to see you cover that.
I remember that. It was in Paris. A nice workshop with Coron and other very good researchers in optimal control. And then I was a student, I was very afraid, and I meant it was not such an important result. And I presented that on the blackboard, and I saw Hector Sussman looking at that, and he told me, "You do not escape this room, we have to talk." And then the collaboration started from this point, and he made me understand all what was behind that. And yeah, it was a wonderful adventure. And Jean-Paul was the good person for connecting people and providing research at the highest level. And this is a few persons rival of that.
Thank you. No more questions? So let's move to the second talk. We will remain on optimal path for wheeled an autonomic robot, and it's a great pleasure and honor to introduce our second speaker, Matt Mason, who is one of the pioneers in robotic manipulation research. Matt earned a PhD degree in computer science from MIT, supervised by Thomas Perez, that everybody knows. Of course, he's currently Professor Emeritus of Robotics and Computer Science at Carnegie Mellon University, and also Chief Scientist of the Berkshire Hathaway Company. Matt has been for 10 years the director of the CMU Robotics Institute, and is the author of several reference books on the mechanics of robotic manipulation. His work was recognized by prestigious prizes and awards, the IEEE Robotics and Automation Society Pioneer Award, and the IEEE Technical Field Award in Robotics and Automation. So today, manipulation will not be the topic of his presentation, but in memory to Jean-Paul, his talk will investigate. So some work he did at the end of the 90s, inspired by the work presented, the early work of Jean-Paul presented by Philippe. So Matt, the floor is to you.
Thank you very much for the nice introduction. I'm making sure there's nothing embarrassing on my screen. Except for my talk. This will work. Say play. Oh. Oh, I know. One moment. Better. Thank you very much for inviting me. It's it's an honor to be included in this group. You just got a taste of some optimal control work that I got involved in, and I'm very fortunate to have followed Philippe in real life and also in these talks, because there is no way that I could present the technical details of this work, and so I'm just going to refer to the previous talk, okay, for technical details. Of course, well, so this is really the story of how I got pulled into optimal control. It wasn't something that I planned to do, and in fact, I don't know about the rest of you, but I spend most of my life trying to convince myself that I don't need to know this and I don't need to know that. You know, you have to be focused, and so I was convinced I did not need to know optimal control, and then that went wrong, okay? And this is the story of how I fell into optimal control.
The Manipulator is a mobile manipulator that uses its wheels both for locomotion and manipulation. It has 4 independently driven wheels, none of them steered.
Can you hear that?
The rubber rings on the wheels help grip the paper firmly. We also occasionally add ballast to the robot to reduce slip. The wheels on the paper are called hands, and the wheels on the ground are called feet. The feet work like a 2-wheeled differential drive mobile robot, while the hands use a differential drive arrangement to manipulate the paper. For this task, there is no visual feedback, and the robot uses the natural compliance of the paper to make sure the paper is flush against the block. There are lots of other interesting ways to manipulate things. Here, the robot moves the paper by vibrating with an asymmetric vibration. Vibration can also be used to reduce friction between the paper and the desktop, as in this motion. While mobile robots use parallel parking to move themselves sideways, the Manipulator uses parallel parking to move the paper sideways. However, since paper is much lighter than a robot, the parallel parking motion can be much faster. The robot can also move cylinders if it can get on top of them. In this case, it uses the edge of the table to mount the cylinder. Once on top, the robot is surprisingly stable. In the absence of paper, the robot must use skid steering to turn. Unfortunately, here its high friction tires become a handicap. We are using visual feedback to steer more accurately. We have also developed a path planning algorithm that uses the dual differential drive to navigate paper from a start to a goal configuration while avoiding known static obstacles. Of course, while the planner expects an ideal world, friction and slip in the real world are far from predictable. Hence, the implemented plan does not always work. We are currently working on using the camera to correct these errors. The Manipulator is a concept car. It is designed to explore different concepts of how a mobile robot can perform manipulation tasks, and, in particular, the interconnectedness of locomotion and manipulation.
All right, so I'm a manipulation guy. Those optimal control guys were mobile robot guys, and so I thought I was safe. But then we built this machine that uses the ILAR-style kinematics to do manipulation as well as locomotion. So that was the beginning of the problem. So the Manipulator, you can view it as two wheelchairs glued together. One of them is doing manipulation of a piece of paper. The other one's doing locomotion. Of course, you can switch which one is which. Now, I like to call them wheelchairs sometimes, but that's not the respectable term. For roboticists, we call them sometimes the two driving wheel robot or the LR-like robot, or I like to call them a differential drive or diff drive. So we called that a diff drive robot. Okay, so how did I fall into optimal control? Starting around 98 or so, we built the Manipulator, and then in Lisp, I wrote the first path planner for it, and I didn't build a path planner for the whole thing. I thought I'll just do one diff drive. So I built a path planner for a diff drive, and it was very crude. It was discretizing things and doing searches in these discretized spaces on grids, and the paths were terrible. They looked so ugly. It was too embarrassing to show people something that looked so ugly. But, you know, this was a real problem because I needed a path planner. I have a path planner. It's embarrassingly ugly, but were they really ugly, or did they just look ugly to me? You know, I needed an objective idea of what ugly would be, or what good would be. How do you objectively define the quality of a path? And I realized then that I knew people that worked on those things, and the beauty of that moment is that I'm sitting at my desk and I'm pondering this and I know what I need, and then I remember Jean-Paul Laumond had recently mailed me a copy of this book. And it was, you know, I'm just sitting here working at my desk, and there's the answer on my bookshelf, you know, 2 feet away. Now, today, no big deal. You've got the internet. You know, I could have used Scholar or Semantic Scholar and looked up the relevant papers in a minute, and it would be maybe even faster than having to reach 2 feet to my bookshelf. But this is like a miracle, okay, for me. And one of the key papers that I used that Philippe was citing is in this book, and so that's where I started. And so that was waiting on my bookshelf. So then, how do you address this question of how to assign quality, some kind of metric to a path? Well, the obvious first metric to consider is the length of the path. How do you think about the length of a path of a robot that can both rotate and translate? You put a bound on the velocities of it, and then you look for the time optimal paths. And you know, this is one of the things I learned from those guys. How do you find the time optimal paths? And you just had a very nice review of the machinery to do that. You used the Pontryagin maximum principle, and then there's some other geometrical techniques developed by Sussman and Tang, by Vossen, by Laumond, and by Philippe. And that was, you know, my activity for the next several weeks or months was studying those papers to figure out how to solve this problem. Now, the thing is, I didn't know the problem was unsolved. It seemed actually quite unlikely to me that the diff drive robot, that the shortest path problem for the diff drive robot would be unsolved. And so I really just didn't believe it at first. But this is the situation as I saw it. After Philippe's talk, I'm going to go back and add one more paper to the lower right quadrant there. There was a paper I was unaware of. But these, so they're the bounded acceleration models that give you the smoother trajectories on the right column. The left column are the bounded velocity models, the Dubin's model, the Reeds and Shep model. And then down here would be the diff drive or the Hilar-like mobile robot. But the bounded velocity optimal controls for that model had not been produced. And it still makes me very nervous to say that. Is that right? Is that really right? I still don't understand it. And I didn't believe it. I thought there must be some way that you can reduce the problem of the diff drive robot to the steered vehicles that I was the new guy in this field, and I'm just too stupid to see it. And I could have just sent Jean-Paul an email, but I didn't want him to know how stupid I was, and so I tried to figure it out myself. And so one question to ask yourself, if you're thinking about this, is suppose you have the path where you leave one wheel fixed, and you roll the other wheel forward a tiny amount, epsilon. Surely that would be an optimal path, a shortest path. And the answer is it's not. You can do a little bit of math, you can do a little bit of just plain old geometry, and calculate that it's actually long compared to the strategy of you pivot in place, you roll forward, and then you pivot in place a little bit more. Okay, that's actually the optimal path, the shortest path, rather than just pivoting about one wheel. And once you see that, it's not too hard to figure out by ad hoc mathematical techniques, simple techniques, that a diff drive making shortest paths will never curve. It will always pivot in place or go in a straight line. Okay, so at that point I'm like, okay, I don't see any way this reduces to a wheeled mobile robot, and I had the courage to then ask Jean-Paul for confirmation. And I had this moment I'll never forget. We were at some workshop or something, and during a break, I grabbed him and I asked him this question. And I remember he was sitting on the staircase thinking, and I was standing off to the side, successfully struggling to remain silent and let him just ponder it. And then he said, yeah, that's right. This is a good thing, you should do it. So, that was the moment that changed my life. There's still a question I don't know the answer to, though, which is why was the upper left quadrant empty? Why had that problem not been addressed? And I have two ideas. One idea is that these guys, this was behind the leading edge. It was low-hanging fruit that had been skipped over. The leading edge of the work, they were trying to develop the controls that would be more practical, controls that you could actually apply, and that they were more interested in smooth trajectories. So they really were more focused on solving the bounded acceleration problem rather than the bounded velocity problem. So in which case it's easy to, you're looking ahead of yourself, you're not worrying about the low-hanging fruit that might be behind. The other theory, I don't know if this is something any of you have ever tried, but one thing that happens when you're writing a paper is you might realize that there's a simple extension of the work you're doing, and you could put it in the paper, or you could leave it out. And then maybe somebody that's reading your paper will look at it and say, oh my gosh, they missed something here. I can do that. And then they'll publish a paper and they'll cite you. In fact, if you're really good at this, maybe a lot of papers would follow and cite you. So I've tried that, never worked. But I thought maybe that's what these guys are doing. Is that what you were doing? Maybe. Yeah, so in that model, you know, Laumond and that gang, they're the fishermen, and I'm that trout there, okay, because I definitely took the bait. So we're skipping over Pontryagin, existence, sufficient family. It does have an analytical solution, and you do get a family, which is simpler than the steered cars. So these are the answers. There's a family of 9. Oh yes, and I also took the symmetries, used the same symmetries that Philippe was talking about. So using those symmetries, you get down to 9 families, and you can see, as I said before, it's all straight lines and pivots. And there's a couple of families down here at the bottom, which are like parallel parking motions. Oh, and I should have mentioned, Devin Balcom was a PhD student who joined us early on, and really he came up with the first exposition of this family done by more ad hoc methods, although he might have missed a family or two, I don't know. Anyway, he did a lot of the work. Here are some animations. Preparing for this talk, the biggest challenge was that these animations were produced by me 20 years ago, and they don't work. They didn't work. I couldn't even remember the technology I used to produce these animations. Do you remember something called Flash? So 20 years ago, that was like the standard for animations on the web. And I had a hell of a time even finding a tool that could convert Flash to modern technique. Anyway, that's all 9 families. Okay, well, we just looked at one of these. For some reason, I drew mine from 0 to 2 pi. Philippe's diagram, you may recall, went from negative pi to pi and put the origin in the center. Is this a laser? Yeah, so this is the origin, really. Okay, it wraps around from 0 to 2 pi. So the question is, in a given length of time, how far will it take, how much time, in a given length of time, from which configurations can you get to the origin? So in a given length of time, you can drive, so this is the x-axis, this is the y-axis. So if you're at 2 pi or 0, the robot is facing along the x-axis. And so it can travel quite a distance in a given set time. If it's going straight forward, if it's going sideways, it has to do one of those parallel parking motions, right? So these are level sets of the metric induced by the bounded velocity diff drive model, okay? And so I would say this is how a wheelchair should think about distance. And there's a slice through it. And Jean-Paul, I don't know if this was common language or I don't know if this was universal or not. He called this the onion. And he continued to help me as we worked on this. And there was a point where pretty early on where he said, well, now you have to produce the synthesis. You have to produce the onion. Like, I'm nodding. It's like, I have no idea what he's talking about. But we figured it out. So that's a slice through the onion, showing several of the families. And, well, okay, there's one other thing I learned about optimal control. And I'm not sure I've exactly heard people say this. I think it's implicit. I had the privilege of being a newbie, a beginner, dropped into the deep end of the pool, hanging out with these guys that know the mathematics that I didn't know, and knowing how to use that mathematics to produce optimal controls. And so when somebody new walks into the room, sometimes they notice things that everybody knows, and so nobody needs to say them. And so maybe this is one of those things, I don't know. But there's something I learned about optimal control. And how did I learn it? was basically from this review. When we first submitted one of these papers, we got a review. This isn't in the review. This is the review, okay? And at the time, I thought that was outrageous. Now I look and I think, that's really nicely succinct. What's that?
I don't think they read the paper.
Yeah, well, actually, he was right, because they rejected the paper. A similar paper somebody eventually did read. Now, why did he think this? Obviously, he was not into optimal control. And my assumption now is that he looks at the phrase optimal control, which was in the title of the paper, and he figured that it might mean the best way to control something, because that's sure what that title looks like, okay? But I think optimal control means a lot more than that. So does it mean how you should control things? Well, sometimes it does, okay? Probably not the optimal controls that I just derived, not the shortest paths, right? Is it about the best way to control things? Could be, maybe not. In my case, not. Optimal control transcends issues of control, and it addresses these very basic geometric aspects of the robot. So let's see, I'm going to refer you to one of my favorite books here, Geometry and the Imagination by Hilbert and Vossen. These guys wrote this book. They got straight to the point, okay? There's no mealy-mouthed, talking about how great geometry is. It starts right out with the simplest surface is the plane, the simplest curves are plane curves, and of these, the simplest is the straight line. The straight line can be defined as the shortest path between 2 points, or etc., right? The first paragraph of my favorite book in geometry. It's that basic, right? It's about as basic a geometrical thing as you can talk about. So if you're a wheelchair, what is a straight line? The optimal control for shortest paths, the optimal bounded velocity for your kinematic model of your robot, that's a good place to start. Okay, that's one way to define a straight line. And then how do you think about distance? The onion. This is the level sets of the metric. So that's the way I look at it. There was some work following on. So Balcom, in particular, Devin Balcom, did some very interesting things, actually working at times with Steve, I think. Yeah. And anyway, but no time to talk about that. One last story I want to tell you, just take a second. Jean-Paul changed my life a second time. I had the great privilege of dining with him and his wife one time, and here comes the big reveal. Okay, I had no idea what we were going to have, although Jean-Paul did tell me it took 3 days to make, and so oxtail stew. And I went right home and bought a big iron pot and taught myself how to make oxtail stew. So you're all invited. If you find yourself in Atlanta, send me a note. Give me 3 days' notice. I'll go find the ingredients, and we'll have oxtail stew. And that's it. Thank you very much.
Optimal control for wheat robot. So now we moved to legged locomotion, and it's also a pleasure and honor to introduce Aline Albuscheffer from the DLR, from the German Aerospace Center. Aline received a PhD in automatic control from TUM, Technical University of Munich, and since 2012, he's the head of the Institute of Robotics and Mechatronics at DLR. His research interests include mainly robot design, modeling, and control from a flexible joint, variable, compliance robot to force control, physical human-robot interaction, and more recently, bio-inspired robot design and control. So we received several awards for IEEE Best Paper Award for transaction paper and conference IQIOS paper. And he was strongly involved in several European projects, and also, of course, as you know, in the development of the DLR lightweight robot. And so today, Aline's talk is related to another line of research explored more recently by Jean-Paul to understand how human locomotion principle could help and be transposed to robotics. And so Aline will present some results from his ESA advancement project and runners that investigates how the new techniques can help, exploiting resonance body effect can increase the performance of locomotion for leg robots.
Thank you. Thank you very much, but I have some trouble connecting, obviously.
Sorry.
It's HDMI.
So he was perhaps waiting that I finished the introduction, no? No.
He's doing some strange things, but not more than that.
Mm-hmm.
That's a shame. I guess. Let's try it one more. Maybe. Usually it's. Well,
Is it? Not true. No.
Does not look well.
No, it's not coming.
Looks like maybe we have to switch and check in the break. I mean, I could try to change the resolution, but we will just waste time.
Yes, or to send if you can copy.
It's long, so then we would need to switch to the next presentation maybe, and then if the next one is ready. Yeah, but it's a big presentation. It's a gigabyte, so it takes a while. Maybe should we switch to who's next?
Done.
Do you mind
No.
jumping in? Okay, then let's try. Sorry for that.
No problem. So I introduce briefly the next speaker, the last speaker of the session, with John Canny.
Okay, I need
Yes, professor in computer science at UC Berkeley. John also earned a PhD in computer science from MIT, and also supervised by Thomas Lozano Perez, and for which he earned the ACM Dissertation Award for his groundbreaking contribution showing complexity of robot motion planning with algebraic roadmap methods. John is Packard and ACM Fellow and made important contribution to different research domains, ranging from computer vision, robotics, of course, AI, machine learning, and more recently, human-computer interaction. So, the talk will concern recent work he's doing on explainable and advisable self-driving vehicle control in order to improve the acceptance of trust in this system. So the floor is to you.
Thank you. So it's a pleasure to be here and reflecting on Jean-Paul's work. So I've had a long trajectory in computer science and in and out of robotics, but in the early 90s, I was doing non-holonomic motion planning and interacting a lot with Jean-Paul. So I have a brief story from that period when I visited Toulouse and had a very nice dinner with Jean-Paul at a restaurant that he liked very much, which on the menu had carpaccio de boeuf à volonté, which is all-you-can-eat beef carpaccio. And I thought that was, maybe a little bit risky since it's in Toulouse, which doesn't have exactly cool weather.
But I thought 1 or 2 plates, risk is probably pretty low. But we went to the restaurant, and then I realized that he's an optimum control guy. And the minimum cost solution for all-you-can-eat beef carpaccio is order all-you-can-eat beef carpaccio all evening. So we immersed ourselves in a very nice conversation about robotics and sort of lost track of time and how many plates of beef carpaccio we'd ordered. I'm pretty sure I got to about 8. And at that point, the very thin beef was starting to look really thick. And so I had to stop. But Jean-Paul did another 2 plates and kept smiling the whole time and seemed really happy. And I guess, the story has the expected end. So the next day I did suffer from some problems. I think of it as BGV, which is bathroom at grande vitesse. And so I recovered after a while and saw Jean-Paul, and he was still smiling, which shows he's a better control person than I am. Anyway, so I'm going to talk about 3 different projects that are contemporary work. So this is in the area of human-robot interaction, which was close to Jean-Paul's interests later in his career. And so what we're trying to do with this work is develop models that sit on top of self-driving vehicle controllers that provide some understanding and explanation of what they're doing, hopefully to improve acceptance of those models by human passengers. So in this work, we're not doing optimum control. We're relying on deep neural networks because they have a lot of flexibility and they can deal with a lot of real-world situations that are very difficult to formalize and plan for. But, by making that trade-off, by relying on, instead of lots of data and scenarios that are real-world scenarios, you lose the understanding that you have from formal models and, control techniques. So the idea of the explanations is to put some of that back, give the user some understanding of how and why the vehicle's behaving the way that it is. All right, so we'd like to enhance trust. We'd like the user also typically to have understanding in the sense of being able to expect or predict what the vehicle might do in different situations. And also to facilitate the user being able to express to the vehicle how they would like it to behave. Perhaps, driving more carefully or driving more aggressively. And the explanations ideally, because the user is probably doing something else in the vehicle if it has an automatic driver, they should be ideally not using the user's hands or eyes. So ideally, speech is an appropriate medium for explanations. All right, so an interesting challenge, though, with explanations in the context of self-driving vehicles is that perhaps the easiest first way you might attempt to solve the problem is by using human explanations as a training data set. One challenge, though, is that people, when they're explaining their own actions, have a strong bias to represent themselves as idealized drivers and not admit to mistakes or faults. So this list is a list of actually reported explanations of accidents. These are all English drivers, by the way. French drivers, I think, are safer, but and American drivers. But these are examples of things that people actually have said. So I'll just pick out one here. I bumped into a lamppost, which was obscured by human beings. So it's funny, but it's also, it's actually encoding a real bias which people have, which is sometimes called the fundamental attribution error, which means that if you did something bad, you tend to blame something else, the environment or other people, whereas if somebody else does something, then they directly get the blame. So a challenge with using this kind of data is that you don't really have ground truth because people are actually, more than explaining what they actually did, giving an explanation in terms of what they should have done. So a priori that seems like a negative bias, but we'll see right towards the end of the talk that it's actually a useful kind of bias that we can exploit in a different way. Okay, so also when people give explanations, at least in this kind of context, they're trying to give a causal explanation, which means they're explaining some phenomena or observation in the environment as a cause of the behavior that they made. So simplest case is if the vehicle slowed down approaching a stop sign, the explanation would be that the vehicle slowed down because of the stop sign. And what that actually means, if you sort of extrapolate in a logical sense what the meaning is, that it did slow down because of the stop sign. It did slow down. If there was no stop sign there, it should have done something different. All right, so the stop sign had some kind of direct and causal influence on the behavior of the vehicle. All right, and these explanations are actually coming from a literature in psychology on explanations, which gives principles and best practices for human explanations that we were able to draw from. And at the time, Tanya Lombroso was actually at Berkeley. So the first attempt at explanations of how and why the vehicle behaves the way it does is to use visual attention. So this is inline visual attention, meaning that there's some kind of multiplying element. We can just maybe focus on one part of this big picture, because I'm not putting the right, is it the button or something else? Ah, okay, thanks. Yeah, so there's one, I'm still not getting it, huh? Oh well. There's one multiplicative element which has the pi in it. You can see over towards the right there. It's an inline multiplying element. Okay. Cheers. Okay. Yeah, it's an inline multiplicative element, which means that the vehicle controller, which is over here, along with figuring out how to control the vehicle, it's also computing an attention mask over the input. So in other words, it's focusing on certain parts of the image in a multiplicative way, which means effectively it's not looking at certain areas of the image, it's zeroing them out through the process of the pipeline through to the controller. So this kind of attention is very useful because it gives us ground truth for things that are not relevant to the vehicle's behavior. So it's similar to visual saliency, but it's a slightly stronger notion because it formally removes stimuli that are not relevant. Okay, so in other words, it defines true negatives, areas of the image that don't receive any attention weight, can't have an impact on the output. However, you have a problem that generally the attention's a bit too diffuse. It attends to lots of areas of the image that may have an influence, but in practice don't have any influence. So in other words, it has a fairly high false positive rate. So since we have a notion that we want important areas of the image to have a causal effect on the behavior of the vehicle, we can actually do that with a direct measurement. If we first cluster the attention into blobs like this, we don't have objects yet, they'll come later on in the work, but hopefully those blobs are aligned with objects that are part of the image. So the simplest way, if you like, of segmenting the image at this level, very elementary level, is just to cluster the blobs, which produces some discrete elements that you can then mask selectively, feed through the controller to see if it changes its output in a significant way. So it's a calculation you can actually do if the number of blobs is not too large. All right, so yeah, so in this plot you can see some attention maps for different frames of video from a sequence, from actual scene. There's something else going along on this vertical axis that's not super important, but there's a formula that regularizes the amount of area of the image that's attended to, which is this lambda parameter. And you can force the attention before this causal filtering to be more sparse by making that attention weight a little bit higher. So, okay. Here's the effect of different attention weights. It makes the image generally a little bit more sparse as you increase it. But there's a trade-off. As you make the attention more sparse, attend to less of the image, you also tend to reduce control accuracy a lot. Like with this very large value of attention weight, image is very sparse, but you also have very poor control because it's evidently missing some actually important areas of the image. So these, just to clarify, I didn't fill everything in, did I? So these are areas in the controller's direction or acceleration relative to a human training trajectory. And the model becomes more accurate generally with lower attention weights, but on the other hand, there's a small range of difference. So it doesn't hurt you too much to use this kind of attention, and we can achieve a little bit more sparsification using the causal filtering that I described. So what we're aiming at here is generating a fairly simple and fairly sparse heat map across the image that gives a user that's interested enough to look at those images some idea of what the vehicle's attending to when it's making control decisions. All right. And very quickly, we don't quite see an improvement from adding this attention layer on top of the vehicle, but it doesn't hurt performance very much. I'll just summarize those results. It's not super important to look at all of them. So where we are now is that we've been able to do some sort of annotation of the scenes, individual frames of video that help us understand which parts of those images are important for the controller. But as we said earlier, we'd really like to get textual explanations of what's going on that could be fed to the driver with speech. So yes, and the secondary advantage of having a textual explanation is that you can say what kind of effect the stimulus has, as well as what the stimulus is. Whereas with the heat maps, we only get to see which area of the image is causing some effect. We don't know what the effect is necessarily. So when human beings make text descriptions, when human beings make text explanations, there's also a description of the thing being explained. That's actually quite important to resolve ambiguity. I'll show you some examples in a moment. Actually, there's some here. So a human being explaining the scene up here would say the car is heading down the street. So that's just a description of what's happening because the street is clear. And sometimes the descriptions might be a little different for the same scene, so it's important to have them in there explicitly, or the explanation often won't match. So the very high level here is that what we're trying to do is generate a text explanation that somehow really encodes what was important for the vehicle's behavior. And as we said earlier, that's kind of tricky because human beings arguably aren't doing that when they explain. So we've got to try to do at least as well as human explanations, hopefully maybe a little better. And we do that by using attention twice. So there's visual attention that we saw earlier, these attention maps that were being used by the controller in a kind of natural way in line. And then we also use an explanation generator that has its own heat maps. So in other words, when the explanation generator is another neural network, when it's describing a scene, it's attending to certain areas of the scene, and hopefully if it says stop sign, it's actually attending to the stop sign. And by then aligning those two different models, the attention from those two different models, we hope that the explanations are actually salient to what really was driving the vehicle, if you like. Okay. So at Berkeley, we acquired a quite large data set, which consists of these pairs of action descriptions and then justifications. So here's some examples. Basically, people give these in natural language, but they are sort of encouraged or coached into using some kind of delimiter, like these ones, between the description and the explanation. So perhaps most complicated slide I have here. Here's the driving controller again. It has its own attention here, attention map. It's outputting control signals here. And then we generate explanations in one of two ways. The first way is to use the attention from the controller directly as the attention of an attention-driven description module. So we're really forcing it to basically not be able to see anything except what the controller saw. And yeah, that will generally generate some reasonable explanations. A method that works slightly better in practice is to give the explanation module its own visual attention maps. And while you're training, use an alignment loss between these two sets of attention maps, which are frame by frame because it's video. And you're basically teaching this explanation module in general to attend to the same things that the controller is attending to, but you're not forcing it to actually look at the same things necessarily when it's running live. Okay, so that's the loss between those two elements. And I might just, in order to stay on time, go a little bit quickly through this. But anyway, it generates explanations. They're not always the same as what a human would say, but they're generally capturing some of the same sense. And so here's the two things running. There's a controller running and generating headings and accelerations. And down here, there's some explanations being generated about what's actually happening. And you should, yeah, these are the ones coming from the controller. And, you know, there's a lot of those kind of events of just driving forward without much happening and then stopping. Hopefully it gets that. All right, so let's go. Pretty dense slide. Generally, it does best with the weakly aligned attention, which is having a separate attention map for the explanation generator. And these measures up here are all textual measures to compare the explanations generated by the vehicle with human explanations, which, you know, the human explanations, we want to take some care not to worry too much if we're not doing exactly what the humans are doing, because the humans are not necessarily always explaining. They're sometimes giving normative explanations of what they should have done. Okay, so an interesting thing happened, or is possible once you do this, which is you can start looking at the statistical distribution of words that are coming out of the explanations and compare those with the human explanations. And one word that's underrepresented is pedestrian, which is very disturbing, but perhaps not too surprising because the model is looking at actual video of drivers. Pedestrians have a limited direct effect on the controller. They have a limited causal effect typically because mostly they're walking across intersections where there are red lights or stop signs. So the system already attends to those cues and understands them, and it relatively rarely sees, in the training video, sees pedestrians walking out in the middle of the street and doesn't understand the important semantics of that. So that's obviously a concerning weakness of that kind of model. And so it steered us towards doing what we call advisable models, which is where humans can have direct input on what the vehicle should have done. So, all right, so we've had explainable systems where, you know, we have a description of an action and then a cause. And you can think of that as if you put it backwards, it becomes a kind of a condition-action rule. So I stopped because there was a red light. Generally speaking, you should, which means you can take these descriptions and turn them into rules. And so that's kind of nice because we already have this big data set of condition action rules coming from BDDX. So what we're hoping, though, is that we can extend them with more general advice, potentially even, you know, a driving manual or other kinds of human texts, or input directly from a driving instructor who sees the vehicle do something that they don't like. So, and yeah, as I said before, an explanation often in practice is an encoding of a normative rule. That is, I stopped because there was a red light, and I should stop if I see a red light. So we took the actual descriptions from all of the BDDX data and turn them back into these kinds of rules, and then put them into the controller. And I think this is, yeah, it's just repeating what I just said. And built this system. I guess I lied to you. This is more complex than the other picture, but basically the key thing here, the thing to pay attention is a sequence-to-sequence model. So basically the front end here is similar to what we saw before. It generates, though, this time instead of descriptions and explanations, it generates just the, let's see, the explanation part, which is the condition. So it generates just the conditions, and then we train up a sequence model or a text-to-text translation model, if you think about it that way, which goes from the conditions to the actions. I've got to be careful with that mic. Goes from the conditions to the actions and generates the action that the controller should take based on the text input. So this works a few years old, and things have moved incredibly fast now, and people are doing similar things now with massive language models to sort of produce some kind of description of what's happening and then prompt a general purpose model to produce a reasonable action. But anyway, we didn't have that stuff back a few years ago, so we used the condition action rules sort of reversed to do this. And it helps. With that advice, it actually reshapes the attention map slightly, and you get a little bit more attention on some pedestrians in the right-hand image. And more generally, yeah, this is, yeah, I'll keep going because I want to finish on time. I'll just show you some videos that show the encoded advice from a BDX data set helping the model in some slightly more difficult conditions. This is stopping at a stop sign, excuse me, a stoplight in the rain from a simulator called Carla, which is a widely used locomotive simulator. And yeah, you see it doesn't quite succeed by itself at stopping under those circumstances. So it stops a little harder on the left. And unfortunately, the video times out when it stops. But and you can see another situation with a stop sign. How are we going? All right, so keep going. Yeah, so I think I don't want to run over. We did a human evaluation with a short survey that's shown over there, and the quick summary of the results are that with advice, with the compiled advice, we were able to do 3 difficult scenarios with higher success rates. We had actually 100% failure rates without the advice built in, and we dropped that to around 25% or less by adding advice. And perhaps the most interesting result from this work is that there's a huge increase in user trust for these kind of systems if you can demonstrate that they're advisable, much more so than just explanations alone. So these are just like at scale histograms of how popular the respective answers are between I do not trust the system gets a 1 score, through 5, which is I trust the system, you know, a lot. And you can see without any kind of explanation, people generally don't trust the controller very much. It gets 1s and 2s. When you add explanations, you still get mostly 1s and 2s, but you get a few 3s, 4s, and 5s, but not very many. And finally, by adding the advice back again, you push it all the way to the right, most of the way to the right, and mostly get positive scores from users. And finally, people thought it was better once you add advice. So it's a useful, you know, it perhaps unexpectedly had more impact than our original goal, which was to improve trust in the system via explanations. We actually found the explanations didn't do very much, but the advisability did. Okay, so I'll stop there. Yeah.
The statistics at the end are interesting. The statistics at the end are interesting. I'm wondering, how do people respond if you give them a car and they can give it advice and it's nodding its head, so to speak, but it actually doesn't use that advice at all? They
Yeah, we
notice
didn't
that
do that.
difference?
We always showed them something like those videos with and without the advice, so they believed that it was doing something. I guess it's a good question. Yes, what would have happened if we didn't give any demonstration? We didn't do that. Good question, though. Yeah. Maybe, I mean, we could just show them that video and it may not have actually done anything. So that's the other thing. So you could give them a non-realistic demonstration that it's doing something. And that should work. Okay, sure.
Yeah, thank you. I gave it another try because some of the videos are not running in Philip's computer, but it doesn't seem to work. So let's switch to that one. Yeah, looks like it's something with my presentation.
So you can change the slides.
Sure, but we are still missing. Yeah, it's contagious.
I think it switched to the American system, so if you're coming from the US, it will.
If you try to put back your presentation, you want me to
Should
present
be
it
related
again?
to my presentation, I guess. I mean, he even stopped. The presentation.
If you just have your plain screen without the presentation,
I mean, you could just stop my presentation, but it shouldn't be that. So Apple took control of the system, not allowing any Windows computers anymore.
yeah, but without the presentation, it still doesn't work. Right? It's just USB-C thing.
Yeah, we can use this one, maybe, the white one that was there.
Yeah, where was it?
I have one.
No, but it was directly the USB-C thing. It was a USB-C cable. Where is the USB-C?
Je sais pas s'il y a quelqu'un de technique.
Il y avait le régisseur, mais je ne sais pas où il est parti, le régisseur. So it doesn't work on your computer either?
No, I tried it on mine. Let's try this way.
It's on a key. If you have another computer, maybe if we try another one.
Sure, we can try mine.
It will break yours as well. My presentation is either. No. All right.
Mine is a Mac.
No, but I mean, I could copy it on here.
I think it's the same.
Oh.
If you want to try. No, it's not this one.
This is weird. Je peux peut-être essayer de trouver le régisseur qui est... I'm going to try to find a technician.
Excuse me.
Yeah.
Is it Adele?
Yes,
Maybe
it's
it's not
Adele.
this one. I guess should work with this one.
I mean, he had a computer running before, right?
Right.
So you had your computer, right? You used that one for the introduction?
Yeah, for sure. It was working well. So maybe it's the...
Maybe they need to reset the system.
Yeah, so the person who is taking care of the YouTube things went to see the register.
No, I'm sorry. So this one does not seem to work.
John is trying to copy it.
So can you try to connect your computer again to see if...
I'm just copying it.
Okay, sure.
About a minute.
Sure.
Hey, John. I know it's radical and ugly, but I solved this problem once by having a second computer and use its camera pointed at my computer.
That's interesting.
Yeah. You can try.
It's not my computer because his computer also is not working. You mean the system here of the projector? Yeah. So there's nothing to reboot over here.
We should have a technician in 1 minute.
Okay.
I apologize.
I mean, do you want to...
Oh, I have so many videos.
Do you want to just work? You could also just work from PowerPoint without full screen. I need my connector, the white one.
The white one, which is over here.
There.
The one we lose
But there was,
anytime.
There we go.
when we started, there was a connector. Where did it go?
I think
It probably
this
went.
one, no?
No, that's mine.
You checked?
What's that? No, I mean I brought it up here when I did my talk.
What happened?
So it was already missing. Yeah.
So it's maybe Mac.
But did you take the connector? Do you still have the connector?
All right. Let's see. Where's the mouse? There we are.
No, I think it's not a story of computer. It's the story of the system.
That's very strange.
We can try with this connector. Maybe it's magic.
Yeah,
That's
maybe.
the name of the
No, but he has
I have the
I mean,
method.
he just played with that,
True.
Yeah,
that
that's very
computer
strange.
before, right?
Yeah. Let's see.
Ah.
Give it a second. That's very strange.
It's working longer this time.
Yeah, that's totally.
That's weird.
Yeah, you can try that one.
Yeah, we can try that one. Okay, so maybe the magic.
Il marche?
Non, ça marchait impeccable.
On va juste essayer.
Ça n'a pas marché non plus. Okay, I think we are going to move the pause. We are going to have the pause now, and then we'll have the talks after that, and hopefully it will be fixed by then. Sorry about that. I apologize.
Yeah, I'm well.
I don't think it's you. It's that.
Yeah. Yes, yes. You tell me when to start.
Okay, so I already introduced the third and now last speaker of the presentation. Yes. And so now that the system is working, please come inside. It's time. And now that the system is working again, we will the pleasure to hear the presentation of Aline on the locomotion and the recent work he is doing in his RC project.
Yes, so thank you. I hope it's worthwhile, all this effort. I'm back with my computer. And I will talk about a geometric perspective to nonlinear oscillations with application to locomotion. And yeah, I focused on this project, which is on my current ERC project, because it was very much inspired by the work Jean-Paul has done. He has an ERC project also on geometry and locomotion. And we all know his presentations. He was a great scientist, but also a great presenter, right? Being able to conceive in a very intuitive way the things he has done. And his main idea is about studying the geometry of motion, but also, principles of efficiency and in human and robot locomotion. And you see here the Poincaré map, a tool for searching for periodic gates. So there's a very strong link and actually a direct link of inspiration to what I have done and what is my ERC project about. I'm looking also at locomotion, but from an additional perspective of studying oscillations. Probably my big part of my research career was linked to oscillations. I started fighting them for maybe 1 or 2 decades with Alessandro De Luca and others, and then I came to the point of loving them and trying to use them nowadays. And of course, the motivation is that biology exploits elasticity in order to excite nonlinear oscillations, but still in robotics, I think we do not have the right mathematics to do so. So I started an ERC project, well, because I'm at the German Aerospace Center, the motivation was about space exploration, but actually the main and deep motivation is really understanding, the dynamics behind and how it can be exploited to understand biology and to improve locomotion. So from biomechanics, of course, we know those pictures about the cost of transport of animals, and all robotics groups are trying to pinpoint their performance, and we know that still general robots are below in terms of performance than biology. And one reason for that is probably that in biology, animals go into resonance modes for different gates. And the biomechanical experiments show that, for example, horses switch between different gates depending on the speed to get into resonance. And so every gate has the speed where it's most efficient. And then there's a very inspiring work by David Remy and his group showing that if you take a model, this is a very simplified model with massless legs and so on, but you take a passive model, give it the right initial conditions, and then most of the gates known for horses will emerge automatically. So they are embedded in the dynamics of the system. There's no control in here, just the right initial conditions. This is found numerically, and Well, I think I still have to stop for a second because it's going into automatic switching and I don't like this. Okay. And the difficulty is if we just think about rigid bodies in a potential field, we think about those nonlinear systems as being chaotic systems if they are not controlled. You can see on the left-hand side the image of a double pendulum. It is just a mechanical double pendulum, right? And we experience that also for our system. So just elasticities and multi-body systems is a very complex dynamics. And the question arises, how is it that at the end biology succeeds to bring so much order with all these latencies in the neural control and all these limitations? And the tool to study that is, of course, the analogy between muscles and bones on one side and rigid bodies, springs and actuators on the other side. And it turned out that what we are looking at periodic motions, which are far beyond the linear regime, because running just brings you at the limit of your actuation performance. And it turns out that studying this, the ideal tool is geometry, and this brings me to Jean-Paul. And in this particular case, Romanian geometry, right? Just to start from some very simple facts, looking at a linear oscillator, everything, something which every student in engineering should know, then the orbits in phase space are ellipses. And so assuming you have a conservative system. And if you just look at the projection on configuration space, it's a line where you oscillate back and forth on that line, right? And of course, again, standard engineering, of course, you can diagonalize this and then you have imaginary eigenvalues. And then this is also extended to nonlinear systems. And just a simple example, you have two masses, two springs. You have two modes. One is swinging in phase, the other in antiphase. And if you look in configuration space, then again, you will have two lines on which the system will oscillate back and forth, right? And all the other directions, you would have a complex coupled oscillation. So now it was known since the 60s that also some nonlinear systems have those properties. For example, if you have a cubic spring, then you would have something which is not really sinusoidal, but still you will have a line, and if you initialize the system on that line, it will oscillate back and forth on that line. But in the nonlinear case, this is generally not the case, right? But it turns out that you can generalize this idea of saying that in the nonlinear case, you will have a curve which, again, under some conditions for constant energy, if you initialize your system on that curve, it will stay naturally on that curve without any control. So it's a stable orbit. And in order to understand and study that, you need to go from Euclidean geometry to Romanian geometry. And there was a talk I think in Philippe's presentation, showing that it's about the way you compute distances in Euclidean geometry and in Romanian geometry. Just, a short introduction for those who are not so familiar to the use. You need to go from planes to smooth manifolds. And of course, the configuration space of a robot, let's see, at 2 degrees of freedom. So robot is this square where you then identify the opposed sides. Or if you go, if you would like to have it smoothly, then it's a torus, right? Because you glue the opposing sides together. So it's all about geometry and shortest path on the torus, as we will see. What's the point with the shortest path? Well, in differential geometry, they are called geodesics, right? And if you search for the shortest path in a Euclidean plane, of course, you minimize the distance over different families all the families of curves, and then you end up with a straight line. Where if you're on a manifold, for example, on a sphere, of course, there's no straight line, but you could do the same thing, right? Taking all possible paths, minimizing the distance, and you will end up with another shortest path, which on a sphere turns out to be a segment of the great circle. And of course, on manifolds, the shortest path is not a straight line, but what is called a geodesic, and that's why when you look at those maps of airplanes, they fly on geodesic parts and not on straight lines on the Earth, right? And how you do that, basically you integrate the velocity with respect to a special cos function in order to get the length of the curve. So you take the velocity vector, integrate along the curve, and then take the minimum of that, right? And if your cos function is the inertia tensor, then this geodesic minimizes kinetic energy, right? And this proves to be so if your norm of the velocity, is the norm given by the kinetic energy. And this proves to be a useful tool to generalize from linear to nonlinear systems. Why? Well, we all, in robotics directly jump to the Lagrangian formulation of motion or to the Newtonian formulation. But actually, this comes, as we all know, from the principle of least action, which most of the time we do not really consider in detail. What does it say? First, let's take the integral of the Lagrangian, where we ignore potential energy, but just take kinetic energy. Then the principle of least action is just saying that the nature is such that the dynamical system will take a path which minimizes this cost integral, which is the norm of the velocity with respect to the inertia tensor. So basically, the mechanical system is following geodesics with respect to the inertia tensor, right? So trajectories of freely moving multi-body systems are geodesics with respect to the inertia tensor. And basically, this means that you can reduce for constant energy dynamic planning to pure geometric planning. So you can have an analogy between a double pendulum and a point mass moving on a surface of appropriate shape. And basically, you push all the dynamics into geometry, and at the end, you have just Newton's law of a point mass on a surface, right? And, well, this is not new, but it might be an interesting news for people used to do motion planning, because they are used to do motion planning with cost functions where the shortest path is not a straight line. Of course, they have different cost functions for obstacles and so on, but just imagine of taking your mass sensor as a cost function, and that's how you could plan those motions. Then you will ask what happens if you add potential energy. Actually, this is something which is, I was surprised that in robotics is not so widespread, but in mechanics, Jacobi introduced that, so not the Jacobi matrix, which we all use, but the Jacobi matrix. And you can do the same thing with a new metric tensor, which is just basically potential energy times the mass matrix. So it's E minus the potential energy, which is the kinetic energy. And for historical reasons, there's this too. Meaning that also, if we have the general dynamics equation we know, robot dynamics generally reduces to the motion of a point mass on a high-dimensional manifold if you are in the conservative case. And that's interesting, because this brings you, and I don't know if here at Collège de France we have mathematicians or theoretical physicists, but people doing differential topology and differential algebraic topology and differential geometry, they study geodesics on different types of curves, and there's hundreds of years of mathematical results about this kind of systems. And the first time I came across that is maybe 15, 20 years ago, in the book of Arnold, where he shows somewhere just this picture and showing for every two numbers, n and m, you can find a trajectory of the double pendulum which rotates n times around one axis and m times around the other one, right? And just by contracting rubber bands, so instead of shooting what we're doing in optimization, you just contract rubber bands and computer sort this path, right? Which is very interesting. And I asked actually last week for today one of my PhD students to just contract for the double pendulum, this kind of 1, 1, 0, 1, and so on trajectories. This is how they look on the torus, and this is how the dynamics looks like. So indeed, you can find them, and you can need almost no energy to stabilize. So we have seen this double pendulum, which is unstable. You can find, some orbits turning once around one joint and no time around the other one. You can find even more than one, but those mathematical theories guarantee you the existence of at least one solution, which is different from Poincaré map or other shooting approaches. And we remember, this video I've shown at the beginning of being chaotic. Yes, the system can be chaotic, but can be also very, very irregular, actually behave like linear systems. And that's the interesting insight I've got from out of this. And well, these are this kind of circular parts. So just take a rubber band, wrap it around the torus, then let it contract with respect to that matrix, and then you will get an optimal trajectory which needs no energy. Well, but you can have two types of periodic trajectories, of circular type as the one presented, and then this kind of line type. And these are the ones we generalize the eigenmodes of linear systems. And mathematicians called it braking trajectories because, you know, you move back and forth and brake and stop at one end. And, well, let's go very quickly through that. But actually, there's a conjecture which is still not proven by a guy called a mathematician from Heidelberg called Seifert, which says that for every classical conservative mechanical system, which has a equipotential line and equilibrium, you will have at least as many this kind of periodic orbits as degrees of freedom. And he could prove that there exists at least one, but he conjectured that n exists, and I'm in contact still with mathematicians trying to prove that with higher and higher accuracy for our case, right? Okay, now the question is, when is this the case? And I will go just a little bit in detail. So assuming you have a curve, you'd like to ask yourself, can I make this curve to be an invariant manifold for the system without control, just mechanically, right? And we published a paper with a PhD student of mine and Stefano Stramigioli showing that the condition for this case is that you make this curve to be a geodesic of the multibody system, and then the acceleration due to the potential is tangential to this curve. So that's a necessary and sufficient condition, right? If you would like to turn any curve into a stable manifold, right? And a very trivial example is this one, right? Hopping in place, of course, because of the symmetry, you can hop higher and higher, and the system, although coupled and nonlinear, will stay on that manifold. But it turns out that in general, so, you know, you take a double pendulum or a full robot, this nonlinear curve, so won't be invariant for every energy, but if you take another energy, the curve will deform. And just as an example, you know, take the double pendulum, and this is how those modes look like. So the small cross here are the linearized, so the eigenvectors of the linearized system, and then you increase the amplitude, and then you will always still find oscillations. We have a MATLAB toolbox which gives you those oscillations, but they stand to bend and curve. And this is a representation in 3D, so at small amplitudes you have linear oscillations, and then you increase the energy, you will still have periodic motions, which is very interesting. This is how they look like, for example, for a double pendulum. It very much looks like an arm, you know, with an antiphase oscillation. You remember the two masses, and the in-phase oscillation, and you can imagine some throwing motion or some locomotion based on those eigenmodes, right? And again, it's natural, and it does not need any control other than stabilization. So, you know, very quickly, I hope that I could give you an overview that, you know, initially we thought that searching for this kind of periodic motions with Poincaré section optimization is about, you know, looking for the needle in the high stack. But now it turns out that there are plenty of needles there in the high stack. There are even some theorems guaranteeing you that there are plenty of needles, right? And there's also some structure. So there are different types of needles. This circular shape periodic orbits, and these break orbits, and what we call strict modes, and so on. So, you know, I thought I will research that for 6 months and then start building robots. Now, after 2 years, I'm still digging into, you know, it's like Alice in Wonderland, where they go in the rabbit hole, and it gets bigger and bigger, and the whole field of mathematics and fields open up. And I'm just trying to, you know, to bring this closer to our robotics community. I think it's worthwhile looking into that. Still some results, some practical examples. If you know about those modes, you could first of all try to design your mechanics such that, you know, those modes, or what you would like the robot to do, is embedded mechanically into the system. And one of my PhD students, Dominic Lakatos, he compared, you know, this two-segment leg with a pantograph structure, and he could show that if you would like to embed a vertical mode, which is just hopping, then the pantograph is much better because you can, you know, the left one just works with zero masses in the links, while the pantograph works for general parameters. And this might be an explanation why biology, you know, uses this pantograph structure very often in legs. And this is a simulation showing that, if you choose the right distribution of stiffnesses according to the theorem I mentioned, you can have a system which, naturally springs vertically without any control, while with the wrong parameters, it has this chaotic behavior we are used to expect it as engineers. Now we are designing a prototype of a quadruped. Good question after Marco and Boston Dynamics having so fantastic robots while still building robots. But for me, there are templates for studying these motions. So this is a 12 degree of freedom robot. The legs are fixed to the ground, 6 constraints. So you are left over with 6 degrees of freedom. And these are the 6 modes of this elastic quadruped. So it has springs in every joint. And then you can start with your imagination and ask yourself, is it running? Of course, we did not design it for them. It just has equal springs in all the legs. And, but we have a material toolbox. You feed in the dynamics of the system, and you get out the results. And then you can use that to, interestingly enough, if you detach the legs and excite those modes, the system, starts doing steps. And this is an interesting one, this twisting, shaking. When you detach the legs, it starts basically doing some walking motions naturally, right? Still, there's hybrid dynamics. This theory does not, is not extended to hybrid dynamics, to all these cases. So still a lot of work to be done, but I think it's an interesting way. And they are, by the way, very easy to excite. So that's our, prototype just 3 weeks ago set up. And you just take a bang-bang controller, Pontryagin principle, as we heard before, and you can easily, excite those modes. And we are doing first experiments. And again, we have a toolbox. You can take any elastic robot like our humanoid, and then trying now to generate some throwing motions based on those modes. And it's going much faster because you are optimizing just in a n-dimensional space. So velocities are irrelevant. It turns out that you just need to optimize in the configuration space. Well, then, just 1 or 2 minutes on the control. We are used, what we have done with Alessandro and many others for years, control, which a lot of control authority, every millisecond, commanding torques to stabilize. This is a mode of a swing. What people are doing are just letting it swing its mode and just injecting at the right time a little bit of energy to compensate for energy losses. So this is the idea, right? Just take the natural dynamics and just give it some kicks at the right time and let it swing, right? And humans are very good at that. I give you a rod in your hand, you will excite a swinging mode, although, it's a complex system within seconds, right? Well, I don't have much time to go in the control of that, but using this bang-bang controller along the modes which we pre-computed, it turns out that it's easy to excite, those modes, even in contact dynamics where the robot is hammering against a surface. And even, with some objects which you have never known, these are this kind of gymnastics rods. I don't know if you know them. And you are asked to excite them in resonance, and the system quite easily identifies those resonance modes. And, well, these are steps on the way to a robot which locomotes in those modes. We applied that to different models, and some preliminary results on our hardware. For example, on the white robot over here, we have free locomotion patterns which are, well, they are not perfectly on the theory. I'm still working to have exactly proven that we excite those modes, but close to that, and we had some gates on walking, trotting, and bounding, exploiting the resonance of the system. Okay, and of course, I dream of using that also to explain biological locomotion. These are some motion capture data from animals, which I got from a group in Leipzig. They are beautiful, and they show still how complex, biological motion is. It's hard to get dynamic models of those dogs. That's the difficulty, because we are trying to do some, inverse optimal control and to see if they are really exploiting the modes. And this brings me to the end of my presentation. So I shared this view with Jean-Paul of studying biology, trying to understand basic principles on biomechanics control, but also neuroscience, building robots, and then use those robots to validate those approaches, but also to build better robots. That's the particular thing about us in robotics. Of course, behavior of humans is studied by many disciplines, but what we say is what I cannot create, I do not understand. So we really want to prove that the understanding of motion is as good as to allow replicating technologically those approaches. Okay, this is the end of my presentation. Thank you very much.
Yes, Aline, very nice indeed. So, if I understand correctly, the role of control in this context is, one, to bring you toward this natural oscillation, and then probably to compensate for dissipation. So to inject whatever
and
you're
to
losing
stabilize those orbits. They are not necessary. I did not talk about stability because it will open up another hole. But they are not all of them stable. They are periodic if you start on them, but if you get small deviations. But the point is, the control can quickly, you can do some linear control even laterally, locally, to bring you back and to stabilize those orbits and to compensate for dissipation. So still you can't get completely, we won't remain without a job as a control engineers. I learned from that, yes. Thank you.
Hello everybody, I'm Nicola Mercer from Toulouse. So we are now starting a session with a very close collaborator to Jean-Paul. First example with Eishi Yoshida. Eishi is a professor at Tokyo University of Science, and before that he did most of his career at AIST. We could speak a lot of your career. For example, your award, I discovered that you are a Chevalier de l'Ordre National du Mérite. So basically a French knight. I was not aware of that.
But I can write rules.
But what is interesting for us today is rather the mobility of Eishi from first inside the domain, from precise mechanics and network communication to artificial intelligence, from swarm robotics to humanoid robots, and on the planet also from Tsukuba and Tokyo to EPFL, then Versailles, and finally Toulouse. So I was told that Eishi was a key person for deciding the humanoid robot to be installed in Toulouse, and then the Joint Robotic Laboratory follows, which had also a big influence on my career. That's the reason why I'm Toulouse. So thank you for choosing Toulouse. GRL, the Joint Robotic Laboratory, has been known to be very famous in human robotics, and that I think because of the careful work between Jean-Paul and Eishi during long years in Toulouse, and then followed by the co-direction also of the Japanese side of the Joint Robotic Laboratories in Tsukuba. I think Eishi was also one of the colleagues contaminated by the ideas of Jean-Paul of studying together human and robots, like Aline just showed. And your talk today is about that joint study. So, floor is yours.
Thank you very much for your kind introduction. So, yeah, I was completely contaminated. Okay. So, thank you for organizing this workshop. I'd like to thank Philippe and also John. So I'd like to, now I'm at Tokyo University of Science. This is a private university in Tokyo. But as Nicola introduced, so I was formerly as a co-director of Joint Robotics Laboratory, JRL, with Jean-Paul and in Toulouse. So I'd like to talk about our adventure. So it's not really scientific, a lot of episodes, but I'd like to trace the adventure with Jean-Paul. So I can clearly say that the period I stayed in Toulouse from 2005 to 2009 was my most enjoyable moment of my research life. So we started this new adventure for human robotics. At that time, human robotics was not that popular other than in Japan. But Jean-Paul was a very known researcher in motion planning. So I don't know if he was really interested in this kind of new things, but he was even excited. And also, I thought a bit unbalanced, the co-directors, but he didn't really care. So I learned a lot from Jean-Paul, of course, scientific insight and foresight, and also culture. So he has a lot of culture and also open-minded personality. And now I also want to focus on the importance of the sharing the space and time physically. So the time I spent with him was invaluable. And I shared office with him. He was always noisy at telephone, but it was a very, very nice moment. And of course, this is kind of a base of my research thereafter. So briefly introducing this joint lab. So it was, at the beginning, it had a very special structure. There was two sites in Japan and in France. So in Japan, it was co-directed by Dr. Yokoi and Dr. Abraham Makeda. And JR France was co-directed by Jean-Paul and me. So the particularity of this joint lab, initiated by Dr. Kofi and Tanier, we have the same platform. So the HRP2 robot, I think it's still, is it still working, HRP2?
I'm sorry, not.
Not, okay. But it has been working for, I think, around 10 years. So it was good because we developed the software and we can share the results by using the same platform. And then also having a real robot is also a nice thing because we can directly see that your algorithm is working or not by applying to the robot. So it started with IROS 2004. So for some reason, we are still looking for the host laboratory of this JRL. And Jean-Paul was there in Sendai in IROS 2004. And he was presenting this work, planning fine motions over digital factor terms. So it is the PhD student at that time, Gustavo and Claudia. And so I think he was intended to some session of the graphics or human factors, but he was apparently embarrassed that his paper was classified into the human robot. But anyway, so we attended with Dr. Yokoi to his presentation. So I think the reason why that was put in the human session was maybe from this figure. And we thought that it could be very interesting if we can integrate this motion planning and also human robotics. Then after that, there are a lot of discussions and negotiations, and he sent me a letter that I can start in Toulouse, the joint lab, and he also accepted to be a co-director. And we started from almost zero. So we started the Gepetto team. I think there are how many people now?
Gepetto maybe
Yeah,
25.
25. Yeah. So we started at 5 or something when we started. 6. Yeah. So and then, but just starting the team is not enough. So we need to introduce this HRP2. So first the budget, but at that time he had a good project to support most part of the robot. And also, we need to do some public procedures because for the public funding, so some open bid or something. And also, the Kawada Robotics that produce this robot, usually they only lease the robot. But thanks to the Jean-Paul's very attractive personality, so they accepted sale this is a very rare case, maybe not very popular in Japan. So they decided to sell the robot. So it arrived 2006, and we were also worried about this custom for the import, because I heard that in when they imported a Wave vehicle, it was blocked at the airport or seaport because this didn't have a number plate for the vehicle. So we were worried about, but in one day it just cleared. Maybe it looks like human, so it custom cleared. And but we decided to open this platform with other labs but this is kind of national platform provided by CNRS, and we organized workshop for the proposals. And then we did some ceremony to inaugurate HRP2 for the media. So I like to have his live voice, but I don't know if it works.
Je disais dans les titres, c'est une avancée considérable dans l'épopée de la robotique.
Ah, sorry.
Le robot HRP2 a débarqué à Toulouse. C'est le premier robot humanoïde qui quitte le Japon. Il a coûté 400 000 € au laboratoire d'analyse et d'architecture des systèmes. Objectif, accroître maintenant au maximum l'autonomie de cette machine. Marie-Martin et Denis Martin.
Un salut d'artiste, c'est l'un des tout premiers gestes de ce robot exceptionnel. HRP2, c'est son nom, est né au Japon en 2003. Conçu par un dessinateur de manga, sa première caractéristique est sa complexité physique.
Il y a plusieurs prototypes de robots humanoïdes. Celui-ci, c'est celui qui se rapproche le plus de la morphologie humaine par sa taille, il fait 1,54 m, par sa masse, il fait 58 kg, par ses fonctionnalités, mais surtout par son ouverture. C'est une plateforme qui est essentiellement dédiée à conduire des recherches fondamentales en robotique.
HRP2 est le premier robot humanoïde de sa génération à quitter le Japon. Il sait marcher, monter les escaliers, se relever. Acquis par le laboratoire d'analyse et d'architecture des systèmes pour 400 000 €, il n'est pas encore destiné à effectuer des tâches précises, mais ici, durant 4 ans au moins, 10 laboratoires français s'appliqueront à compléter ses capacités physiques pour une plus grande autonomie.
D'abord, remplacer les...
So we started to integrate the motion planning technology with the human robot. So they had a very advanced motion planning result with digital actors. So we quickly tried to integrate this with the human robot. So first we started with a two-stage algorithm, two-stage method. First, we plan the path by using the usual motion planning method with a simplified model, and then the path is transformed into the dynamic walking motion with upper body through what we call dynamic motion pattern generator. And then, but it may induce some oscillation and also the unexpected collision. So we reshape the path and so on to get finally the dynamic walking motion with upper body. So this is kind of integrated result with the last technology and also the human robot technology. So this is dynamic walking, which means that if it stops at any moment, the robot can fall down. So also, we extended. So instead of doing this kind of iterative process, we introduced generalized inverse kinematics and to integrate the balance and inequality and also collision avoidance. In the right figure is that, so you just add the links at the 1 foot, and then it can be regarded exactly the same manipulator to plan, to step, to also plan the stepping. And we extended also whole board manipulation. So this is kind of pivoting So pivoting is that when you move bulky object without lifting. So this is very inspired by the work of Matt Mason. So if it is, we see that if this motion is small time controllable. So this is a very important property for the motion planning. And I've never come up, I would have never come up with this kind of solution without Jean-Paul. So he showed that it is small time controllable by using Lie algebra. And then we did this kind of whole body, combining by the humanoid whole body controller that I showed earlier. So we can do this kind of pivoting motion, and also by, sorry. Doing some combining different modes of motion planning. So when you pivot and the motion, the object, and also combining some free walking motions. So I was almost absorbed with the robotic side of this human robot, but I think at the beginning, the reason why he was excited by this human robot was at the beginning also there was an introduction of Professor Beltos. I think he was looking at far in the future of using this kind of human robot to push forward the science into human. So I think Katia will be talking about this thing, this inverse optimal control thing. But he was also very interested in doing the human side research, also by using human robots. Maybe if you can reproduce the human motion strategy, it can be also tested by the human robot. So finally, I should. This is another episode. So I should leave the last, and he kindly organized the farewell party. Prepare this kind of
boys and girls, this is going to be legendary.
Sorry, so this is Manish, Indian PhD student who brought the Indian crowd. So he was nervous because he wanted me to enter while they are practicing this demonstration. Okay, so this resulted in the 28 co-authored publications. It was a really wonderful adventure. So I have been also get very interested in the research related to human. So we, after returning to Japan, we started to do some retargeting, human motion retargeting, and to also that can be used to evaluate the wearable devices, and also the human modeling by using human models. So it was also very inspired by the collaboration with him. So one of the results is this retargeting, so to reproduce the human motion by human robots. So by this method, research with Dr. Aizawa, so the robot can reproduce the motion, and also we can see that how the human can be, how the human motion would be if you had a robot constraint, so which means that it can show that the classes of the human motion that can be well evaluated by the human and robot. So we did different types of retargeting, and we used it to evaluate the very powerful wearable device to help you to lift heavy objects. Actually, by integrating some sensor-based control with the retargeting, so we can quantitatively show that this device actually generates tens of the Newton meter to help lift up the things, the heavy objects. And also we did human understanding by using IMU sensors, the mass cascade model, to evaluate, to estimate the motion and the mass flow activities, and also joint reaction force in real time. Some other human model is doing planning some supportive device depending on the status of the patient, to reduce the burden to the users. So, so now I like to go further challenges. So I was always interested in understanding human behavior, motion, and also other things. And of course, the human motion is target motion, but we can't really measure what happens inside. So we can use, if the human robot can reproduce its motion, we can see the internal state. And also we can use the simulation to improve the controller model. So this is also related to maybe the Alin's presentation, and we can do it in complementary manner. And then, so far, this has been the motion model-based approach. So, but I like to have some context-rich motions and try to integrate some some learning scheme to model this kind of, how can be symbolized this kind of very complex context-rich motions. So I like to finish my talk by also sharing some many unforgettable moments. So I moved to France I lived for France for 4 years with my family, and he was very, very helpful to support our family, and we did some sushi party at home, and I think this is the same thing that he showed. So this, you can see the same pot here, but it was very delicious, and he was very he had a lot of sense of humor. So this is he is very relaxed, and we sometimes went to expositions to do some demonstrations. And as Nicola mentioned, so fortunately I could get this Automate award. So it was in the French embassy, and Jean-Paul was in Japan, and he also attended. So with Dr. Albert Makeda, who is also here. So thank you very much for your
That's working. So we have some time for questions. Is there any question in the audience? Maybe I have a question. So how much is true about you choosing Toulouse only for scientific reason? What was the personal reason behind the scientific reason for choosing Toulouse?
Do you know this?
I'm not sure.
Also, my wife and daughter was playing piano. So I also asked Jean-Paul if there is a good place to learn piano. So we found, fortunately, we could put my daughters in the conservatoire to Toulouse. So that's another cultural reason.
So the story is true. That's the story that is running inside.
Yeah. But of course, the scientist first. Yes.
Any other question? Okay. HRP2 is not working anymore. That's unfortunate. It has been replaced by Talos. It should be able to run. We are keeping very quiet and protected in the storage. Maybe it's just waiting for you to come back.
So, I'll tell you when I drop in Toulouse.
Thank you again.
Thank you. And also thank you for Jean-Paul.
So we will now have a talk by Katia Mambor. Katia is a professor at Waterloo University, close to Toronto, if I'm correct, where she benefits of the excellent research chair. Prior to that, she was a full professor at Heidelberg University, where she was also leading the ORB research group, so ORB for optimization in robots and biology, biomechanics. So again, influenced by again, this same culture that we find here with Jean-Paul. Like Aishi, she is also an adventurer with a long research stay in Korea, but also, of course, in Canada and in Toulouse, where she spent 2 years. With Aishi, Jean-Paul discovered humanoid robotics, obviously. With Katia, Jean-Paul discovered that we can survive without geometry, using optimal control, numerical optimal control to discover optimal decision for the robot and explore the structure with what Jean-Paul called derogatory linear algebra, covering something that is not geometry. The work that is maybe saying the most of the collaboration between Katia and Jean-Paul was the work of inverse optimal control, which is still influential in the mathematical team in LAS, with both the results and the data set widely used by our colleagues. I think that this optimal control collaboration, inverse optimal control collaboration, is the basis of your talk today. So, thank you very much.
Okay, thank you very much for the kind introduction, Nicola. Good morning, everyone, and thank you very much to Philippe and Jean for inviting me. It's really an honor for me to be here and to talk about my joint research with Jean-Paul, and also how that has inspired my research in the future. So I had the great opportunity to be part of Jean-Paul's team from 2008 to 2010. I was part of the French project Locomotion, which was on discovering the fundamental principles, fundamental computational principles of human locomotion, and to spend, same as HE, really the 2 best years of my scientific career in Toulouse. Before I came there, I came from a scientific computing, optimal control background, and I had spent a lot of time looking at simple passive dynamic style, but controlled, actuated systems, looking at open loop stability, just purely optimal control, just purely in simulation, then moving over to doing complex simulations of human movement, optimization of human movement, and I had just started to get my first real robot, which was a hopping robot. So this is where I came from, and then I had this great opportunity to work with Jean-Paul in Toulouse in this project, and for me it was the first time I could really work with humanoid robots, get close to them, put my results on them. I also had the chance to work with really biomechanical human motion capture experiments, both at LAS and then also at Rennes, the groups of Julien, Armel, and Franck. And we also had that great collaboration here with the Collège de France and Alain Bertos. And I discovered that there's not only biomechanics and human locomotion, but also the neuroscience perspective and the role of the brain. But really, the best part about the project experience were the many really inspiring discussions I had with Jean-Paul about modeling human movement, about modeling robots, and about optimal control in humans and robots, and how we could use that to build this computational foundations. We had different perspectives. Nicola already mentioned it. So Jean-Paul was really trying to convince me of the beauty of analytical optimization, as Philippe has shown it really nicely in his talk this morning. And I was trying to show him that also numerics is not that bad, and there are also quite some nice experiments can be generated by numerical optimization, and also might provide some insights into for further theoretical discoveries. But it was really amazing for me that someone with that experience, as Jean-Paul, was always open to discuss with me. So that was really great. So one of the things we really both were convinced of was that optimality plays an important role, and that there is a huge amount of optimality in natural motions, because motions of humans have been optimized over the course of the evolution, but also the individual learning process and training process of people over their lives, are also of becoming more proficient in activity. So this somehow gave us the justification to use optimization as a tool to study human movement, but and also to generate motions in walking robots. The big question, of course, is what exactly is optimized? I mean, we were convinced that something was optimized, but of course the precise function that is optimized depends very much on the individual situation. So a marathon runner will optimize something else than a sprinter. Small children will optimize something else than older persons or grown-up adults. And also in different other sports and martial arts or dancing, we will have all these different, objective functions that are naturally underlying this human movement. So the question is, what is that? And this brought us to developing the inverse optimal control. So the standard, on the left side, you see the standard optimal control approach. So this is essentially, we have a given model, we have an idea for an objective function, and then we apply that, and we get a resulting solution for the system. But the problem we are facing here is a different one. We are somehow convinced that something is optimized, but we don't know what. But we have observations of the system. So we have measurements of the motions. Usually it's not full measurements, but it's partial measurements of the motions. And now we want to identify what is the optimization objectives that gave us this observed solution. The way we did it is we say there's always a lot of guesses around what an objective function might be. So usually, if you look at sport or if you look at everyday motions, there's always a lot of assumptions around what people might be optimizing, but there's also a lot of contradictory opinions. So you can just take all these ideas and put them in, create a weighted sum, and then let an algorithm determine which of these ideas is there at which importance. So we essentially developed an approach to solve the inverse optimal control problem by a bi-level approach. So in the upper level, we are comparing our current guess of the weighted objective function and what that does to the model, and the solution we get out of that, compare that to the recorded data, optimizing over this weight term alpha. And in the lower level, we are solving a forward optimal control problem for the current set of weights alpha, and then in order to be able to evaluate again for the upper level. So the first problem we applied that to was the problem of finding an optimal path, or rather an optimal locomotion trajectory. So if I'm entering a space and I'm standing at a point A with a certain orientation and I want to go to a point B, what is the path I would be choosing naturally? And this is something that humans just do automatically without thinking, but we would like to know how they do it so that we can also do the same thing in robots and do it naturally. So just give you two small examples. So we have a robot here who starts from the green origin and wants to go to the red target. So we would expect it to not do this very robot-like straight line and then turn, so that the arrows essentially show the orientations at origin and target. So this is what we don't want. But we would expect a human and a robot to do something like shown in the red curve. In another example where the target is just a little bit next to the origin and the orientation stay the same, we would not expect such a curved line similar to the one we had in the beginning, also not something like that, but we would probably just expect sidestep. So the question is now, how can we model that and how can we generate these trajectories so that these solutions come out in a natural way, in an automatic way. We developed that model for locomotion dynamics, for walking, and that may look a bit familiar. It's builds on top of what Philippe was presenting this morning for non-holonomic systems. But in walking, we have the problem, so it's non-holonomic in many cases, but there's a few. So this was the first one I just showed you was a non-holonomic case, the left one, but on the right, it's clearly not non-holonomic, so it's clearly a holonomic way of moving. So actually, we augmented the existing model by keeping the non-holonomic part, but also allowing for sideward motions. We also could have rotations, and now we needed the objective function that generated the trajectories automatically in the way we would expect it. So this was done based on human motion capture experiments looking at many different target positions and orientations, and we came up with a combined objective function looking at time, looking at acceleration in the different directions, and also looking at minimizing the orientation towards the goal, because that seems to be a human tendency to always wanting to look towards where you're walking. That were essentially the objective functions given to the inverse optimal control code, and the pink weights you see were the results, and they were really well able to replicate all the measurements we had done. So one of the important characteristics of that solution, and that's actually also what that last term does, is that something we discovered that the motions are asymmetric. So meaning we are usually not walking back on our own path. So if I go from A to B, it's not the same as if I go from B to A. So in a really cold winter at Heidelberg, a bit later we tried to visualize that. There was a rare occasion that Heidelberg Castle was full of snow for more than a month, and while Suleiman and Manish Srivastava, also two former last students, and visited me in Heidelberg, and we tried to visualize that in the snow. So you see here a person on the left is walking towards the person on the right, and that's the trajectory he's generating. But if he walks back, he will take the yellow one, which is not the same as the pink one he took when coming. So there also were, of course, more systematic experiments done with real sensors to track these trajectories, and we also came up with a good model of how big this asymmetry is in walking trajectories. So later, with Manish and Marina, a student in Heidelberg, we also extended that by saying we also, this orienting towards the goal comes from the fact that we want to see the goal, so we have to take the head into account. And that's also a lesson I learned from the Locomotion project, is that the head is always leading the motions. So we also wanted to include that in the model. So essentially we augmented it a bit more, introducing not just body orientation, but also head orientation, and then having a spring-like coupling term between the head and the trunk. So essentially the head had its control, and the trunk was just leading, driven by that passive element, for which we identified parameter from also a quite big data set. So now we have a model here. You see it for one example motion from the top and from the side, how this coupling between head and trunk orientation works. Currently in Waterloo, we are also trying to extend that to not just these locomotion scenarios, but also to settings where we look at communication and talking to people to improve the body language of robots during talking. Yeah. So what exactly does that help for robots? Because so far we've been mainly talking about humans. So the idea is that with inverse optimal control, you come from human measurements, you have the optimal control model, and then you take that and apply it via forward optimal control to robots in order to generate new motions for the robots. And I think HE also had them. There was also from a paper we did together with Jean-Paul and HE, where it was applied to HRP too. Yeah. Of course, inverse optimal control is really helpful for many other situations. We have and are still applying it to walking motions in very different situations, to yo-yo playing. We also started looking into emotional locomotion, movements of artists while they are doing paintings, and then also for comparing running motions of athletes with and without prosthesis, but then also for different other pathologies. Or how does do cerebral palsy gaits differ from healthy patients or healthy persons' gaits, and also how does back pain affect our styles. So we still think it's a very useful tool for looking into all these situations and for identifying how humans behave and then be able to predict in the future. So after I left us, we also continued to work with Jean-Paul, first in a small ECOT project on generating optimal paths, which had mainly also algorithmic focus. What it was about combining path planning algorithms and optimal control algorithms, and then we applied it to an industrial robot setting and another humanoid robot setting. And then out of that, we also started, prepared having a really big European project, which Jean-Paul also still helped very much to prepare in the beginning. Later, when it finally happened, he was very busy with being in Paris, being in Rome, and then also with his own ERC. So I was also very glad that Philippe stepped in and took the lead for Lars in this project. So that project was about, it's called CoRobot, and it was about developing principles for locomotion and like identifying laws from humans and transferring them to robots, so taking the different embodiments into account. And that was a project in which many groups were involved. Up there was also there, and also from Lars, the HRP2 robot was involved. And even though at that time it was also already quite old, it was really the big power horse of the project, I would say. We did really, really nice things in that. One of the things also following up on optimization that we try to do in this project is to tackle the fact that optimal control is a great tool, but it takes a lot of time. So computational times may be quite large. So the idea was, and that was a collaboration also with Olivier from LAS, where to think how we could combine optimization with motion primitives and with learning, so combine model-based and model-free methods. So the idea we had in this context, which just very briefly, is to use optimal control just to generate training data by applying it to many different cases. Then learn movement primitives that are simple representations of these optimized motions, and then only use these movement primitives once a new motion has to be assembled in real time. So all expensive computations are done as a preparation, and the online motion generation only requires to find the weight of the movement primitives. And yeah, we also applied that to the HLP2 robot in LAS, and yeah, and it generated really nice results. So our current research that we are doing in my group is still today very much inspired by the time I spent with Jean-Paul at LAS. We are still essentially learning, like looking at human motions very much in detail. So right now I have my own motion capture labs, and I have my own humanoid robots, but we are trying to learn from humans to see how robots can acquire this motion intelligence, this intelligence to move in the real world, to interact with people in the real world, and then feed that back into robots and into humans and in two aspects. So on the one side, as Eileen also just pointed out, the robots can lead, of course, to really nice insights for human movements, but they also robots can also support humans and really improve their lives. So the examples we're looking at are in the field of humanoid robots. We still try to teach humanoids to move in a very nice way. I think the top one is not moving, so that it's actually standing up from sitting. So optimal control also helps us to do very fancy motions. We are trying to teach robots to climb over obstacles and walk stairs, and also to do manipulation tasks. We also are currently trying to teach our robot to drive the Segway, also by doing biomechanical experiments, identifying human behavior, identifying Segway behavior, and then putting it into simulation, and are currently in the process of also putting it on the robot. But on the other hand, we are also looking at humanoid robots going into medical fields, and especially we are focusing on preparing robots for doing delicate tasks like the COVID swab test. And all that has a lot of like simulation and optimization background. On the other hand, we are also working with assistance robots. So we are developing robotic rollators and also other walking and sit-to-stand assistance devices for the elderly. We are working on exoskeletons, namely lower limb exoskeletons, and also spinal exoskeletons. And in all these cases, we are developing precise models, which include, in this case, the human and the robot, and is in particular their interaction. And there we're also trying to gain a lot of knowledge for the models from experiments on how the robot or the exoskeleton changes the behavior of the human with respect to the human moving along. So this is, as I said, all current ongoing research, highly inspired by Jean-Paul. So with that, I would like to come to the end, and I would also like to show you this picture. So this was taken briefly before I left LAS. So Jean-Paul had invited the entire, so there was a farewell dinner, and he had invited the entire Geppetto team to his home, as he did several times during my stay. So I think this is a really nice memory, and I still have that picture. I got it as a souvenir gift. I still have it in my office and like to look at it. So with that, I would like to end. I would like to thank Jean-Paul very much for all the inspiration he has given me and for all his kindness. And yeah, I'd like to thank you for your attention.
Thank you very much for in particular for this very nice memory. Do we have some questions in the room?
Because in CoRebot we started to think about that. Are you using machine learning at this time?
Yes, I just did it just hinted on it very briefly. So this was essentially learning these, learning the motion primitives, but we are also looking at other representations for the middle part. So I've done that for very simple systems already. We haven't managed to do it for the humanoid ones, but I think that's definitely one approach we're pursuing. In addition to having combined approaches for being able to model components and optimize components and having components of the system which are just black box and which we are just trying to look at machine learning. Yeah, so I definitely think that combination, and I think I also had it on this slide, but didn't really say it. So yeah, it's really on optimal control, but also in combination with other methods.
Hello. Thank you for this very wonderful talk. Very enlightening for such a person as myself. I'm not at all a roboticist, and my question will not be technical, but more methodological. I'm struck by one contrast between the first talks we had this morning early and yours. In the first talks, we had obviously an ongoing research program which was cumulative. In other words, everyone was resting, on Poincaré and Gauss and God knows, and everyone was resting on standing on someone else's shoulder. But in the robotic work that you're talking about with these assistive robots and so on, it seems to me that there are hundreds of labs that are pretty much doing more or less the same thing. And I was wondering to what extent one lab like yours rests on another lab's work.
I mean, I think we are using some of the same classical people standing on their shoulders. A lot of our work still is on modeling these systems, and there's a lot of standing on Newton's shoulders. So in the end, we are describing everything as mechanical systems, and we are trying to come up with refined models, for example, for the interaction. That's a very big problem here, because we have to define the coupling terms and also include them. For example, for exoskeletons, we have to make sure the interacting forces are not too large and things like that. So yeah, and also see what people can tolerate and all this kind of stuff. So I think in our case, the contribution is really on the modeling side, but having a realistic model. And that also includes having a realistic objective function if we use the optimization approach that gives us a good prediction. So we really focus on the models, but we are really trying to close the loop between doing another experiment with the approved system and then again seeing if we can again improve the model to have a better one for the next case or for the next iteration. But there's of course also other labs that just build and that are really good in building stuff. So I come from the computational side. We have started building. So from the experiments you see here, the middle one is a broad one. It's the IIT twin exoskeleton. The left and the right are built in my teams. So we are trying to go in that direction too, to also have it, because we also think it's important to have the system in order to be able to improve the models. But I think there's also people who build that just without any model experience.
Thank you for helping me to keep the watch. So for the last talk of this session, we will go with Justin Carpentier. So Justin is one of the two former students of Jean-Paul that was selected for one of the talk of today, which is saying something about his excellence, of course. Maybe something more accurate with that. So you know that Jean-Paul was very active in keeping his students close to him, with the example of Philippe, of course. But in the case of Justin, it was not possible anymore. Time has changed, so Justin has to move to Paris. And maybe it's a coincidence, but Jean-Paul decided to move right at the same time and stay very close to Justin, to his last student. So Justin is maybe the best consequence, or the best, I don't know, well, best consequence of the fine alloy that Jean-Paul forged with Aishi in humanoid robotics with his own career, in geometry for robotics, and in numerical optimization with Katia. And Justin took all of that for himself in his research. He's the guru of the library Pinocchio that maybe most of your group is now switching to if you're working with serial chain robots, human robots. So maybe you can take some time to say thank you for all the night he's spending on that. Today he will try to give a picture of the last research that Jean-Paul was driving with him in Paris. So with his thesis first in Toulouse and with his early career in Paris. So Jean-Paul, Justin, the floor is yours.
Okay, thank you, Nicola, for the nice introduction. So hello everyone, I'm Justin Carpentier. So I'm a researcher within the Willow team at INRIA Paris. So working with Jean, with Jean-Paul at this time, and also with Yvonne Laptev and Cordelia Schmidt. So we are working on trying to make the intersection between vision, perception in general, and robotics. And also we are trying to work together with people in machine learning and optimization to bridge the gaps for building what we call the computational foundation of artificial motion. So in fact, I met Jean-Paul like 10 years ago. It was in this room, so just the room upstairs, I think. It was at Collège de France. So this is the inaugural lecture of Jean-Paul here, so in January 2012, sorry. So I was just on the left. And for me, this was the first time that I've seen robotics written as mathematics. So just to let you understand what was my mind at this time, it was that robot is mostly something, a toy that we can play with. So this is the French Robotics Cup, which is a yearly program in France to work with robots. And this is a fantastic way of diving into robotics. But for me, at this time, robotics was this kind of things. So playing with robots, trying to build robots, and trying to program robots. And then, so during the class of Jean-Paul at Collège de France, so this is the class of Jean-Paul, so which was in this same room, in fact. So we have two people, no, at least, so three people in this room, which was involved in this demonstration. So this was the first time that Attribution went out of class, or maybe not one of the first time, but at least for teaching robotics in Paris. So this was a bit exceptional. And so this is, I will just let you see, sorry, there is no sound. There is a little, okay, I will try to give you the sound. Oh, sorry. So I cannot change the sound. Do you know how I can increase the sound? Okay. Okay, thank you, Nicola.
I'm not sure it's a good solution. Let's see.
La trajectoire a été préprogrammée, mais on vous projette en même temps, donc vous pouvez vous reconnaître ici, hein, par exemple, prêt à prendre la photo, donc vous pouvez prendre la photo ici. Hein, tout le monde est là, donc vous allez voir, donc projeter ici ce que voit le robot. Voilà.
So this is a demo of Usama Kanoun demonstrated by Echi. So on the real robot. So this was pretty amazing
donc,
for young people.
Sa main apparaître et on ne distingue pas très bien l'objet s'il est là. Oui. Alors vous voyez ici la forme anthropomorphe dans toute sa puissance. Hein. Donc là, tous les degrés de liberté ont été utilisés pour prendre cet objet au sol. Encore une fois, comprenez bien, cette trajectoire est issue des calculs automatiques que Nicola Mercer vous a présentés. On n'a jamais dit au robot qu'il fallait reculer.
So this was very impressive, at least for me. A bit a mystery, but so that's why I decided to move and to join this team. So this is a Geppetto team in 2017, if I remember well. So we can organize a lot of people in this room. So the idea that, at least for robotics, what we should understand that we need robots, but also we need people to make this robot work. And this was a fantastic journey to join this team and to understand how we can move robots. So now for me it's time just to move on because I think the time is running. But I just want you to introduce the main result of my PhD, so which has been under the supervision of Nicola and Jean-Paul, of course, and with a joint work with Mehdi Beneleg, mostly. So at this time, so it was in 2014, most of the robots were using very simplified model to move. The most famous one is the so-called card table model, which is this representation where we have a mass which is just evolving at a constant height. And this implies very major limitations in the motion of robots. So the whole picture and the whole understanding of Jean-Paul also in this frame was also maybe to try also to go beyond these simple models, but also to try to understand what are the models beyond humans. And of course, human is not evolving with a constant altitude center of mass, and so we need to think further. And so the main question that we asked during my PhD, and also maybe still today, what is a good model to analyze and control anthropomorphic locomotions? So if I come back just to the basic principles, so this is the human body, and if I'm just a human body, I'm subject to gravity, and with gravity, I'm falling. So the gravity, in fact, to avoid to fall, we need to create contact interaction, and if we look to this contact interaction, they are acting on the virtual point, which is nothing more than your center of gravity plus the angular momentum. So these things, if you're able to control these quantities here, it means that you are able to create and to build movements and to move forward and to locomote. And this is the real idea of my PhD, but this is the same idea that many teams in the world have followed. So like the team of Ludovic, for instance, also Pierre Brice, if I remember well, there was also the team of Abder in the room. So it was a general idea in the air. So what we have done first is that we have first tried to analyze human motions. So for that, we have equipped people and so on. We have recorded motion, a lot of motion. We can see here Jean-Paul, which is just attending the recording session in Toulouse. And so from these measurements, what we have tried to do is to first build what we call estimator of the center of mass, because this is a virtual point which has no existence, but we need to try to recover this information from data. So data means motion capture markers plus force space measurements. And from that, what we have observed is that the center of mass, if we just draw it from this estimator, we can see that there is a given geometry. And in fact, if we analyze this geometry, you can see that it follows what we call a cycloid. Yeah, thank you, Philippe. So it follows a cycloid, which is just the motion of of a point on the radius of a wheel. And so we have done this analysis, and we have tried to highlight the fact that for many people, so I think there were 25 people registered, we can find a linear relation between the size of people and these two numbers. And as we will see at the end of this presentation, so I have a bonus for everybody, that the wheel was like a vector of direction for Jean-Paul along his career. So starting from the beginning, I think, Atlas NRS, until the end, it was the wheel which was motivating largely his research. So from a humanoid perspective, we try to move forward and try, so as I remember, to remove this assumption of a card table model, so having a center of mass which is evolving on the plane. And for that, we use this famous central model, which is a bit more complex to use because it's a non-convex quantity that we need to control. And for that, we use optimal control. So we use the tool that Heidelberg University was providing, so-called Muscode, to drive the locomotion of robots. And for that, as a team effort, we built this world computational pipeline, which was a bit unique at this time. So meaning that at the first glance, what we try to find is the contact planification of the end effector motion of the robot, like the feet and the hands. And then the second stage of our planning was to compute the so-called central dynamics together with the contact forces. And then from that, we can just use classic whole body controller in order to track all these quantities and to move forward. And all these things have led to a generic framework and a generic approach with a single program able to generate a large quantity of motion, while at some point it was not possible to go so far at this time. So here we have just a generic locomotion on the HRP2 robot. Maybe it was one of the latest experiments that we did on this robot. So on the right, we have just the same robot with the same program. We just changed the footsteps, and we are able to climb stairs, which is pretty easy. So I will move a bit forward. And so here we have the same thing, but now we are trying to use the on-rail. And so this was the setup of the Coribot project led by Katja and also co-led by Philippe. And just to show the difference, so this was a bit at the same time at the DARPA Robotic Challenge. So this was the Atlas robot of HMC team. And this robot was not using at all his hand in order to climb the stairs. All the idea from in the air at this time was really to try to exploit the environment to move forward and just move much more faster, because here you can see that the motion is 4 times accelerated. So I will move now forward just to illustrate a bit the perspective of research that we are trying to bring in Willow, and this was done with Jean-Paul. So just robotics, where do we stand today? So of course, so as mentioned by Jean-Paul at Nicola session, so robotics was a very young field of research, but with a great impact, so like automation in manufacturing, mobile robotics. But as soon as we want robots outside of laboratories, of industries or plants, this is a failure. This is a strict failure because we are not very able to handle all the complexity of the environment, and mostly we are not able to properly interact with in-controlled settings. So how we can move forward and how we can achieve this thing, I think we need to step a bit back and just try to understand how we control a robot. I think most of you are already familiar, but for those who are not familiar, so there is the physical space. This is the space where all the forces, Newton forces, occurs. So this is the ambient space. And from this ambient space, we only have a perception of this environment through our sensors, so like cameras, accelerometers, and encoders for robots. And then from that, we need to take a decision at each instant in order to control our motor space with muscles or just electrical motors, which produce action in the end in the environment. And this is what we call often a control policy or control law in control theory. And so the whole idea of robotics, or at least at this level, is to build a mapping between sensor information and control outputs. So there is at least now 2 ways of controlling robots which are very well advanced. So the one presented, in fact, by Philippe this morning, which is just optimal control, which is a generic setting for the controlling system, from which we can also extend the notion of optimal estimation, so meaning that we aim at inferring the state of our system according to the input measurements, and from that we aim at optimally computing the control output to control the system. So this is the Rishian way of thinking about control. And on the other side, we have something which is now exploiting in our community, which is policy learning. So what it means, instead of just thinking about a single trajectory, we try to find a world control policy, pi of theta, in order to control our systems. So in a raw picture, what we are trying to do is just to try to build with often neural networks to build a relation between inputs and outputs by learning. And for that, we need to generate often billions of simulations in order to really capture and control the system. And this is coming from all the theory of Richard Baldman, which were provided almost at the same time. And so from a picture point of view, what we are trying to do at the optimal control level is that we are trying to identify control trajectory and state trajectory over the time, while at this level, what we are trying to do is rather to try to capture the whole vector field. So this is illustrated by this illustration. So on one side, we have trajectories. On the other side, we just want for each time instance to come to and for each state, quantities, we want to infer what is the right control to apply. And this has provided very nice results. So for instance, in optimal control level, we have Vossen dynamics, which is now, I think, state of the art, we can say, for generating highly agile locomotions. So this is based on the same principle that I have presented before. So just computing online trajectories. So this is planning, online planning. On the other side, we have policy learning, and with nice results from ETH Zurich and from the team of Marco Hutter, where the robot is able to encounter very versatile substrate and just to be stable. So now it is not yet clear how we should move forward within the community. I think I will try to draw some important problems that we are trying to solve now in our team, at least, but not necessarily in our team for this one. So the need of a good design. And I think this is illustrated here by these small robots that we can see. So I just let's run, and you will, I think, totally understand the principles behind this video. Okay, so then we have different aspects. So from physics, we only partially understand and capture complex physical phenomena. And I think, so as we have seen that both optimal control and reinforcement learning or policy learning needs a simulator to capture the physics. And so I think we need to move forward on how to simulate complex phenomena, because we are, for instance, just only using very simplified model of the contact phenomena. In terms of control and learning, I think there is a strong interplay between policy learning and trajectory optimization, but we are not able yet to exploit it. And this is something I think very prominent to focus on if we want to accelerate the learning of control policy. From an optimization perspective, we have dedicated middle and solver for robotics. We need that, and currently we are mostly using off-the-shelf solvers, which are not sufficient if we want to target autonomy of robots. And then from a perception perspective, we need to fusion sensory information to move forward, and we are not able yet to do. So to move forward, so we have several students in the team here, which are all listed, which are working so both to make progress scientifically, but also to make progress as a software perspective. So as mentioned by Nicola, so we are trying to build, in collaboration with Toulouse, still to build like a set of software which can be very versatile and very useful for all the problems that we can encounter in robotics for manipulation and locomotion mostly. So before finishing, I just want to finish by this sentence from Alexandre Grothendieck, which mentions like 30 years ago that he was convinced that time is the only decisive test for the fertility of new ideas and of views. Fertility is measured by offsprings, not by honors. So I think in this room there is a lot of offspring of Jean-Paul, either by ideas or just by careers. And I think this sentence summarizes a lot the career of Jean-Paul. So if I may, so I have a bonus, so maybe no question and a bonus. Is it?
We have the lunch break for questions.
Okay, okay. So I think I will need your microphone.
I'm not sure it was of any help at all.
It was sufficient? On?
Pourquoi je m'intéresse à la robotique humanoïde? J'ai toujours une réponse en deux temps. Le premier temps, c'est ce que j'appelle le syndrome Fukushima, où on a été saisi par le fait qu'aucune machine ne pouvait intervenir suite à la catastrophe dans la centrale nucléaire pour aller fermer des vannes ou faire des opérations. Ce sont des hommes qui ont dû y aller dans des zones extrêmement dangereuses. Et comment fabriquer une machine qui serait capable de faire ça? Ce serait une machine qui devrait être capable de marcher sur des gravats, de grimper à une échelle, d'enfoncer des portes. Et quand on réfléchit à la forme que devrait prendre cette machine, on voit bien que si on lui met des roues, elle ne peut pas évoluer sur des gravats. Si on lui met des chenilles, elle ne peut pas grimper à une échelle. Donc la forme anthropomorphe surgit assez naturellement. La deuxième réponse, c'est que se poser la question de comment faire marcher un robot pose la question de, mais au fait, comment nous marchons-nous? Comment nous marchons? C'est qu'en fait, l'homme ne marche pas, il roule. Mais il faut revenir un peu plus de 5 millénaires en arrière. C'est l'invention de la roue. La roue. Le rondin était utilisé pour transporter des charges lourdes, mais le rondin avait un inconvénient fondamental, c'est que la charge qu'il transporte se déplace 2 fois plus vite que le rondin. Mais moins de 3500 à peu près, hein, on ne sait pas très bien où, c'est l'invention de l'axe. On met un axe sur le rondin et la charge se déplace à la même vitesse que le rondin. Et alors là, c'est la grande découverte. Et la roue, c'est un objet technique qui n'existe pas dans la nature. C'est une invention de l'homme. Donc cette roue, elle a la propriété fondamentale, son usage, c'est de transformer une rotation en translation. Marcher, c'est se déplacer, c'est faire une translation. Les translations, on les mesure en mètres ou en kilomètres. Vous vous êtes déplacé d'1 kilomètre. C'est faux, ça. Vous ne marchez pas 1 kilomètre, vous marchez exactement 171 360 degrés. Comment vous marchez? En mettant un pied devant l'autre, en bougeant votre jambe. Comment votre jambe bouge? Elle bouge en rotation autour du col du fémur. Donc vous avez un mouvement de balancement, un mouvement en rotation qui fait que vous mettez la jambe devant l'autre. Ce que je viens de faire, c'est de traduire le kilomètre en nombre de tours de fémur. Le nombre de tours de fémur, je l'ai calculé, il est de 476 tours de fémur pour faire 1 kilomètre. Mais on a poussé le bouchon un petit peu plus loin et on a observé des marcheurs qu'on a enregistrés avec des systèmes de capture de mouvement. Et à partir de ces informations, on a pu déduire la position de notre centre de gravité. Et la question qu'on s'est posée, c'est lorsque nous marchons, quelle est la trajectoire suivie par le centre de gravité? Eh bien, on a observé que la trajectoire suivie par le centre de gravité était une trochoïde. Une trochoïde, c'est de la famille des cycloïdes. Les cycloïdes, c'est les trajectoires d'un point qui est entraîné par un disque. En clair, une trochoïde, qu'est-ce que c'est? C'est le mouvement de la valve de votre roue de bicyclette. Alors là, c'est complètement fou, parce que toute la complexité de la marche humaine, c'est-à-dire la coordination de tous les muscles, des bras, des jambes, le balancement, la tête qui oscille, etc., tout se concentre dans un mouvement d'une extrême simplicité pour le centre de gravité, c'est le mouvement d'une trochoïde. Voilà pourquoi j'ai dit au départ qu'on ne marchait pas, mais qu'on roulait.
Thank you very much for this moment. So let's go and celebrate with a lunch.
Okay, and so Everybody is on his own for lunch, or on, except the speakers that we are going to take for lunch.
It should work. So it says no signal. Something's saying I'm getting no signal. That's what I was afraid of. You know, can I just try something? I'm going to try to do this. Plug this. See, it's very strange.
Yeah,
not,
yeah.
It is?
Yeah, it's here. Okay.
There we go. Okay. Saved.
All right. Hi, everyone. My name is Ludovic Rigali. I'm a professor at NYU. I'm here. I'm replacing Martial Hilbert. He was not able to come today. So we'll be chairing this session. So our next speaker is Céline Peters. She was the first student. Well, she was the student who worked with Jean-Paul, a PhD student, when Jean-Paul started to work on rhetoric and robotics. So I guess you're going to show us how Jean-Paul was a complete scientist who really was looking at very different things. So Céline is a postdoctoral researcher in rhetoric at the University of Vienna, and she still works on the philosophy of media and technology. And she did her PhD thesis jointly at INRIA, at INSA in Toulouse and at the Université Libre of Brussels in Belgium. And you did most of your PhD thesis at the last CNRS, surrounded by roboticists. And so today you're going to talk to us about what does it mean to talk about machines, and I'm very much looking forward. Thank you very much.
Thank you. Thank you for the introduction. And I will myself start with an introduction that Jean-Paul especially liked when we would present our work together. So this is about the well-known roboticist Ruzena Bakshi, who during an interview in 2010 explained the motivations of her research on active perception in robotics, which she started in 1983. In that interview, she highlighted the fact that as humans, we don't just see, we look, we don't just touch, we feel. At this time, she was concerned with improving robots' visual perception, and she used this analogy with humans to support the idea that if a machine could adapt actively to the scene around it, its perception of the environment would be considerably ameliorated. She specified, being human, our pupils adjust to the level of illumination, our eyes bring the world into sharp focus, we move our heads or change our position to get a better view of something, and these features have a direct impact on our knowledge of the world. So now the question is, when such human behaviors, or more generally, when living organisms' behaviors are simulated on machines, and that it works, of course, can we then say that a robot looks and not just sees anymore? That the robot feels and doesn't just touch? In the fields of robotics and artificial intelligence, many words and expressions that form our representations of robots are borrowed from the vocabulary of the living. So we talk about intelligent machines, autonomous robots, moral agents, and we say that the robots learn, they decide, robots know, they want, they feel, etc. And those words seem to challenge humans' perception and understanding of robots. But what do we really mean when we use these words when talking about robots? This is the problematic that gathered Jean-Paul and I for a 3 years PhD program at the last CNRS in Toulouse between 2017 and 2020. Or at least it's a question that started this common research, because at the end we didn't look at what these words mean exactly. So we didn't engage in a search for accurate definitions for those words, and we didn't aim to establish if it is or not appropriate to use such a vocabulary when we talk about robots and the discipline of robotics in general. So our objective was rather to better understand what we do when we talk about robots and what are the effects of this language. And we did this by starting from the observation of actual linguistic uses. So in other words, the whole idea was to bring the discipline of rhetoric in the context of robotics. In our modern society, rhetoric is often reduced to eloquence, or worse, it's considered in a caricatured form of manipulation. But according to Aristotle, the discipline of rhetoric is the art of finding the available means of persuasion in a given case. So rhetoric is firstly a technique of discovery and invention of arguments, which include the cognitive and linguistic tasks that consist in passing from general concepts and ideas to speaking and acting accordingly in a particular case. And this is with such a conception of rhetoric inherited from Chaim Perelman and Lucy Olbrecht-Iteka, who founded the School of Rhetoric of Brussels, where I myself studied, that we formulated the questions of this research project, which were the following ones. So how do we humans read robotics? Why do we use certain words and not others that would maybe seem more appropriate when we talk about technical aspects, when we talk about machines? Then what does the lexicon used to talk about robots tell us about the way that we, humans, perceive moving machines? And finally, could we find alternatives if we wanted to? So could we talk about robots differently than what we do now when we use these words spontaneously? And in this way, and like I said before, the main idea of the project was to better understand how humans perceive and talk about robots from their own stance. And to these questions, you are probably wondering if we found answers. So to the first one, why do we use certain words to talk about robots and not others? So the reasonable answer is probably we don't know exactly. But we managed to show that movement plays an important role in that aspect. And I think we all know how excited Jean-Paul was when him and I realized that movement might have something to do with this. So in fact, we explained the use of these words that we call the agentive lexicon through the problem of the ineffability of motion. Ineffability being the difficulty or impossibility of putting certain experiences into words. So a natural language is supposedly capable of expressing all our sensations, perceptions, abstractions, etc. But in fact, no purely verbal language ever entirely achieves total affability. So as an example, think of having to describe in words alone the smell of rosemary, for instance. Now, motion can be described in many words, since it can be appreciated by visual perception, but also through the sense of touch. So we commonly qualify movement as being smooth, for instance. And yet, a strong struggle, or at least feeling of struggle, remains when it comes to actually formulate movement into words, so to code movement linguistically. But because we must still express the situation, we instead describe actions and dispositions. So, for instance, we say a tennis player hit the ball, rather than the tennis player raised his right arm, made a dynamic movement from up to down, etc. So motion can be translated to natural language, but we simply don't do it. In the context of robotics, motion raises the same problem of ineffability, and the adjunctive lexicon, again, enables to bypass that problem, as we can then quickly and efficiently describe a situation with a robot. So in rhetorical terms, we say that this language produces the effect of enargeia. It makes actions visible. In other words, it creates an effect of clarity, and in this way it fulfills the primary function of language. The discourse shows more than it tells. On the other hand, when we say something as simple as, for instance, the robot doesn't want to go to the other side of the room, the effect of enargeia brings, for sure, clarity and is efficient, but it also brings persuasive effects that might be felt as inconvenient for researchers who are trying to introduce robots in their technical aspects, for example. And I'm sure you all have experience with this already. But considering the role of movement and the problem of ineffability that it raises, surely enables to observe that the words of robotic, the adjunctive lexicon, is extremely hard to avoid, or at least it's hard to avoid when we express ourselves spontaneously. And this is hard to avoid whether we believe that a robot is intelligent or not at all, whether we have more or less an affinity to anthropomorphism. So when we come to ask, could we talk about robots differently? Should we use alternative words in order to avoid any confusion between the living and the machines? It's probably interesting to consider that while we have a lot to gain in thinking and choosing finely the words that we use to talk about robots, the matter of the language of robotics goes beyond that semantic level. It concerns the discourse in its whole, and even more than that, it concerns our epistemology of language and our relation to our own representations. So in that sense, our ability to debate constructively about robotics and to discuss plausible societal problems that might come with the development of new technologies depends rather on our ability to revisit our own relation to language and representations than on agreeing about the words we use and the way we define them. Now, that's where Jean-Paul would tell me, okay, so what? And I could not make this presentation without mentioning this, because he said it to me so many times, while giggling a bit, because he would know I would come to his office being very proud of myself that I finally have a sort of clear conclusion, and he would just like to tease me and say, okay, so what? So in fact, this so what is what I tend to explore in my current research at the University of Vienna, where I focus on the problem of responsibility in the context of robotics and AI. So surely there's a general interest in being able to conduct constructive discussions in order to prevent potential risks and ethical issues related to technology. And while, for instance, Rodney Brooks regrets that mistaken extrapolations distract us from thinking more productively about the futures, this is a reference to his 2017 work. He also highlights the problem of limited imagination when it comes to ethical reflection. And by the way, the state of the art in practical ethics is quite unanimous on this point. So firstly, there's a call for defining, assuming, and exploiting our imagination as a tool in this context. And beyond that, this is a call for more likelihood or plausibility within our practice of imagination about technology and the future. But how do we exercise imagination, and how exactly does it serve the ethical reflection about robotics? So I aim to research this problematic using again the discipline of rhetoric as a heuristic method. So concretely, this means that I wish to conduct an experiment where roboticists and specialists in narration, so writers, screenwriters, illustrators, are gathered around a same creative task, a narrative exercise. And Philippe already did one at the Cité des Sciences in 2018. He knows it's possible and not horrible to do this exercise. So if there is any volunteer for this experience, let me know. But so what I wish to explore with this are the following questions. What do we consider as being plausible or not? On the basis of which criteria do we decide if one or another scenario is likely to be real or not? And knowing that, of course, influences how we will spend our energy and resources to prevent certain risks and not others. Also, how are the criteria of likelihoods different to experts in the field of robotics and AI than to specialists in narration? And this is a way of understanding how fiction and reality intermingle with each other and how one could serve the other. And finally, what are the eventual advantages in reconsidering the role of imagination and fiction in ethics of technology compared to the formulation of ethical principles and rules that researchers and also entrepreneurs are invited to follow through regulations, guidelines, codes of conduct, recommendations, etc. Because as Mark Johnson reminds us in Moral Imagination, while moral principles and rules have a role to play, because they encapsulate our past experience, we should engage in an open dialogue about them. So morality, according to Johnson, is not a system of laws, but an imaginative exercise based on what we share with others. I can now thank you for your attention, and I'll be glad to answer your questions if you have any.
All right, we have a few minutes for questions. I think, Jean, you have a question?
Yes, I don't know how people talk about robots, but the fact is that you have a few sci-fi writers and movie makers and a few roboticists, but the vast majority of people in the world have never met a robot. And can we draw a conclusion from such a small sample of the human population, or should we wait until there are robots with people?
Sorry, I didn't hear that.
Or should we wait until robots are close to people and people see robots in their daily life?
I don't think we should wait, and also this vocabulary that I was talking about is not only people in the street talking like this.
No, that's the point. It's not the people in the street. I'm sorry, I don't mean to be aggressive in any way. I'm just saying the people in the street have never seen a robot in real life. So maybe once and if robots live with us, maybe the way they will talk about them and their perception will be different. Because even the fiction writers or the movie makers are specialists in a certain way, right? They are not like random person in the street. Do you see what I'm trying to say?
Yes. Yeah. The thing is between the language and the representation. Of course, there is not a very clear border, so we cannot just say maybe when the robots will be more popular in our society, maybe people will talk differently. But in a way, that's what was the conclusion, is that the semantic level is not as important as long as we work on our representations. But to do that, the language is a good tool, and the fiction can be a good tool.
Okay, thank you. Right. Is there any other questions? I think we have time for one more question. Actually, so I have a question, if you don't mind, since we are a little early. I was actually wondering, how can we translate what you're discovering about the use of imagination to talk about robots in our future into concrete things about how we maybe develop robots and how we maybe design policies about how we use robots?
Yeah, that's the thing, that we have this common idea that fiction is in the popular culture, and then we have serious discussions on the other side, and we make regulations that have nothing to do with this. But there are more and more studies showing that, of course, the general representation, and in rhetoric we talk about topos, with like common ideas that we share, are anyway in those regulations, and they have an impact, of course, of how robotics is thought. And also there are also a lot of roboticists who have this idea to start a career because there's this dream and wonder about robots that is, of course, conveyed by the fiction. So it is an important role also.
Right. Thank you. Thank you again, Céline. Thank you so much. So the next speaker is Ken Goldberg. So Ken is the William Floyd Distinguished Chair in Engineering at UC Berkeley. He's also the co-founder and chief scientist at MB Robotics. And Ken is not only a roboticist, but he's also an artist. So he's also has an appointment in the School of Art and Practice at UC Berkeley. And also, so we just saw that there's a lot of intersection between robotics and rhetorics. There's also a lot of intersection between engineering, robotics, and art. And I guess today you're going to talk to us exactly about this intersection, so I'm very much looking forward to that. Thank you.
Thank you very much. So I have to say, it's a real honor to be here, and I want to thank Jean-Paul in particular for reaching out to all of us and bringing me here. I also changed my slides around a little bit based on what I saw this morning, because I sort of wanted to talk about both some art and some science in this context of Jean-Paul. So this is my group at Berkeley. These students are really should get the credit for most of the work I do. I wanted to just say it's good to be back in person after the last 3 years. And what I want to mention this, start with this problem. It's a motion planning problem, a bit different than what we talked about this morning, but has a similar structure in many ways. The idea here is to orient an object, in this case a polygonal extruded object, by a sequence of grasping motions with a very simple parallel jaw gripper. And here's 4 runs of that plan, the motion plan, each one vertically, that all end up with the object aligned with the major axis of the gripper. So the problem statement is that if you're given an arbitrary object, any polygon, can you find a sequence of gripper actions that will have this effect, that it will orient the part up to the period of symmetry, or report that no such sequence exists? And so there's some assumptions that we make. It's a planar motions here and frictionless. But so the idea of the algorithm is to first observe something about the mechanics of pushing and squeezing. So, and this is really this was work that was done when I was a student of Matt Mason, who's sitting right there. So correct me, Matt, if I get some of this, if I'm wrong here. This is actually Mason's law, that if you start to push an object like this, as you continue to push it, it will land and stop moving on an edge. And so the center of mass, as you see, moves in a monotone, decreasing fashion. So what we could do is capture this with a width function that captures the width. Actually, squeezing now is where we have 2 jaws making contact, and you have a similar structure where this piecewise sinusoidal function is actually is capturing the distance between the 2 jaws. And there are local minima and maxima in this function. And then we can wrap this around into a torus. So we can capture the idea that if we take a range of orientations coming in, that when the jaws close, there'll be a range of there'll be a much smaller range of orientations coming out. So the input range of orientations is on the bottom, and the output is another range of orientations, but will be singletons at each of the stable orientations. Then the nice thing we can do with this is we can actually use it to capture, we can actually compose a push function or the width function with that squeeze function and get a combined push-squeeze function, as you see in the bottom. But then we can use that to construct a plan. And the idea is to consider here, we're unrolling this, this sequence, or sorry, this connected torus, just flattening it out and wrapping it around. And so we're looking for regions, a pre-image, if you will, of the blue image that shows you that if you started at the green and you closed the jaws, it would end up within the blue range. And we can then iterate. So here, let's illustrate. If you start out in the blue, you end up in the red. And then if you wanted to find a target for the blue, you start out there with the green. And so to match all these up, you just have to understand the relationships, or measure the relationships of all the intervals, and you can recover the steps of the motion. So here's a motion for an object shaped like a house. And you can see that if we push it in this direction, it will then line up. Another ancient video back in the days of VHS here. Just like Flash, very hard to recover these. All right, so, and this is guaranteed to always orient the part regardless of its initial orientation. Again, no sensing is required here. Now, the other thing that was a challenge Matt said to me was, he said, well, if you can prove a completeness, then you can graduate. So I spent an entire summer working on this problem, and so this relates again to what we were talking about this morning of these. It's one thing to construct a solution; it's another to show that it exists in all cases, that a motion plan exists. So here, the idea was that it was possible to construct a formal representation of these step functions that map from S1 to S1, and then to characterize the period of symmetry that exists within that. And then the claim is that we can always find a sequence of intervals of increasing measure until we reach a period of symmetry. And so then the idea was to start at some S interval that has measure h, and begins at some value theta and ends at theta plus h, and then that's the projection of its. The S is how it projects into the squeeze function, and then the claim is that we can either we can find a larger interval. There exists a theta, a positioning that will enlarge theta, so it's the image is smaller than the current h, or for all theta. That all values of theta, that the projection is exactly equal to h. So now we take those conditions, turn that into a function, as you see on the bottom, and then we integrate that over a period of symmetry from 0 to t. That's a period of symmetry in the object. And if you look at this construction, we can change the bounds, move things around, and then fortunately this integrates to 0. So then what that says by the mean value theorem is that that's exactly what that function says, is that either there exists a point that's greater than 0, or there exists a point, or less than 0, or it's 0 everywhere. So that gives us our proof of completeness and allowed me to graduate from Matt's lab. So that was the completeness result. We could also prove complexity bounds when I did it to n squared, and subsequently Doug Iyer already proved that, extended it to linear. And it's been extended in a variety of different ways over the years. So that was about the time I started teaching at USC, and I was invited very warmly by the promotion group that has been mentioned earlier. And several of them are here in the room. I remember this fondly. This was outside Rome? Outside Rome. In Rome, right. Okay, all right, excellent. It was really wonderful, and I remember being so delighted to be included, and then it began a relationship of collaborations and interactions that still continues to this day. I also want to mention this, which is, it was a few years after that that Antonio and I got together to organize a workshop on minimalism in robotics. And this is, you may recognize some of these characters here. That's Jean-Paul. There's Antonio, John is here, Matt, and there's me. So 4 of us are here today, and we miss the 5th very much. All right, so on the idea of motion planning, the other thing I would like to add is that very recently I've been working with a postdoc, Jeff Ichnowski, and looking at the problem of optimized motion planning, and in particular optimizing using the grasp constraints. So I won't go into all the details here, but this can be posed as an optimization problem and numerically solved. And the idea is that we're shrinking down the motion speeds and to find a motion that will max out one of the torque limits. And so we recently extended this to handling inertial constraints. So you can also formulate inertial constraints in the same framework, just adds another constraint to the objective, and then you can optimize these motions. So where there's a constraint. Now I'll just show you what this looks like there. So that's moving a glass filled with beads, where the motion constraint is to make sure that the vector continues to point toward the bottom of the glass, so that none of these beads will fall out. And if you remind me about this at dinner tonight, I'll show you another variation on this. All right, so now I'll shift gears to talking a little bit, and it relates to what Celine was just talking about the issue of semantics. What do we mean when we talk about a robot? And I think we can go back to the ancients here. Ovid's Metamorphosis talks about the story of Pygmalion, and the sculptor who falls in love with his creature, his sculpture. And then we go up through the Golem of Prague, again, created out of clay to assist the rabbi. And then Da Vinci, of course, famous, his variety of different robotic devices that goes up through the 1700s and all the automata, the amazing mechanical systems that are built, including our friend von Kempelen. We all remember the Mechanical Turk. And right around this time, E.T.A. Hoffman writes The Sandman. If you're not familiar, it's a wonderful story, a parable about a boy who falls in love with an android. And then 100 years later, Frankenstein, and 100 years after that, we have the flu pandemic of 1918. The reason I bring that up is that right around this time, a book comes out on exoticism, and importantly, Sigmund Freud publishes his book on Das Unheimliche, which is later termed the uncanny. It's 1919, right after the pandemic. And then exactly a year after that, Karl Čapek comes out with the word, coins the word robot from Arbeit in Worker in his famous theater piece, Rossum's Universal Robots. So just coming back to what is a robot, what does that word resonate? Then what are these meanings culturally for that word, which has been adopted almost universally? So it takes on many forms after that point. Fritz Lang does this famous film Metropolis with a feminized robot. Asimov's iRobot series with the laws of robotics we're familiar with. Nam June Paik does a series of sculptures and installations with art installations with robots. And then in 1970, Masahiro Mori publishes a paper on design of robots, and he postulates this idea of what later becomes called the uncanny valley. But I think everyone's familiar with it. It's the idea that if you loosely plot, just conceptually, it's not any kind of accurate axis here, but you have a non-human to human axis, and then you have likability on the vertical axis, that as things become more human, they become more likable in general until you reach a point. And this is what the uncanny valley. So you get a point where the similarity is too close for comfort. And there's a great sense of discomfort there. And that's the uncanny, what's later been called the uncanny valley. And that was actually, that relates to Freud, but it was a woman who's now living in Britain, Yazia Reinhardt, who made the connection between Freud and Masahiro Mori. And I recently was able to reach her, and I want to tell you for the first time, no one knows this beside Casper, the organizer, but she will be giving a plenary speech at ICRA this year. She was the one who coined the term. Anyway, uncanny valley has been used in a vast variety of applications. It's used by all animators, that if you make the eyes in an animated character too realistic, you make the audiences very uncomfortable. So that's why most characters, Pixar and others, use very sort of caricatured eyes. And this is explored in thousands of themes in films, and also by our colleague Hiroshi Ishiguro in building what he calls geminoids, which are basically twins of humans and researchers. It's been used, the uncanny comes up in all kinds of contexts. So here's, why am I forgetting his name? Stellark, thank you. Stellark from Australia, good, John, with his implants an ear and has it grow on his arm, and he claims to actually hear through it. But this again is playing off this idea of the uncanny in our reactions. My own work is, in some way, looking at a variation on this was the project called the Telegarden that we launched in 1995, the early days of the web. It was a real garden, but tended by remote users from all over the world who would come in and use their Mosaic browsers at that time, very early internet connection, but they would be able to observe the garden and then plant and water their own seeds, so collectively tend the garden. So we started this really as an art installation. It was kind of a critique of the claims of the internet at the time, and also an engineering project. But we didn't count on was the amount of people who would be interested in planting seeds. Pretty quickly, it grew so vastly that it turned into more of a study on the tragedy of the commons. So we had to cut back the garden periodically to keep up with it. We published a book with a series of 8 artists, 8 engineers, and 8 philosophers, looking at thinking about the implications of this in the context of the internet. In particular, the issue of what it said about the distinction between virtual and distal reality. That the virtual reality is something that's fictional, constructed inside the computer, and distal reality is something that is real but distant, so is mediated by some sort of computer system. And the line between them was really what we were trying to think about. And I would say that in the 20 years since we wrote the book, this line has even become more ambiguous. Let's see, I'm going to skip that. I wanted to look up this. I had seen Jean-Paul one of the very last times I saw him speak in Canada and Montreal. He was giving a talk about this. He showed this beautiful work with pianos, and I was just trying to find it, and I was like, pianos moving. This is the kind of stuff I kept finding. Of course, there's always our piano movers problems. But then I finally was able to find it, what I was looking for. And so Jean-Paul collaborated on this project with Celeste Boursier Mougino, who's an extremely acclaimed artist, and it's very beautiful. I think everyone who knows the movers problem will appreciate what's going on here. And this would just run for hours. And there was a camera overhead that would make sure that the robots would plan very beautiful, elegant motions, but make sure that they didn't collide with each other. So, so that, and then in 2020, I want to mention a project that my students and I initiated as somewhat of a sequel to the Telegarden that we call the Alpha Garden. And whereas the Telegarden was about remote teleoperation and collaboration, the social dynamics of users over the internet, this project is about artificial intelligence and about the claims, I think somewhat exaggerated claims that we experience today about the promise of deep learning. And so the question here was whether we could get a robot to tend a physical garden. And so we set up a system in the lab, and this is showing you a time lapse. We exhibited this in New York, and here's a time lapse of the growth. And what happens is that this was launched in February of 2020, so right before the pandemic. And then as we moved into March, they shut down access to the galleries, and we were not able to go back in. And so we could no longer tend the garden. We couldn't do anything. The water was shut off. We just had the cameras in there, so we were able to watch what happened, essentially from the sideline. And it was very interesting to see something I didn't expect, but all these plants, essentially they were growing, but they suddenly went to flower, and they started shooting out these almost accident. It was almost like desperation to me that they're reaching out, because at this point it hasn't been watered for several weeks, and it's really just, you know, trying to get attention. It's just striving for attention. And it's tragic because we had to watch this thing essentially fade until late April. It was essentially dead. So just considering this, I thought of this, reminded me of something I was thinking and was struggling with it for a while until it hit me that those last few stages reminded me of Guernica in some way. That there was some, especially this figure on the right, there's some idea of this garden kind of trying to desperately reach out. So I think this again comes back to Celine's point. I think that robots are mirrors. They're mirrors of ourselves and our what we imagine ourselves to be. So coming back to this question of what is a robot, and I know that we could discuss this over dinner and we'll probably get many different answers. It's really frustrating because in our field we can't even define the fundamental element. But I think if we're going to answer this question, it's intimately tied up with the question, what is intelligence? And this we also know to be extremely difficult to answer. Turing's test only offers a simulacrum, and as we know, it's very easy to fool. Many people can fail the Turing test, let's put it that way. And if we even want to understand that in the embodied form of what we are talking about here in robots, the bigger question is, well, what is alive? What does it mean to be alive? And that is, again, a very deep and fundamental question. We don't have a good answer for that. I mean, we may know some things about carbon forms on our own planet, but we don't know that how we could more broadly define the idea of something being alive or not. So, so the very last thing I want to leave you with is this project that Jean-Paul and I talked about several times, and he was very excited about and proud of, which was, again, with Celeste, they did this project at the Venice Biennale in 2015, and it was a very elaborate system that had, as you saw, those platforms, and then what was built around it was a living tree. And so the system, this would very, very slowly move in this environment, inside the pavilions, and interact with visitors, and was really a major piece recognized by the international art world. So with that, I want to say I miss Jean-Paul enormously. He was a wonderful colleague, great friend, and a real inspiration. Thank you.
All right, thank you so much. We have a couple of minutes for questions. I don't know if anyone has a question. Yeah.
John?
All right, I'll make the hard one. So when you're comparing machines and trying to describe whether they're alive or whether they're intelligent, how do you know that you're alive and intelligent?
Thanks, John, for that low ball. Easy question. Right. You know, I think it's that is the fundamental question. And in fact, if you think about something like Blade Runner, right, it was actually right the essential core question there. What is a replicant versus whether it's a human? And I think that this problem is fundamental. I mean, I think it's fundamental, and it's extremely important because of the tendency, especially today, to answer the question in the negative form, to reject the privilege or the rights of others to be considered an equal form, and that inequality in all forms, economic and social, is a huge, massive question today. So many people want to deny, the question is that person, an equal of myself. So I think these questions are very deep, and I think we're not going to. They're, for me at least, the kind of questions that the more I look at them, the more complicated they get. So I think that's what art is trying to do. I think that's what Jean-Paul was doing in this latter work in the latter years, bringing his insights into geometry and motion planning and bringing them into these expressive forms, working with Celine and others that were trying to look beyond the mathematics to start to understand what is this saying more broadly.
All right,
thank you. Thank you.
Thanks, Ken, again. Thank you so much.
Oups là. Alors, est-ce que ça va marcher? Le moment de vérité.
All right. Okay, so our next speaker is Daniel Handler. So Daniel is an emeritus professor at the Sorbonne University and a member of the Académie des Sciences Morales et Politiques. So Daniel began his academic career as a mathematician, especially working in logic, and then became more interested in the philosophy of science, and especially cognitive sciences and artificial intelligence. And I guess that really makes the nice, again, showing that all these fields are really are interacting with each other. So today, Daniel will talk to us about whether having a body is sufficient or a necessary condition for AI systems. And I guess, I don't know if you're like me, but the roboticist, I think this is a fundamental question that I find is fascinating. So very much looking forward to your presentation. Thank you.
Thank you very much. It's a very, very risky thing to ask such a question in this audience. Before I tell you why I'm among you and thankful to be, I'd like to say just one word about myself. It is so moving to me to find myself, and it's rare, it happens once in a while, to be among mathematicians. I mean, that's my original family. So I have the impression when I'm in an audience such as this and see mathematics on the screen, I feel I'm back home again. But it's a home that I've left so long ago that I know that I'll be an expatriate all my life. So guess who was on the faculty when I walked into the Berkeley Math Department in 1969? None other than Dubin, in fact. He was a professor there. So why am I here? Well, let me show you the next slide. I was approached by Jean-Paul. We'd been in touch, but not for such a long time and not in any particularly deep way. He asked me to come and comment on one of his papers once or twice, but we weren't very close. But then, as a member of Académie des Sciences, he asked me to co-organize with him this workshop with the Académie des Sciences Morales et Politiques, of which I'm a member. And so for very, very intense 8 months or 9 months or a year, I don't remember, he and I worked very hard trying to set this thing up. And we had the assistance of Céline, whose drawing you have, that's hers, and it'll be also on the next slide. And so, as you will see from, this is the talk that Jean-Paul gave, Robotics, Intelligence Facing Reality. So you see, I think Ken was saying something about reality just a while ago. So clearly Jean-Paul was interested in some fundamental questions and was willing to ask them in a naive question, in a frontal question, in a frontal way. And I think that's the way to do it, at least once in a while, before we fall back in conversations between specialists. So this is what I'm going to try and do in a short while. I forgot to start my watch, so I'm not very good at controlling time, I'm afraid. There we go. Okay, so first of all, one quick question. How does AI feel about intelligence? Remember in the beginning, we had those statements by such luminaries, pioneers as Minsky. You know, in a few years, we'll have a fully intelligent machine of the full human sense, et cetera, et cetera. And of course, Minsky was not the only pioneer to say such things. Newell and Simon and several others said the same. So that was the late 60s, early 70s. And then there were winters of AI, you remember. There was a winter in the late 70s, and then there was a second winter from the late 80s to the early 90s. And so essentially the profession sobered up, and it decided to entirely forget about, you know, so-called strong AI, that is AI with consciousness, AI with understanding. It decided to forget about human-like intelligence, about general intelligence, about autonomy in the sense of being autonomous of the intelligence of the programmer, and of intelligence altogether. That was just not interesting to be talking about intelligence in general. One excuse being that nobody knows what intelligence is, and we heard Ken say this. It's false. It's not quite true, but it's an easy way out. Nobody knows what intelligence is. Okay. So the name of the game in this sober period was so-called narrow AI. So the point was to do intelligent things precisely without intelligence. And how to do it was to can as, you know, put in a can or in a bottle, knowledge, and then automatize processes one domain at a time. So all of this is absolutely familiar. And the only reason I bring it up is that, of course, with deep learning, whose claims are somewhat exaggerated, I agree with Ken, well, suddenly the vision of a fully intelligent machine, of a really intelligent machine, is back. That's the vision is coming back. So how do we know? Well, it shows in interviews. I don't think it shows in academic papers, but in interviews, except from this community of the so-called general artificial intelligence, artificial general intelligence, that's sort of the sect that really is actively pursuing real intelligence. But the mainstream of AI doesn't really say this. It's in interviews that you know, the leaders of the profession, especially the leaders of deep learning, somehow betray their real goal. So we have these quotes from, I have one quote by each of the three musketeers, Benjo, Lequin, and Hinton. And each of those quotes, which I won't read, you can do that by yourselves, clearly says, look, our machines are dumb, so we have to, you know, we have to do something about it, and they don't exactly agree on what we should do about it, but there is something to be done. And why? Well, because we don't want to be stuck with dumb machines. We want really intelligent machines. So that's why we can again talk about AI's ambition to generate real intelligence. So the second part of my talk is about embodied cognition and robotified AI. Pretty obvious. I don't even need to, put up my slides. You know what I'm going to say, but I'll say it nonetheless. First of all, a short slide on the allure of embodied human cognition. So this is the idea, the general idea. The body plays a major role in human cognition, and that's very plausible for several reasons. First of all, we can say that cognition has evolved and has taken the body on board, so to speak, with reciprocal effect. We can say that the body gives access to important resources. So, for example, information about the physical makeup of the world, about other people, and what people are up to when they interact, cooperate, learn, survive, mate, etc. The body provides a rich ontology, which is reflected in language, and this relates to Céline's talk, who didn't mention the fact that there's a whole school, but I'm sure she knows about it, in semantics and cognitive semantics with people such as Len Talmy from Berkeley again, and George Lakoff, Berkeley again, who emphasize the fact that our language is shot through with spatial ontology. So how do you get, if we follow them, we couldn't be talking with this extraordinary ease of communication and so on the way we do if we didn't have at our disposal these spatial metaphors. How do we get spatial metaphors if not by being familiar from the day one with space and movement? And so there are many reasons why it's perfectly reasonable, plausible to suppose that our body plays an important role in our cognition. But now we raise the difficult questions. What exactly does embodiment consist in? What parts or dimensions of cognition are concerned by embodiment? How much, and that's more of a sociological or historical question, how much has the embodiment paradigm actually achieved for cognitive science over the last 20 years or so? I'm asking those questions not as a means to cast doubt on the brute fact that, again, cognition is embodied in one way or another, but to draw attention to the fact that how to take account of that embodiment is anything but obvious. Still, it wouldn't make sense to wait until these questions are satisfactorily settled, all the less so as it may never happen. Some of these questions are deeply philosophical, and as Ken suggested, it might be a long, long time before we agree on a full response or answer. So it wouldn't make sense to wait until these questions are fully settled to explore the implication of embodiment for AI. And so let's go artificial. And so here there's a apparently self-evident inference. First of all, AI aims at recreating human cognition in artificial systems. 2, human cognition requires or rests on its being embodied. 3, AI has up to now failed to recreate human cognition. 4, AI has up to now remained a disembodied phenomenon. So it follows that in order to succeed, AI needs to be embodied. That is, to be equipped with a robot or embedded in a robot. So that's the self-evident inference, but is it really evident? So to make things a little bit difficult, I want to raise 2 objections. First of all, AI aims at recreating human intelligence, maybe not the whole of human cognition. So of course, we'd have to go into an elaborate discussion of the relation between cognition and intelligence for some, it's the same. I remember in his general introduction to the 4-volume MIT encyclopedia, not in the encyclopedia, but the sort of 4-volume textbook on AI, directed by the psychologist Daniel Oscillations, who was a friend of mine. I mean, he still is, but we don't really interact very much. And he said, just to present what cognitive science is or cognition is, it's just the exercise of human intelligence. For him, it's the same. But I contest that. I think it's useful to distinguish intelligence from cognition in general. So what do we mean, or what does AI actually mean by intelligence? I don't think it quite means just cognition. And then, of course, the second objection is that the inference is best plausible. It's not deductive, right? I mean, look, the first planes failed to fly, okay, and someone could have said, look, they failed to fly, they're not like birds, let's make them like birds, and then they will fly, right? So it's the same sort of inference, so it's possible, it's plausible, but it's not deductive. So let's take a second look at intelligence. So there, I'm on very, very slippery terrain, I'm aware of that. So intelligence is usually defined in terms of problem solving with bells and whistles. I mean, I've looked at the, there are 120 definitions of intelligence that have been, more or less taxonomized. But basically, there's this idea that intelligence consists in the ability to solve problems, all sorts of problems, et cetera, et cetera. That's the bells and whistles we don't have time to go into. And I claim that if you take problem, more or less in the strict sense, and the paradigm of the strict sense is what we do to, we're given a problem to pass our qualifying exam in math. There's a problem, there's a unique solution, and if we're smart enough, we're working enough, we've solved it. I claim that's a good sort of paradigm, a good example of what a real problem is. It's put forward, it's set by a professor or by nature, and there is a solution, and the challenge is to find the solution. And I think that's in fact how the notion of problem is understood, at least in practice, maybe not in the theoretical, explicit way, but implicitly that's the notion of problem that AI rests on. So if you take problem in that sense, and if you agree that AI is after a general problem-solving capacity, ability, then it's no longer obvious that intelligence is, in fact, amounts to cognition. There are lots of other things in cognition that are not about solving problem in the strict sense. And it's no longer obvious that having a body is necessary for having a human-like ability to solve problems, although it might help. So the objection would be, I think, that having a body makes it possible to inhabit the world, as opposed to merely possessing an internal model of it, right? That's the Brooks line and many others. So it makes it possible to react to novel events or evolving situations in real time. But it may not be the only way. So being present on the spot might be a constraint that seemed inescapable maybe in the old days of AI, of symbolic AI, with very slow computers and small memories and so on. But with present-day computational power, we might free ourselves of that constraint. Again, I'm not claiming that it doesn't help to be in the world, but I'm saying that it's not a necessary condition. And one able commentator of AI, François Chollet, who works with Google, I think has the same opinion. He denies the fact that AI requires a body. Okay, so, and just because I'm again reminded of my mathematical past, it suddenly occurs to me that when I was a very young assistant at Orsay, way back, And we had a blind colleague, and he was interested in sphere reversion. And he was trying to explain, and I was there. He was just standing outside the math building, and he was explaining to someone who didn't get it how to put the sphere inside out. And although he was blind by birth, he was constantly saying, "But you see, can't you see? Can't you see how it works?" So you don't need eyesight, in order to get some notions of seeing. And maybe we have the same thing. For intelligence, we might get disembodied intelligence doing the work of embodied intelligence. So these are doubts. I'm not making any strong claim there. So let me take a second look at intelligence, and let me give you my unorthodox proposal for what intelligence is. And I'm going to run into trouble, I know that, but you know, what is life at my age if you don't take risks? So I say that intelligence is the capacity to do the right thing. That is, to deal with a situation appropriately. Now, what do I mean by situation? Of course, it's a very broad word, and I have no particular claim on what it really means, but this is what I mean by situation in this context. It's a singular, particular state of affairs attached to a particular person who is part of it, has a stake in it, and has a perspective on it. So that's typically my case right now. I'm in this particular situation. I'm facing you, hoping that you will hear me to the end. And I have a stake in it. I don't want to make a fool of myself. I have a perspective on it, etc. So that's what I call a situation. Now, there's a third part of third aspect, which I will, for the sake of time, not discuss. Of course, appropriate, what the right thing to do is, what the appropriate behavior is a normative concept. And there's a lot to say about it, but I think I can skip it just for today. So my point is, what is required for being in a situation? So I'm sort of trying to make my way back into the notion that indeed intelligence requires a body. And this is the way I'm trying to do it. So you have to be an integral part of the world. Inter alia, you have to interact with real entities. That requires having a body, and a body that is one's own, and that one knows to be one's own. So those two last things, especially the last one, get a little bit delicate. And this is almost my last slide. So I'm going to leave you with essentially a puzzle on knowing that my body is mine. But I'm sure there's resonance in, you know, the thoughts that you've had as roboticists, of course. So this is the bug. Having a body, knowing all there is to know about one's body, the position of one's body in space, the degrees of freedom, etc., etc. And yet, it's possible, I claim, that's why there's a bug, not knowing that it is mine in the right way. So what seems to be missing is what philosophers and linguists are calling a décès representation of one's body. Décès, they claim, and I tend to agree with them, but there's endless discussion about that among philosophers. A décès representation of one's body, a perspectival representation of one's body is not entailed by any non-perspectival facts. Fred can believe that Fred is tall without believing that he himself is tall in circumstances such that Fred doesn't realize that he is Fred. So this is what philosophers, and I think the expression is that of John Perry, a very able philosopher, a very popular philosopher also at Stanford, what he called an essential indexical. So clearly we humans have correct DC representations of belief in normal circumstances. So this thing about Fred being tall, knowing that he's tall, but not knowing that it's he himself that's tall, involve intricate scenarios. They're tons. They're very amusing, in fact. But they're scenarios, I mean, sort of unlikely circumstances. In normal circumstances, of course, I know that I'm speaking, I, Daniel Andler, am risking my reputation and so on. It's really me. No doubt about it. So that's not in question. But the problem is, for philosophy, to try to account for DC beliefs or essential indexicals. What exact cognitive mechanisms are at work that allow me to know that I am the person speaking right now? And for cognitive roboticists, the problem is whether they can equip an intelligent robot with DC beliefs. So, oops. No, won't move. So wrapping up, it's about time, a little behind, sorry. So if one, AI aims at human-like intelligence, if I'm right in claiming that's the goal. If two, intelligence is the ability to engage with a situation appropriately. If three, the ability to engage appropriately or not, in fact, with a situation requires having a body being embodied, then being embedded in a robot is necessary for being intelligent, but it may be sufficient only if the robot has a DC representation of itself. And this may require, for example, some kind of self-aware ownership of one's body. Maybe developmental robotics can teach us something about that. That's it. Thank you. Resting my case with the hope that my question rings a bell.
Thank you so much. We have time for one question. Yeah.
Thank you very much for such a thought-provoking lecture. I really appreciate it. In your very last slide, you mentioned representation, and I was kind of curious what you think about the enactivism versus representationalist debate in philosophy. The enactivists such as Daniel Hutto and Andy Clark, and representationalists being more Newell and Simon. And is that relevant to your talk today?
Well, I can't give a full response. I think that I started out as an anti-representationalist because, in fact, speaking again about myself in Berkeley, when I arrived, I met and befriended Hubert Dreyfus. Hubert Dreyfus was a premier critic of AI, and he was strongly anti-representationalist, and among his disciples, the issue was who is being the true anti-representationalist, the really hardcore one, and who's being a little soft. And actually, with the years, I've become a little soft on this issue. I think there's the perfectly legitimate uses of representation in CogSci, lots of areas of CogSci, and sort of this strong anti-representationalist stance seems to me sort of ideological. I don't really espouse it. But more specifically, yes, I think the issue is extremely relevant because we have to know whether a representation in the sense is, can we distinguish between representations which allow us to function in a certain way, have well-adapted, well-adjusted behavior. If I don't know that I'm myself, I might make a terrible mistake and fall off the stage or something like that. So we have to, we seem to be relying on some sense of representation. We have to know what exactly we mean in order to know whether there is a distinction between a DC and other representations, which some philosophers deny. They're in the minority, but they do deny it.
Can I ask you just a quick question? It's probably it's very naive and probably wrong, but to me there's one good argument to have embodied intelligence, is that at least in my most of I know about AI, real AI today, it's about acquiring skills, logical intelligence, and most of what I know of AI is about really doing pattern recognition, so do regression or do classification, and usually in classification the labels that you put on things are purely symbolic. They don't mean anything. So when I recognize a dog, I don't recognize a dog. I put the label of the bag where the examples were. And at some point, it seems even for moderately intelligent skills, You need to have some understanding, I'm not sure what it means, of what things are. And for that, you need to ground, in some sense, whatever you are doing. And to me, it seems plausible that having a body is a way to ground it, because you interact with the world, and that will give some meaning to what you are doing. So what do you think?
Well, no, I agree. It's a perfectly plausible way to go. And this is, in fact, why I was mentioning developmental robotics, because you see the Oudeyer's small babies who sort of grope, and you imagine they're beginning to ground their internal symbols somehow, perhaps. But yeah, I tend to agree, it's plausible. But I don't have a fully worked out theory of that. Yes, thank you.
All right, thanks, Daniel, again. Thank you. All right. Yeah. I'm just waiting for the
okay.
to flip. Okay,
yeah.
cool. Okay, so last speaker of this session is Antonio Bicchi. So Antonio is a scientist working in robotics and intelligent machines. He graduated in Pisa and received a PhD from University of Bologna, then spent some time at MIT. And then he became a professor in robotics at University of Pisa. And then he founded the Soft Robotics Laboratory at the Italian Institute of Technology in Genoa. He's very famous in robotics. Among other things, he created the IEEE Robotics and Automation Letters, and over the past few years, he's been working on building, more than the past few years, decades, working on building artificial hands. And today you're going to talk to us about bots and men, and very much looking forward to your talk. Thank you.
Thank you, Ludovic. Thank you, everybody. It's been a great pleasure to be here. 10 years since I came last time for the inauguration of Jean-Paul. It's really something that struck me, not just because Jean-Paul is not here longer, but because of the fact that so many of my friends felt the same. I think this was, and today is even stronger, because we are talking, and it seems to me that many things we are saying have been influenced so deeply by this group of people, by Jean-Paul mainly. So I'm going to speak about bots and men for those who haven't read Steinbeck of Bots and Humans. Robots are something that fascinates us because basically because we in robots see our reflections, and sometimes it's like Narcissus. We really spend time in looking at the nature of artificial things and admire ourselves. But so this relationship between natural and artificial, or between body and mind, is something that is coming back and forth. Ken has mentioned that already. What we do is we try to study intelligence per its embodiment. I think this is what defines robotics with respect to pure AI, as we just saw in the last talk. And this is a picture that Ali, for instance, has also shown before. The work that we do tries to build machines that build on top of the understanding we had from nature. Human motor control, psychology, neuroscience inform our cognitive models, the artificial intelligence we use, the humanoids we build, the very motors, the actuation, the mechanics, and then the sensors, and then we try to understand better by recreating. Behind this idea that is common to many of us is an assumption that I recently discussed in a talk, and there is a paradox, really, because we are building lessons from, we believe that body are important to intelligence, and then we try to learn lessons from body A that apply to body B, but body B is completely different from body A, so how can it work? And the only way to do this is through the use of mathematics, of course. We need to abstract lessons from one domain, from one body type, to something that is more general, mathematical, if you want, build a science, to build a science of embodied intelligence. And here, of course, I cite Galileo, who said the universe is a book that is written in mathematical terms. I think this is really where Jean-Paul and myself, Jean-Paul and many of us, really had the strongest connection. This idea of trying to understand at a higher level what happens. I'm very glad that Ken showed this already. This is something we did back in 1996. You mentioned that, and you also have a website where I pick this picture every time because I tend to lose it. So this idea was, this workshop was about minimalism, trying to find the simplest solution to a given problem or set of problems. I think this was, this is this is rather far away from what we do today, what many people do today, where you have no limitations on computational resources, for instance. At that time, many of us thought that, well, you know, you have to think deeply to whatever you do and try to find what is the minimal set of sensors, the minimal algorithm, the shortest time path to do something. I really think there is some worth in this. Of course, there have been some exaggerations. So for instance, going back to this, I was thinking of non-holonomy. At that time, I have slides from a very, very old talk, 2000. Non-holonomy on purpose. So we have been talking of non-holonomy. I was very pleased to listen to Philippe this morning. Non-holonomy means that basically you have less inputs, less actuators than states, less actuators than configurations. So you can drive a complex system with fewer actuators, so that can save you something. And then at that time, we were you know, trying to spare hardware, but not just for the cost, but for the conceptual saving. So this idea of building non-holonomy on purpose was something that was mentioned by Brockett. And Nakamura and Sordalen built a whole arm, 6 degrees of freedom, that only had 2 motors, and proceeded by combining their motions in ever more complex Lie brackets to move everywhere the end effector. It was a very complicated thing. It was not very practical, but you could move everywhere in space with only 2 motors. There have been many others. Arise under actuated Peshkin and Colgate, Mad Mason, what is it? With Kevin Lynch, Ostrowski and Burdick, Kodicek and Rizzi. I've been working with hands since a very, very long time. And the hands that we did at the very beginning were hands that had at least 9 actuators, at least 9 joints. Actually, Salisbury's hand had 12 motors because he had one slack degree to control. This other on the right is in Bologna. And the goal for dexterous manipulation is to reorient objects in an arbitrary SE3 configuration. And then at that time, we started doing, okay, but if we exploit rolling motion, then we can reorient an object at will by only using 2 inputs. And indeed, we built this little device here that was rolling around objects, bringing them in an arbitrary position and in an arbitrary orientation. And these times, I remember very often discussions with Jean-Paul, who was developing his own work in a similar but different rate. And this is another version of the same thing. Something interesting was also the fact that, and we discussed it with Jean-Paul, that if you roll objects, not only smooth object roll, but you can also roll polyhedral. And if you take a die and you roll it right, back, left, and front, in the end, you get to the same position, but with a different orientation. So there is non-holonomy there too. And you can actually define a non-holonomy in discrete systems. That took me a very long time to just to give a definition. And on this topic, I wrote a paper that took me, it took me 7 years to write the paper, and I got 7 citations overall. So it's one of the, well published on TAC, on TAC, but you know, it's not very effective. But I think it was one of my best loved papers. I still love it. And there is a lot of things that, because depending on the ratios between these sides and angles, you can either have a lattice or a dense set of reachable positions and so on and so forth. But the thing where Jean-Paul really inspired us was in optimal control, which is important to translate theoretical intuitions in precise concepts and usable tools through which natural and artificial science and technology can meet. It provides a principled basis to compare performance of different embodiments, and it is also the dominant paradigm, still today, is the dominant paradigm for understanding and generating model behavior in formal or computational terms. Even today, I mean, optimal control is the way most of our four-legged vehicles move around today. There are 2 main ways by which you can use optimal control. One is inverse optimal control. We have heard Katya speaking about this before, or direct optimal control, which is trying to do the solution. And this might be computational or formal, symbolic, trying to distillate principles. So this paper that was this is one of the papers that we have seen this morning. That was important because we had these tools of optimal control applied to natural locomotion. This is the work that was done to, was shown a little ago by Katya. In the meantime, we were trying to find optimal control for vehicles under non-holonomic constraints, such as vehicles with fins or wings or wheels that had limited field of view, which is similar to what was discussed in this paper here. And we tried to do this analytically, and it turns out that if you do Pontryagin maximum principle, and if you consider that the feature that you have to go to has to remain within the camera, then it has not to get out of the borders. So basically, it's a bang-bang control that goes through there. And the extremals include straight lines, parabola, and logarithmic spirals. And when we found the logarithmic spirals, we say, wow, what is this? Why? And very funny, it was that we then found out that falcons, raptors in general, go to their prey following logarithmic spirals. Because what they do, they want to keep, and this again was a suggestion by Jean-Paul to look into this, they want to keep the most aerodynamic posture so they don't tilt their head, and they have lateral sight with limited field of view. So to get to some prey as fast as possible, what they have to do is to keep the prey at the angle of their eye, and that means a logarithmic spiral coming out. And not only them, but also moths fly along spirals, and therefore winged vehicles with side-looking sensors should do that. Fishes, sharks, follow logarithmic spirals. And humans, to the approximation given by the studies that we had from Jean-Paul's and Katya's group, also follow rules that can be reconstructed by these extremals. So that was work by Paolo Salaris and Lucia Pallottino, myself, and others. And that was very fun to remember. I must say that today it's been kind of strange because I started out listening to talks, and in some sense these talks were giving me a hand to make a shorter talk because they were already introducing many of the things that I'm saying. On the other hand, they were recalling me things that I had almost forgotten. I said, oh, wow, but that was also that thing that we did with Jean-Paul. So I was putting more slides in the talk. Coming back to hands, hands have been, a long story for us. Human hands are very complex systems with incredible number of nerves. There are 350,000 nerve fibers that go to the hand, tendons, nerves, and sensors, receptors in the skin. And the question that comes to mind is, again, how can the brain cope with this complexity? And again, my, I would say, obsession with simplification, making things simple, which is not easy, always. We're not, I must confess, we were not very happy with this non-holonomic planning. But we wanted to have hands that used less than 19 motors. Not just because we were stingy on motors. Because I don't believe that a person that uses a hand, for instance, as a prosthesis, can afford the attention of moving 19 degrees of freedom independently. Or even a programmer of a robot. You don't want to write programs that deal with 19 and think of where the pinky should be when I grab an object. So we came up with the idea of synergies, considering synergies as constraints that the embodiment imposes on the learning and control strategies. Therefore, not mere bounds, but rather the definition of the freedom. And these synergies are at all different levels. In a project that we had some time ago, it was called The Hand Embodied, with some colleagues that are listed here. Aline was one of them. We defined this architecture where you have these synergies that basically are abstractions that go from sensors, for instance, to abstract percepts, or from motor commands to the detailed implementation in the motor apparatus, but also sensory-motor synergies, which are the early loops that are closed between the motor behaviors and the sensory behaviors. Now, synergies turn out to be everywhere. Since then, we have discovered that synergies are at every level in the architecture. Of course, they are at the kinematic level, where you can observe them by just making the statistics of how people move the hands and taking the first principal component, but also at the muscular level, in the cortex, and even in the spinal motor neurons that speak to our body. And there are connections that you can make between these systems of synergies that are important. For instance, in prosthetics, in a project that we are doing now with Dario Farina and Oscar Asman, to control a prosthetic hand in a natural way with the inputs from the brain. We have been building on this idea of synergies. We have been building soft hands that have basically the same degrees of freedom of a human hand, 19 or more, but only use one or now two motors to do one or two synergies. And there has been some development of these hands, both in industry and in prosthetics. The feature is that although there is only one motor, the full degrees of freedom of the hand are there, and so the hand behaves in a very close way to the human. To achieve a given configuration of the hand, you have to reason on how the environment will deform your hand. will affect your shape. So I think this is interesting, at least it is to me, because instead of now having 19 actuators to think of, you have 1 degree of actuation, but you have the full dimensionality, 19 independent degrees of freedom, that will get their shape based on the interaction that you have with the environment. So basically, you have to think how the environment will shape your hand when you do something. For instance, if you want to put your hand in the pocket, the pocket itself will make your hand straight. You don't have to make it like flat before putting it. You will just go this way, and then it will flatten within the pocket. And this changes the perspective of how you think about things. It's not, I was mentioning already that the feedback part is also very important. There are 350,000 nerve fibers, of which, interestingly, only 10% are efferent, go to the motors, go to the actuators. 90% are sensory. And when you do control of the hand, therefore, the sensory part is important. It's not important, it's dominant. My colleague, the surgeon, Oscar Asman, says motor control is a sensory phenomenon. It's dominated. So the question is, how do you use this and how do you address this? There is a very interesting paper by Johansson and Edin who says that basically whatever we do is, whatever control we give to our body is not just a motor command. It's a motor command together with an expected output. And when they match, then you are in a situation that you say, okay, everything is going smooth. So there is this sensory motor contingency or sensory motor synergy that is part of the plan. So motor plans contain a sensory expectation, and the physical iteration generates feedback, and if you do it artificially, it must produce a consistent feedback. And if you want to have a natural bionic hand, then it requires to have consistent artificial sensory motor contingencies or synergies. So here is
this prosthetic.
Yeah. So sorry. Oops. I just didn't want to have the sound, but okay. The video should start.
This competition for me means really being in a great team, in a special team. I really feel the support of all the members. Being there in real life, this competition for me means really...
Yeah. So here are some videos, not showing very well, some videos of the prosthetic hand and the kind of abilities that you get out of this minimalistic, in some sense, design. It's minimalistic in the sense that it only uses one motor, but it's maximalistic in the sense that it's the artificial hand that has the most number of degrees of freedom. Okay. Soft feet help humanoids and humans as well. So if you move the same principle from the hands to the feet, you have something that is more recent. This is work by Emmanuel Candelano together with Jason Ventoux, of having feet that adapt to the environment. And you see HRP4 there that is walking, and we have seen very nice videos this morning from Nicola and others. But if you put a 1 centimeter square obstacle under the flat foot of a robot, still today it is a problem. While if you have adaptation in the feet, then the same robot, the same control, no modification, can easily handle that. And of course, this also reflects to prosthesis, where people can help, can negotiate small obstacles much more. So this is something that physics can do for locomotion very easily. final part of the talk is the same idea of sensory motor contingency through a device that is no longer a prosthesis, but is an avatar. So, well, in some sense, it's the same thing. It's a distal reality, if as Ken said before, or is a complete prosthesis, if you want. It's your body somewhere else. If you want to live somewhere else, in a remote, in a distal reality, then what you want to do is to be completely there. You want to see whatever the robot sees. You want that the robot can do things with their hands. You want to move your head, you move around, but also you want to have reactions from the environment that are consistent with your expectations. So your sensory motor contingencies have to be matching. And we have done this in several cases. We started in 2016 with a robot that we sent inside an earthquake, a humanoid that we sent inside a house with an earthquake, just to use the extra capabilities of robots to assess, for instance, the damage in the house. And you can do, also you can use this very simple idea of sensory motor contingencies to plan actions of a robot. So for instance, here is a robot that is being teleoperated to do pesto, which consists of a very few simple operations, like you need basil, you need pine seeds, and oil, and then smash it. Okay. So what the robot does is a sequence of things. If I see that the basil is here, I just go and grab it and put it there. And what we do is we record this sequence of sensory motor contingencies. And once you have recorded them, you do replay. And wherever they are, they don't need to be in the same place, but you know that first action was to get basil. So with your perception, you look for basil, and then you pick basil and you put it there, and so on and so forth. You simply go for the next situation in the recorded sensory motor contingency route, and then you replay. And it looks like it has been learning, or it has been, something more, but it is just a replay. And it can do, of course, the same thing many, many times, even faster. Along this line, we have developed a smaller robot that is manageable. It's called Alter Ego. It's an autonomous humanoid robot that accepts human inhabitants. It has soft robot muscles, soft hands, tactile, visual, audio feedback, and the possibility of controlling the impedance can be stiff or soft, depending on how the human wants it to be or how it is programmed. So it can be autonomous, as you see here, doing little things like following, giving your hand, shaking hands, nodding, being nice to people, these things that that you are used to see by now. But as I was saying, it can be inhabited by humans. So you can jump in and become the robot. So you can do things, for instance, the idea is that you can leave it at home and do things that are useful for people there from wherever you are in the world, at office or somewhere else. You see what it sees, you feel what it feels, you are there. And actually, after a little while, people really become convinced that they are there. We tend to forget that you are there. One last thing is that we discussed with Jean-Paul was dancing. You know that Jean-Paul had many, many interests. One was dancing, and here is the robot dancing with people. In some cases, it is following. In some cases, it is autonomous. It can learn. But that's pretty much it. So I will close with this little picture of Alter Ego. I was saying one thing that I came to notice is that after a little while you become a robot, you are a robot. There are things that are very funny. So you feel like if you become him, so or it or her. So if someone comes, you're afraid. If you see someone that surprises you, you have reactions. If you come back after a little while and you see yourself, you jump because you don't expect yourself to be there anymore. You sort of disappear from. So so the question is, it makes me think of what it is like to be a bot, in the sense of what it is like to be a bat. The famous cognitive science paper by Nagel that I'm sure Christian knows, that asks what is it to be a robot. So this is Jean-Paul, and this is a picture that was not taken for Jean-Paul. This is a natural picture. I think I love this picture because Jean-Paul is with us, but you see his position is there. It's not just elsewhere. It is there within us. Okay, thank you very much.
Right, thank you very much. We're a little late, but I guess there's a break, so we have a minute for one question. If there's any question.
Yes.
Yeah.
It makes you feel like a kid, because you see everybody from a little bit below, and so you feel like a little bit weaker, a little bit something that everybody loves. It does influence your way, the way you feel. Yeah, definitely. Not in a bad way.
All right, on that note, thank you so much, Antonio.
So we have the break now, and we have to be back here at 4:30. Thank you.
to say a couple. I'm going to have a show.
Oh, that's Jean-Paul?
Yes, a little bit overly. I want to say a little bit. It's kind of like the mentor of the mentor. There's a recorded talk of his here next week. You're next week. Yeah. Then you're next week. Training intros for you. I'm going to list every one of your publications and all of your service duties that you've done. And then you don't have to publish. In the 90s. That's all I know. There's debate about it. Jean-Paul said it was in California, but somebody else told me from Arizona. That's a New Mexico license. They believe, but I still think it's California because of the water line and stuff. I don't know what they were doing. Okay, let's go ahead and get started with the final session. So I'm Stephen Laval. I am a professor at the University of Oulu. I'm American, but you might notice that I have a distorted French name. My ancestors left France for North America about 14 generations ago along my paternal line. Somewhere in the middle, we lost the ability to speak French, so I'm sorry about that. You can blame Napoleon for that one. So the Louisiana Purchase kind of forced our people to change their language. So I was very, very fond of Jean-Paul Laumond. I found him a great inspiration. He helped me many times. He was a great friend, and it's very sad to lose him. I gave a memorial talk about him at Wavefront a month ago in Washington, D.C. While I was researching his background, I loved this picture because I noticed in so many of Jean-Paul's talks, he mentioned Georges Giral, who was the co-founder of LAS. And he mentioned Georges Giral as his source of inspiration, and so I thought it would be nice to mention him here as well. This is it kind of shows Jean-Paul's sense of humor, I think, as well there. So the director and employee of the month. So this is kind of a funny American thing that they're poking fun at the same time. So I have a brief video clip that I really like of Jean-Paul, so I want to play that, and then I'll go into the session. Okay. This was I believe this was taken from a brief speech that he gave for his inauguration into the French Academy of Sciences. But correct me if I'm wrong, but I think that's what it is.
La roue de la fortune m'a amené à vous. C'est aussi une belle reconnaissance pour la robotique. Les robots, ces machines qui bougent, font l'objet d'interrogations légitimes et de peurs souvent fantasmées. Le roboticien a le devoir de dire ce qu'il en est. Comme un artisan un peu démiurge, il interroge nos connaissances et parfois contribue à leur production. La robotique nous dit ainsi que notre intelligence, cette notion moderne qui n'apparaît qu'à la fin du XIXe siècle, n'est pas le seul apanage du cerveau, mais qu'elle doit beaucoup au mystère encore non élucidé de notre corps en mouvement, ce corps qui dialogue et lutte sans cesse avec la gravité. La robotique, c'est l'intelligence de la gravité. Contrairement aux idées reçues, ces progrès sont lents, logarithmiques comparés aux impacts exponentiels des travaux actuels en intelligence artificielle. Il est d'autant plus important de soutenir ces équipes de recherche. Je vous remercie pour la confiance que vous m'avez accordée.
Okay, thank you. So with that, we have 3 talks in the session. The first one is recorded in advance. So the speaker is Professor Vince Hayward. He's a professor here at the University of Sorbonne, so just around there somewhere, but he was unable to make it today. He is very well known for his work in tactile, touch, haptics, tactile perception, and he's from Paris originally, grew up, at least born in Paris. I think he may have grown up there. And then he spent most of his career at McGill University in Quebec, and then has returned to be professor here. So I will switch over here and play his video. I think he's not going to be available for questions online. So.
Good afternoon.
That's not going to work.
I'm particularly touched to be able to...
Yeah, it could be. Does someone know how to send the output? I don't know this laptop, but it's regular. It could go out through HDMI, but if not, I'll put the microphone. Should I do the microphone trick and just, okay. Should listen to you. Oh, and thank you to Jean and Philippe for organizing this. I forgot to mention that. I appreciate it very much. Okay, let's try yes, I'll go back a bit.
Good afternoon. I'm particularly touched to be able to speak to you in the memory of Jean-Paul Laumond on a topic that is very dear to me and which Jean-Paul also had a keen interest. My activity is mostly concerned with the natural world, and but I also keep an eye on what's going on in robotics very often, and I hope that some of my findings will have some echo in the robotics activities.
This one's doing nothing. Okay.
What I would like to emphasize is that, of course, all animals have a keen sense of touch. It's not limited to extremities. You know, the entire body is sensitive, and there are many ways, actually, animals take advantage of touch. It could be whiskers, it could...
It was fine. Well, it was fine, I think. Okay. Sorry.
Nice try.
It could be hoops, etc.
Sorry.
Good afternoon. I'm particularly touched to be able to speak to you in the memory of Jean-Paul Laumond on a topic that is very dear to me and which Jean-Paul also had a keen interest. My activity is mostly concerned with the natural world, and but I also keep an eye on what's going on in robotics very often. And I hope that some of my findings will have some echo in the robotics activities. What I would like to emphasize is that, of course, all animals have a keen sense of touch. It's not limited to extremities, you know, the
entire body is sensitive, and there are many ways actually animals take advantage of touch. It could be whiskers, it could be scales, it could be hooves, etc., etc. But here we'll focus on the soft extremities, which are very often an attribute of mammals. And so that's an example here, but many mammals have soft extremities, which are particularly interesting, of course, in terms of tactile mechanics. So the first question I'm asking is that, of course, touch is a computational problem. It's a problem that robots or brains have to solve in order to be able to take advantage of sensory data. And this problem was of course, looked very carefully in the visual world. There is a well-known way of expressing or framing, if you want, the space in which visual computation takes place, and it's called a plenoptic function, which means essentially it's an abstract function which embodies anything that can be seen. And of course, real robots or real animals only have access to a subset of that space. Like a camera would have access to a two-dimensional image. But in general, in vision, the plenoptic function has 7 dimensions, which are readily deduced from the way photons behave. So the question in touch, what would be the equivalent? And so this question can be framed in terms of solid bodies that interact, like A and B here. And when you have a tactile interaction, then they, in general, undergo deformation. And then here we can assume that the body B has some sensing capabilities, so it's able to tell something about its own state change. The trouble is that actually, because of the way continuum mechanics are made, the configuration of the bodies A and B are by nature infinite dimensional. So there's and essentially the deformation of these bodies are captured by an infinite number of trajectories, which I've labeled here A and B, small n and small b, which establish this plane haptic function. It means everything that could be felt in principle. And of course, the robots or the brain's problem is to guess something about A, like whether it's slippery or sticky, or is it soft or hard, or rough or smooth, and from a very small subset of B, of course, which are essentially the set of mechanoreceptors that are embedded in our body. And of course, this problem is in some way analogous to the problems in audition and in vision, but acquires a particular nature in the mechanical domain because of this intrinsic infinite dimensional space in which it occurs. So I won't go into any development but I'll give some examples, one theoretical and then one experimental of manifestation of this idea. Well, before doing this, I'll mention in passing that, of course, it's not very well known, but like in audition and vision, there are lots and lots of tactile illusions that are really fun to expose. And here there is a reference to an article maybe you might consult, which gives some hint on how to actually make them at home. Of course, there are, since then, actually, there are many more which have been discovered, and they are just as interesting and intriguing as visual illusions. Where does sensation comes from? So we've already outlined, it comes from the fact that when we touch things, our own body deforms as a result of the interaction with another or several. And so here's a very simplified example, essentially a finger which is sliding on a glass surface, and then we've recorded actually, if you want, using an imaging system, what could be these deformation trajectories. And as you can observe, they are nothing but simple, but they do have some characteristic patterns, which you can see actually the periphery of the sliding surface slide before the central region, and then there is a dynamic which is both a function of the materials in contact, which is the skin against the glass, and the movement that you do. Here's another example. It's the same technique, but here the finger moves in sort of more arbitrary manners, and then you can see that there's a different, very different set of trajectories. But what is mostly intriguing is that actually, if you do that on your telephone, you will essentially experience consciously two main sensations. One is related to shape. You will have a very keen experience that actually the surface of your telephone is flat. And the second is that actually it's made of glass. And I can assure you it's partly due to the thermal property, but it's mostly due actually to your brain's interpreting these deformations as being characteristic to glass. And of course, you can extrapolate that this idea can be extended to many other examples or many other situations. This is like a theoretical development on how actually processing could be done. And the idea actually is inspired from vision. Essentially, in vision, it's known that actually an important early processing in visual systems is actually to detect zero crossings in the Laplacian of the illumination, and we thought there might be something similar in touch. And here we have an example. Say you have a coin that you hold in your finger on the upper left corner of the slide, and then if you compute the shear, which is actually the components of the deformation tensor of diagonal components, you see that actually something interesting happens. The shear is as a positive value on one side of the coin and negative value on the other, and it goes to zero when the coin actually touch. And you have something similar, say you have a pin pushing on your skin. And the idea here is actually that maybe it's something due to, it could be due to actually the properties of the peripheral nervous system, or maybe to a higher order computation. But it could very well be that actually detecting zero shear is a way of detecting edges. And what we have shown in the paper, it is actually robust to uncertainty. in the same manner as early vision edge detection is to illumination and scale. But here there is no notion of scale, of course, there is no notion of illumination, but there is a notion of actually how hard a object is pushing in your skin, and of course you can immediately experience that if you have an object in your hand and you feel an edge on it. The edge is present regardless on how much you push, and you might really well actually modify the deformation pattern in magnitude by 2 orders of magnitude without even realizing it. So this process is analogously robust to this perturbation, but many others as well. Here is a experimental example. What you are seeing here is actually small specks you see on the screen. Is a high resolution imaging on something called the true contact between a figure and here again glass, and the true contact basically betrays what part of your skin is actually in very close proximity to the glass. And you can see it's very small. You can hardly see it, but if you wait a little, you can see that actually it grows through time, and after a number of seconds, then actually the true contact area becomes your fingerprint. But it took a long time, and so that process is actually explained by the fact that water diffuses from your body and then gets trapped in the interstitial space between your finger and the glass, and then the force of adhesions and friction vary at the same time, which is quite amazing because you've probably never realized it. But if you remove your finger from the glass, then the water will evaporate, and then the finger will come back to a more dry state. And this process is a combination of a chemistry going on, a phase transition actually going on in your superficial layer of skin, and then interaction with water. And then so the so this is reported. If you're interested, you can look up it in this article. But to make it, to drive the point is that we've actually performed the same measurement with an elastomer surface which is actually softer than your skin, because when your skin is dry, it's actually very stiff. And then when it's wet, it actually loses its stiffness by something like 3 orders of magnitude. So it's not very something negligible at all. And you can see that actually if you touch an elastomer, then the friction is immediately established, whereas for glass, it will take, as we've seen, 10 to 20 seconds before reaching the asymptotic value. And this can be actually seen as a super incredibly useful source of tactile information when you manipulate or you hold objects, and you have to tell what they're made of. If it was paper, for example, paper is porous, and the process would be completely different because the water would actually diffuse inside the paper, and then the process would be extremely slowed down, and that will actually tell you that it's paper. And the speed at which it does that is actually a characteristic of the type of porosity that the object has. It could be wood, it could be all kind of common materials which will drive that process. So we have seen 2 examples here. The first was this incredibly rich pattern of deformation when the finger slides on glass, and the second is this incredibly large variations of contact mechanics when you touch different type of materials. So these are only two examples. I've spent the past 20 years collecting all kind of other examples of if you want, mechanical phenomena that are relevant to touch. But the main point here is that I would like to mention that actually often it's said that the skin is like the retina, and that's really a misconception. The retina, as you know, is actually a really elaborate neural net. It has neural layers that perform early processing, and that would be completely, and what they do is really break down the image into bits that are understandable to the rest of the brain. And that process in touch is carried out not in the skin, of course, because that would be probably impractical. It's carried in a nucleus, which is at the top of your spine in a brainstem. And numbers that are quoted here actually refer to a small animal. So if you are talking about a big animal like us, then you can add 1 or 2 zeros to all to these numbers. And the most intriguing part of this nucleus is that it's been identified in fossil records since the Triassic period. So it's a very old brain structure, which is shared by all vertebrates. A little bit like the retina is essentially shared by all vertebrates. And so it's a particularly intriguing piece of neural machinery, which actually makes your tactile system works. So we can look a little bit the way it's made. Essentially, it's made of a large set of cells, of course. We'll look into the architecture a little later, but they are essentially a layer of output cells, which is shown here. It's actually a real image. And what these output cells receive are inputs from the skin, of course. But contrary to what is often assumed, it's a very different type of architecture, actually. All the inputs for a single cells arise from very large regions of the skin. It could be by extrapolation from small animal in a human. It could be one cell would actually receive inputs from the whole fingertip. And so the difference is that actually you will have many, of course, of these cells, and they will have, of course, many synaptic waves. And what we've been able to show is that they perform a really crucial type of computation that is if you want, in some abstract way, analogous to the work that the retina does in vision. It's made like that, essentially. Primary afferents enter from the bottom, and then they project into this really essentially in a human that would be 1 million cells, output cells. and so what we've been able to show is that actually if we drive actually the tactile system with different type of stimuli which differ in terms of their temporal or the spatial characteristics, then these different cuneate neurons are actually not tuned. That's what we were hopeful, but it didn't happen. They were not tuned at all to a specific stimulus. But what they could do actually is actually separate them apart. And that's really the key point, actually. They can separate these very small differences in spatial and temporal characteristics of input patterns. So this is essentially table that shows that actually, instead of being, if you want, clustered in sort of specific places, these cells actually occupy the entire tactile space as uniformly as possible. And that's really the lesson here. So the neural circuitry essentially is a bit like that. You have, afferent inputs from the, which are shown here in red, green, and blue, and they have excitatory inputs on the output neurons, but there are also interneurons which have inhibitory action, both from other neurons and from the inputs. And the whole thing actually, so as I said, you have to imagine that you are looking here at millions. You have a really interesting neural machinery, which nature has invented since the Triassic period to process tactile inputs. And what it can be said immediately is that it's very different, of course, from the neural machinery that makes audition work or vision work. So I'm glad to report that I will be spending the next 3 years to look into this tactile mechanics plus neural circuitry in detail and developed, if you want, a model of how that can be working. And I'm hoping that the result will have some impact on the robotics community. And with that, I will stop. And then because I'm not able to, unfortunately, be there and present, I will be very glad to answer questions by email. Thank you very much.
Okay, the next two speakers are here. I'm happy to introduce Professor Alessandro De Luca. I'll give you a little brief intro, but please go ahead and...
No.
You're good, okay.
Oh, go ahead, if you wish.
Oh yeah, I should be talking at a microphone, I guess. Professor De Luca is originally from Rome, studied in Rome, and continues as a professor at the University of Rome, La Sapienza. I guess if you're from Rome, where else should you go, right? So you've... And his work certainly fits in this workshop very well. He's done a number of works many years back on feedback control of non-holonomic robots. He has a strong control theoretic oriented approach to robotics and has done many, many works. In recent years, he's become more interested in human-robot interaction, particularly in making robots safe for humans and maybe keeping the robots safe too. Would that be fair?
Why not?
Why not? I also want to mention that I very much appreciate his deep amount of service that he does to the community as well. So he seems very active in whether it's conference organizations, editor-in-chief of the Transactions on Robotics, and many, many panels. So he does a huge amount of work. I don't know how he fits it all in addition to his research work. So that's well appreciated. So thank you. Take over.
Thank you very much, Steve. Thank you for inviting me here. I'm wearing a tie, and I was expected to do so. I see that Jean-Paul was doing the same in very important occasion, like it's this for me. So I will talk about a topic which is not really related to what Jean-Paul was doing, except for some news that I discovered just preparing this presentation. So you have seen this before. Let me just add this, that these workshops and this meeting were taking place in Rome, and Jean-Paul has spent a lot of time in Rome, and he promised me that he would come every year to Rome. So unfortunately, this is not longer possible. But this is new. In fact, in one of his longer periods, I spent a sabbatical in 2011 in my department, and he gave a lecture which is nothing else than the pre-release of his opening lecture at the Collège de France. So we were so lucky to have this in preview. And you see here Jean-Paul with Marilena Venditelli, one of the people that has worked with him and written a paper. I haven't written a paper with Jean-Paul ever, and probably one reason was that I was very critical on the name of his group, Geppetto, because I said Geppetto is there's a typo in your group, because Geppetto is written with 2P and 2T. So I don't know. I'm joking, indeed. So let me move to the point. So I will talk about physical human-robot interaction, and my background is in control. So I've heard this morning that you can handle robotics from the optimal control point of view or from the learning point of view. I'm in between, in a sense. I'm not doing optimal control. I'm doing feedback control, and I'm using feedback control in order to let the robot behave as we desired according to some models. So in this context of physical human-robot interaction, there are several problems here. Here is a kind of a chain. We should be safe, and in order to be safe, we should be able to detect collision and react to collision as soon as possible, and also locate or isolate where the collision happened, and possibly without the using of sensor or extra sensor, external sensor, or even extra joint or sensor. If you have it, you can use it. The second aspect is the most common that you find in Industry 4.0. When you hear about human-robot collaboration, what is in fact is just coexistence. They are not doing something together, but they are sharing the same workspace. But if you want to do that in safe manner, you have to continuously monitor the workspace, so you need extra sensor, and you have to implement some collision avoidance schemes. And you should do this in real time. And finally, the most interesting part is when you interact intentionally with a human, because you want to perform something together. So you need to estimate, because you cannot measure them directly, the contact forces, and based on these contact forces, achieve some kind of human-robot collaboration. You may have a force sensor at the wrist or not, and this is what I'm talking about now. Now, in order to address these several control problems, safety-related, after a while, we decided that we have to put everything into a architecture. This is a good thing to do if you develop software. And we organize this in 3 layers, which are always active. The most inner layer is safety. And in fact, with safety, we should handle collision detection, isolation, and reaction. Then coexistence. Indeed, if you have coexistence and something goes wrong, the lower levels should come in, and you have to react and stop the robot or whatever. But then, on top of that, you may coexist with your robot, but at some point, through some communication, which could be a hand waving, a voice command, or touching, and so on, the robot understands that you want to collaborate, and then you switch to this other situation. And typically, you coordinate with the robot typically with physical interaction. There are other possibilities. Just to have an idea of what we mean to that, this is a video taken from, was a finalist video at IRAS 2013, and you can see the 3 layers always active. And here Fabrizio Flacco is waving, and then the robot is going to his hand, but is avoiding the other part of his bodies. And then when he's taking the end effector, then is following like in a play mode. Okay. But I think that the last part of this short video is most important. Of course, it tries to avoid other obstacles. And now, he tried to bring the robot against his other arm. And the robot becomes stiffer and stiffer because, coexistence is more important than collaboration, and in case, safety would be more important than coexistence. So this is the kind of things that we have organized our software with. Now, I said that this is not things that Jean-Paul was working on, but then I discovered this paper by, together with Eichi, it's okay, where he, it's a short conference paper, where he was estimating through a disturbance observer external forces acting on a humanoid. And the model is relatively simple, just mass at the center of mass of the system, acceleration, all the possible forces that are measured at the feet, the external forces Fe, the gravity effect, and then you can estimate the external force Fe by just turning around this equation. So this is not what we have done, because our method doesn't use acceleration, doesn't use it for more multi-body system inversion of the inertia matrix, and is quite efficient in a sense. So we developed what we have called residuals. This is a terminology coming from fault detection literature. And we have a scalar residual, which is energy-based, so monitoring the total energy of the system, and another vector residual, which is momentum-based, so it's monitoring the total momentum, generalized momentum of the system, so the product of the inertia matrix times the velocity. And in fact, you're doing normal operation. When one of these residual grows over a threshold, then you recognize the collision. If not, you continue monitoring things, and then you have a reaction strategy. The reaction strategy deactivates the normal mode of operation, and as soon as the collision has passed, and in fact, these residuals are able to detect also the fact that you're no longer in contact with the environment or with the human, then you can start doing things again. And this is the mathematics of the vector residual, the momentum-based residual. It's model-based, but it's model-based in a smart way, in the sense that it doesn't use acceleration, doesn't use inversion of inertia, like when you're doing parallel simulation of your system. And the result is the last formula on top, which is the decoupled linear equation of a stable filter, which means that the residual is zero when you're no contact. It grows excited by the resulting joint torque from the collision, and when this is gone, it returns to zero, so that you can restart normal operation, all in the same vector signal. And it has more important properties like being able to isolate which link collided in the generic case. And here are very old videos that we recorded, because this activity started when I was in sabbatical at DLR with Aline and Sami at the Dean. And here you can see the robot is in zero gravity, so that you don't bias the reaction of the robot. There is no sensor at all externally. There are joint torque sensors in this robot, but in fact you can implement, the idea that I had was without joint torque sensor. If you have it, you can use it. Otherwise, you can design the residual in the same way without this information. And you have that different type of reaction. I like very much the reflex torques, which does nothing else than amplify the torque applied through the actuators at the joints proportionally to the amount of the residual vector. Okay, the larger is the residual vector, the more is this torque pushing you away. It's like the reflex action when you're hitting something while you're moving with your hand. And of course, you have a lot of possibility of reacting. Here is just a taxonomy of things. It's a portfolio of possibility. The simplest reaction that you do is just stop the robot. But indeed, if the robot has hit you and you have the robot against you, this is not the most safe situation, so you may wish to have a reflection. Or you can also try to preserve what was the original task that the robot was doing. Remember that the robot is doing its own task and the human is sharing and doing something in between. So for instance, if you have a Cartesian path, you may just stop the timing law, reverse the timing law, and then resume without abandoning the path, if the entity of the residual is not too large. If the entity of the residual is not too large, you have to abandon the task because it's too unsafe. And similarly, if you have a Cartesian trajectory and you have a redundant robot, you can do several things. So you can accommodate in the null space of the end effector task the reaction of the robot without abandoning the task. And this is, in fact, the result of this video, where the robot is supposed to do an hexagon in space. And you can touch, and the robot accommodate this, and it's in a relaxed state, but not abandoning the task. But if you push harder, the robot aborts the task and then recover to the point where you abandon the task, and so on. So you can really shape the behavior using always this residual function. Now, what about coexistence? So the second layer, we use a simple RGBD sensor, Kinex, very cheap. And we were able to perform the computation of distances between robot control point, the green point that you see on the left, on the depth video with any object in the environment, so the human body or object or environment, static or dynamic. Later on, we implemented a parallel version of this so that we can consider all the points of the robot, not just selected control points, and we're still running at 300 Hertz, which is faster than the frequency at which Kinect provides sensor data. But remember that we are controlling the robot at 1 kilohertz, so we can predict what is going on with the latest image and then update the image and have this. So having a distance, an efficient distance computation allows you to use your favorite collision avoidance scheme, okay? Artificial potential, vortex field, elastic band, whatever you want to use. And we implemented this with 2 Kinects also in an industrial cell. Very simple. This was a huge robot, not a lightweight collaborative robot. It was a ABB RB 4600. The robot is moving, and the human may enter into this cell just to inspect what's going on, and at this point, the robot would stop and then resume. Okay? Because it's an industrial application, we were forced to use safety-certified sensor like laser scanners, which are much worse than our Kinects in order to locate the human, and also they are very conservative, and so they switch on if you're very far from the robot, while you have seen that with the Kinects we can go very, very close with our algorithms to the robot itself. Okay, so now collaboration. So third layer, I will spend some more time on that. So the task is, first of all, localize if there are some contact and where these contacts occur on the surface of the robot. Now, since our intention is to do something with this exchange of, with this interaction, we should estimate the contact forces. And then here the control comes in, so use this information, try to achieve some desired behavior for the robot. And the idea is to combine this model-based internal information given by the residual, which should be 0 if you have no contact, but then all of a sudden jumps out of 0, and being a vector, you can detect which is the link that has collided, not exactly in which location, but at least which link has collided. And then in parallel, you're monitoring the behavior of your system. With any system, we are using a depth sensor, but you can use cameras, whatever you wish. And then we recognize when the residual goes up, where is the closest point? And then we take this point as the contact point. We compute the contact Jacobian, so the quantity that allows us to relate joint velocity with velocity, linear and angular velocity of a frame placed in this contact point, and vice versa to transfer these physical forces into joint torques. So our residual, in fact, is nothing else than the proxy of this external torque, so the resulting of this gamma force. Generalized force because it includes linear force and moments. So at this point, you have a linear equation. You can do a pseudo-inverse. We found out that most of the time, the moment is very critical. It's better to estimate only with this residual, only the contact force. Because in order to apply a moment, you have really to embrace the robot with 2 hands and then apply a momentum on the link. So with this in mind, this is our early result of estimation. And here you see that the two yellow marks are following just the hand in this video. It's the early version. And the red point is where the contact occurs, and the red line is the intensity of this force. And you can see that there's also classification, contact on link 6, contact on link 2. When you have multiple contact, we don't estimate the contact force because we have not enough information. We do this just when you're touching the robot in one point. And you can touch the robot in any point, okay, essentially. Okay, let's move on. There are cases in which if the contact occurs, if you have many degrees of freedom, or at least 6, and you're hitting the robot at the end, so beyond at link 6 or beyond, if you have more links, then you can reconstruct also the contact force, if you imagine that a pure contact force is being applied, without any information from the external monitoring. This is things that we have shown also in the TRO paper with Aline and Sami in 2017. Or you can equip the robot with more sensors. This is the latest DLR arm, a very nice tool. It's 7 degrees of freedom. It has joint torques on each joint. It has an end effector force torque sensor integrated, and it has a base force torque sensor. Now, with this redundancy of sensor, you can do a lot of things. You can design a more generalized version of the momentum base, and then you can detect multiple contact, estimate the intensity of the force at several points. You can handle singularities. There are some cases where the residual is not able to capture any contact force, so you can push the robot close to the base, and so on and so on. So this is a very nice thing. Indeed, in this case, you need to have more sensor, and you make the best use of it. Now, the other point is how do you distinguish between contact and collaboration? Okay, we can use still the residual, and the idea is very simple. We filter the residual being a filtered singlet itself, so we can design 2 residual with 2 different bandwidth, and if we assume that intentional contact are soft and collision are hard, so that they have component in the frequency domain at a higher frequency. So for instance here, this is a collision. This was not intentional, and it corresponds to peaks in these blue plots at the end. The robot starts again moving, but if you're holding the robot in a more softer way, for instance like this, then he recognizes intentional and switches to a collaborative mode. So, okay. So in this collaborative mode, you can do several things. We implemented a number of control laws, which are standard in robotics: admittance control, impedance control, with natural impedance or modifying the impedance, hybrid force velocity control. The main point is that we don't do this at the joint level or at the end effector level. We do this at the contact level, the contact point that we detected during operation. Well, let me skip this. So if you're a bit familiar with textbook, this is what you implement when you're doing a joint compliance level. So you have a force acting somewhere in the structure, and you impose that each joint behaves as a spring and damper with respect to a reference position. So the robot will go away when you push and come back to the configuration that you started with. Or you can do Cartesian compliance, same story. You're imposing some compliance, so stiffness and damping at the end effector. Now, if you want to modify also the apparent inertia, then everybody should know that we need to measure force in this context. So if you do joint impedance, you may need joint torque sensor. If you're doing Cartesian impedance, you may typically use a force torque sensor. So what we are doing here is we are doing a contact point impedance, if we want to do those, so imposing a desired mass, spring, and damper at the contact point. We are not measuring this contact force. We are not using any other internal sensor, but we are estimating force with our method. Okay, so we are replacing this as a proxy, and then we get along with that. So for instance, these are 2 examples of impedance control. The first on the left is with the natural robot inertia at the contact point. So JC is the Jacobian of the contact point, which changes depending on where you touch the robot. In the second video, we are changing the impedance in the various directions by changing the apparent masses. This was just a choice. So this is kind of simple. What about controlling force? Now, controlling force has a different behavior. Here, you detect the contact, and you're imposing a force control, and you regulate force, for instance, to 15 Newton. Okay? And if you have seen this video, maybe I can show it again. When you're pushing, the robot retracts. But if you're pushing too low, the robot follows you because it needs to find a 15 Newton. Okay? Which is completely different from an impedance model scheme. And here again, 15 stands for this 15 Newton. You can set whatever value here. And we discovered, I mean, at the first point, we made a mistake. We thought that we could control force in any direction. But in fact, you can control force only in the direction where the human is pushing. Because in the other direction, there is no reaction from the human if the robot tries to impose this. It's like the consistency problem in hybrid force velocity control. If you're thinking to be on a table and you want to push on the table, you can regulate force, but if the table is like this, you push and nothing happens, and this is going to be transferred into an acceleration. So this is the task-compatible control of contact forces. Now, last two application. There are, in this project, Simplexity, we should use a robot, a collaborative robot, actually a universal robot one, 6 degrees of freedom, in order to sustain an object which is being polished by a human. Okay? And the human would like to reconfigure the orientation of the object while he's working on it. Okay? So this is the idea. Now, if we have a force-torque sensor, and we're using here a force-torque sensor, so we can detect any force that occurs at the end effector level. But we cannot measure forces which are before. So we use our residual for estimating the forces that may happen. And then we select how to react to this. And the result is the following one. So here there's no object. So imagine that the hand is pushing against the object. The robot stays fixed because you have to do the work. And then you reorient the robot by keeping the same position, by changing the orientation. You continue your operation, and you can do the two things at the same time. So keeping the object in position where the human worker should work on it, while reconfiguring by a simple, not going to the keyboard or even giving a voice command. You don't know how to specify that you would like to see the other part of the object that you're working on. And this is what happened. You see the end effector force measurement and the residual and the joint position and the end effector position. So in this case, when it feels only a polishing force, so the residual is 0 because there's no contact on the body, and then you're keeping everything in place. So the robot doesn't move. It has some compliance, but this is mechanically or probably control dependent. Here instead, there's no measurement coming from the force-torque sensor because you're pushing the robot before, so the residual get excited, and you get a motion in the joint space in reaction to that. And here you have both. So you're pushing on the end effector, you're pushing on the structure, and you're moving, but only the extra body contact force is driving the motion. Okay? In all cases, you keep the end effector still. And this is the last application. Everything this is being done more or less with systems that are open, so that we can enter specifying torque or specifying velocity. We have a model and so on. What happens if you have a closed control architecture like in typical industrial robot arms? This is the same arm that Katja has shown today. Moreover, you can access through this system only at the kinematic level, so you don't know which is the controller, the low-level controller. You have a cycle time of 12 milliseconds from one command to the other. You gather from your robot just the joint position, and in this case, the motor currents. You cannot impose the motor currents, but you can measure them, in particular, just the absolute value of them. I don't know why. And this is what happened. So we implemented the same idea with two-level filtering. We don't have a residual because we don't have a dynamic model, so we're just processing data, in this case, motor currents. And you can see that the robot is able to recognize contact, and this is, in fact, a collaborative mode where the second set of filtered version have been excited, and from there on, you can push the robot around as you wish. Remember that there's no sensor, nothing here. It's really a poor man robotics version. So, concluding, over the years, we have been developing this human-robot coexistence and collaboration in the premises of safety, so detection, reaction, and collision avoidance. Many of these things, in particular the collision detection algorithm, has been extended to UAVs, to humanoids, to soft robots. It's quite straightforward. We can distinguish intentional contact from accidental one. We can estimate in a reasonable way. Okay, we did also some baseline tests with external sensor. It's good, at least at steady state. And essentially, our works puts itself at the low level, I would say. These are control bricks that you can use in any application. If you prefer to use admittance control or hybrid force velocity control or impedance. But it's generalized at the contact level. This is the novelty. And of course, it works also with limited model information. And there are many more things that could be done starting from here, in particular, merging model-based techniques with data-driven techniques. Okay, thank you very much.
Thank you very much for the interesting talk. We have time for a quick question. Anyone? Yes.
Thank you for your exciting talk. So I have a question about how do you deal with the modeling error? Modeling error.
Modeling error. Yeah. You have to eliminate modeling error. No, in fact, in the universal robot, we had a lot of friction, and until we couldn't get a good model of the friction, the residual was not working. In fact, the residual can be used as a, I mean, you can have whatever model you wish, and if the model is good and the robot is moving in free space, the residual should be 0 or below some threshold. If it's not, in principle, you could use the residual in order to estimate your parameter. So what is, I mean, the residual catch what is missing from the model. If the model is good, it catches collisions. Otherwise, it catches collision plus uncertainties.
Thank you. I think we should move on to the next talk. Thank you. Okay. Very happy to introduce the final speaker and our co-organizer, Professor Jean-Paul. Jean was actually the first French person I ever met in my life. I was 22 years old. That was about 32 years ago at the University of Illinois. I was a starting graduate student, and he was a starting assistant professor. And he was a great friend and mentor at the time. Certainly very well known for his work in computer vision, his book, and many contributions to recognition and image reconstruction and synthesis and video as well. I also appreciate his research in the same sense that I appreciate Jean-Paul's work. They both have a deep connection to mathematics and brings a lot of that kind of tradition into their research over the years. Most of his career is spent at the University of Illinois. About a decade or so ago, he came back to France, where he has led a group at INRIA and also was a director of the Department of Computer Science at the very prestigious École Normale. And then for the last several years, he's been at NYU in New York City. So very happy to introduce you. So.
Thank you very much, Steve. Thank you. I'm not just at NYU, I'm also spending half of my time in France. But
okay,
thanks a lot. Thanks a lot.
He's chattering.
Yeah. Okay, so I'm very happy to be here and to welcome you. I've been friends with Jean-Paul for over 30 years. And we have never managed to publish a paper together. And then in December, we lost Jean-Paul. It was a huge shock for our team and for all of the community, and that, we'll miss him forever. It was really a huge loss, and especially for his students and the people around him, and of course his friends. On a happier note, I've never published a paper with Jean-Paul yet, but I'm lucky to be the co-advisor of his last PhD student, Yann de Montmarin, who is in the back over there, and I'm going to talk about his work. And this is unpublished work. Maybe there are bugs, who knows. But I think it's very interesting, and I think Jean-Paul would have liked it. I mean, Jean-Paul knew it. He started, jumped in later. This morning we started with Philippe Swear, who I think, if I'm not mistaken, was Jean-Paul's second PhD student. Is that correct? And so now I'm going to talk about the work of his last PhD student. The two are related. I'm going to talk about configuration spaces, distances, shortest paths, and things like that, and metric balls, which are things that Jean-Paul liked. And I think you will enjoy it. I hope you will enjoy it. All right, so after we started this work, we came upon this citation from James Kufner, where he said that, ideally, if you want to study the motion of a solid in SE3, what you would like to do is to do it in terms of swept volumes. Why? Because if you can minimize the swept volumes, hopefully, as you move, you will occupy smaller amount of space, and you will be less likely to hit obstacles. They said it was unfortunately too complicated and expensive to do. And what this paper is about is really trying to put a metric structure on configuration space using this idea of minimizing the swept volume of our trajectory. So on the right, you have an example of a rod moving in E2 in the plane. On the left side, you have the animation where you do the shortest path in XY theta space, if you want. And on the far right, you have the geodesics that are found with the swept volume distance I'm going to talk to you about using Jan's implementation. I'm going to talk purely about theoretical stuff today. I'm not going to talk about, I will show one more example of his implementation at the end, but I'm not going to talk about algorithms. I'm going to talk about ideas and how you can come up with this kind of notions. When Jan and Jean-Paul started this work, they were focusing on actual robots. I mean, first on just solids in E3, and then on polyarticulated robots. But then we took a step back, and we decided to look at a slightly more abstract problem. So it's the idea of characterizing configuration space of deformable shapes in a affine Euclidean space. Okay. So here. Think of the shapes as robots, and we'll see the relationship with robots later. But it's deformable shapes. They have constant volume, and each instant of this shape is a regular compact body in E3. By regular, I mean in the usual CAD system meaning of the term. That is the thing that is the closure of the interior of its interior. Okay, and so we assume that they have constant volume, and we are not going to parameterize configuration space. The configuration space is the set of all configurations, and the configuration is just one instance of this deformable body. Okay. Now if I equip this configuration space as a subset of E3, if you want, if I equip E3 with the Hausdorff topology, I can define continuous path as a continuous function from the 0-1 interval to the set of all bodies. And then the region swept along that path by my deformable body will be just the union over the path of all the instances of the body. And I will now define the swept volume as the volume of that region, and then the incremental swept volume as the volume of that region minus the constant volume of the object. So in this thing, the swept volume is the orange thing plus the two blue regions over that path, and the incremental volume is the whole thing minus either the volume at the beginning or the volume at the end. Okay, so it's very simple definition, quite general. And the nice thing is that, and this is an example when you take a rectangle in the plane and you sweep it along some trajectory. So the whole swept volume will be the orange plus the red, and the incremental swept volume will just be the red part. And not very surprisingly, you can show that if you take the infimum of the swept volume of all possible paths joining one configuration to another one, this defines a distance, a proper distance on configuration space. So we are actually surprised by this because this is intuitively fairly, it's not surprising, I would say. And we thought that if this were true, this would be a well-known property. And it probably is. It's probably in some textbook somewhere, but we haven't found it. Okay? So how do you prove it? It's actually very easy. All the fact that it's non-negative is trivial. The fact that you have the triangular inequality is almost trivial. The only thing that you need to be a bit careful is to show that when the distance is 0, then the two bodies are the same. And there, this is where you use the fact that you are looking over regular bodies. Okay, I'm not going to go into detail, but it's a three-line proof, so it's very simple. So this is nice. It was again, we are surprised that this was not known. We haven't found it. Maybe it's known. I've talked to people with optimal transport and all that. No, they told me we don't know about that. But maybe it's in a textbook. So this was nice, but one of the things that Jan wanted to do is to is to come up with a metric structure where you are guaranteed that you have geodesics in that metric structure and that you can compute them. Okay, but unfortunately, this distance here is not a geodesic distance, because as you sweep your body along a trajectory, you are going to count a region that is visited twice, only once. And so geodesic distance, you want that it be the sum of the geodesic distance about the two subpaths. And because these properties will not be true in general. Okay? So we had to come up, or Jan and Jean-Paul had to come up with an alternate definition. And one of the things I like, I will forget to say it, one of the things I don't like parameterizations, I don't like equations, I don't like any of that stuff. Here, this is totally coordinate-free, parameterization-free. I don't look at parameterization of SE-free or anything like that. We are going to look at something slightly more abstract. We don't know anything about solid mechanics, but we looked at a bunch of articles and came up and looked at how people really talked about configuration spaces in mechanics. And a typical way to do it is to say you have some reference body in some space, and then you have mappings from that reference body to instances of the reference bodies. Okay? And in our case, the reference body is going to be once again a regular solid in E3. And then we are going to look at mappings that are isochoric, a kind of pretentious word, but it's shorter than volume and orientation preserving, but it's all that it means. So we are going to look at mappings that preserve volume and orientation. And we are going to assume that those are diffeomorphisms from E3 into itself. And very importantly, we are going to assume that the mapping between the diffeomorphism and the corresponding body instance is injective. Okay, and why is this important? Because what we want is to identify the set of diffeomorphism that I'm going to call Q, and each configuration I will call small. Big Q is a set of you understand me? And small q is one of these functions. And I want to identify big Q to all the configurations of the body, all the instances of the body. And when this mapping is injective, then indeed it is, there you have a bijection between the set of diffeomorphism and the set of all instances of your bodies. Okay? So far so good. After we did that work, we found out a paper by my friend George Burdick, and I guess one of his students, that were looking at good representation for 3D solids. And of course, they have the same representation, but again, it comes from solid mechanics. That's not surprising. But in their case, they are looking at solid bodies. Here, we are looking at deformable objects. So now, equipped with a notion, the idea was to look for some differential definition of the swab volume. So you have a body that is transforming along a trajectory. Trajectory is going to be a set of these diffeomorphisms. And as it deforms from the one instance to one at times t plus delta t, you are going to have an increment in volume on the right side. And if you integrate these increments over the full trajectory, you will have another definition of the swab volume. Okay? So we are going to make a few assumptions, simplify stuff, to be able to talk simply about derivatives and stuff. We are going to equip space with a coordinate system. I will not talk about coordinate system anymore later, but it's just so that we can identify E3 and R3. All the results I'm going to show you are totally independent of choice of coordinate system. I'll not prove it to you, but it's true. And then I will consider this time a differential path. A path is what? You take some interval I of the real lane, and it's a map from I cross R3 into R3, such that any element gamma t, so gamma t you define as the thing that associates to a point in the reference body, the value of gamma at times t and in chi, I'm tired. So such that this mapping is an element of your configuration space. Okay? So it's just a path of diffeomorphism. And then, of course, we can define the derivative of the configuration, the time derivative of the configuration, at the partial derivative of gamma with respect to time. Okay? So, and these partial derivatives lives in a tangent space to the configuration space in gamma t. All right. likewise, if I pick a configuration Q and a velocity that is a vector in the tangent space to capital Q in small q, then this will induce a velocity field on the full space R3. And this velocity field will be divergence free because we are conserving volume. All this is easy. You get a simple formula for the velocity field. It's Q dot, that is the time derivative of gamma in chi, whatever. And then you have a Q minus 1 because you want to go back from chi to x. Okay? So now I have this velocity field, it's defined everywhere. And let's take a close-up. This is what we are going to look at. We have our body at times t, our body at times t plus delta t. Part of the body t is going to get inside the next instance. There will be, that's the incoming flux, if you want. There will be an outgoing flux that the part is going to go outside. That's a new part. And what you want to do is measure that new part. And that's what you are going to do to compute the differential of the volume, if you want. So you define the flux as the integral over the boundary of your body at times t of the max of the dot product of the velocity field with the normal to the boundary. Okay? You take the max, it's measured on that because you don't want to count the incoming flux, just the outgoing flux, the extra space you are going to use. Okay? And then given that, you can define the volume swept along the path as the integral of that thing from 0 to 1. And this will coincide with the previous definition of the swept volume, except in spaces where you visit the same region at least twice. Okay? And of course, you can define a function that's going to be the infimum of all possible differentiable paths joining B0 to B1 of that volume. Question, is that distance? And does that distance admit geodesics? So you can guess the answer, yes, under some hypothesis it will. But before I do that, again, in this case, we don't count this region a single time because we take the increments. We'll count it as we enter it, but we'll count it again as we visit it again. Okay, so we can be hopeful that maybe we'll have a geodesic structure with that thing. So the second main result is that under relatively mild assumptions, d prime, this new measure, is indeed the distance over the configuration space. And under some extra assumption, when Q equipped with d prime is locally compact, complete, and path connected, and this will be true in many cases, in particular if you look at rigid solids or articulated bodies, non-intersecting bodies, then any pair QQ prime of configuration is Q is connected by a geodesic, which is exactly what we want. Okay? All right, so how do we prove that? Well, we need to prove a lemma, which is the fact that the function that associated with Q dot, the flux, defines a norm about the tangent space to the configuration space in Q. If you have that lemma, then it's easy. Well, it's easy. No, you have to use strong results from differential geometry, but they come from textbooks. Okay? You use the elementary Finslerian geometry, and for Finslerian geometry, you have to talk to Jan because I wouldn't say I'm rusty, I don't know anything about it. And you use well-known theorems about this kind of stuff. But the key is to prove that lemma. What are the mild assumptions? Well, the mild between quotes. The first assumption is, again, that the mapping between configurations and the corresponding bodies be injective. The second one is a bit more involved, so I need to discuss it now. All right, so let's have a close-up. This is a close-up of that thing. So we have, my body at times t plus delta t, and here in orange I've represented a bit of the path swept by my thing. Okay? So, of course, the velocity field V of VQQ dot changes with time. It's defined at Q is equal to gamma t, so it changes with time. But you can also think of it as a stationary field defined at time t. So you take the value of VQQ dot at time t, and you have these arrows everywhere in R3. You have the velocity field everywhere in R3. Okay? It's not evolving. You fix it. And then what you can do is look at its integral lines. So you take this point here, for example, you know, its trajectory will be a curve like this, and likewise, in serving this body, we'll have new instances of that body before and after formed by tracking these integral lines. Okay? The thing that you obtain is a new path, gamma with the exponent q dot. Of course, this new path is different from the original one. We call that canonical extension because we think it's a pretty nice name. And you can easily show that it's also isochoric, that is also preserves volume. Okay? Is that okay? Simple one. All right, so now we can define our second assumption. The second assumption is that, at least locally, the canonical extension over a small interval, maybe, the canonical extension is itself a configuration. And again, in many favorable cases, this will be true. If this condition is not true, or if the condition about injectivity is not true, then the lemma is false and the theorem is false as well. So these are really, the two conditions are necessary. How do we know that? Because we have simple counterexamples. Okay? But with this assumption, it's quite easy to prove the lemma. Maybe I should say that in the next one. Yeah. Here is the proof, informal proof of the lemma. First, we can rewrite the flux. Instead of having the max of 0 and the dot product, you'd say just half of the absolute value. Why is that true? Because the volume is conserved. So the outgoing flux must be equal to the incoming flux. Okay? So we have that. So now, the fact that this function is non-negative is obvious. It's homogeneous as well. Subadditive, it's easy. It becomes some linearity of dot product and subadditive of absolute value. So the only thing that's still non-trivial is to show that when this function is 0, then q dot must be 0. If you have shown that, then you know it's a norm. Okay? So how can you show that? Well, when this thing is 0, the absolute value of the dot product must be 0 everywhere. That means that the velocity fields must be tangent to the boundary of the body. Okay? In particular, it means that the integral lines of that field starting on the boundary will stay on the boundary. Okay? And in fact, so this is in 2D, but it's true in 3D, and because the thing is compact and regular and all that, you can show that if it's this case, then the value, the body associated with gamma of q dot in T, whatever T in this small epsilon will be the body itself. Okay? That's simple to show. So what do we have now? We have a stationary path whose value is constant and is BQ. And because we have injectivity, if we have this, if we have this because of injectivity, then we have this. Then gamma T of q dot is equal to Q. That means that gamma is stationary. The derivative with respect to T is equal to 0. That means that Q dot is equal to 0. We're done. Okay? So, well, I went really fast. So that's all there really is to it. So 4 things to finish. So this is for deformable bodies. But this applies, I was taught when I was a kid that you shouldn't say trivially, but this applies immediately to regular rigid bodies in E3. It applies also immediately to polyarticulated robots without self-intersection. It can be extended to polyarticulated robots with self-intersections, but then, of course, the geodesics you compute may not be physically realizable. Maybe it will be useful in practice. I think that the practical thing is neither mine or Jan's main thing, but still. So Jan did some easily implemented, so you can compute the trajectories, did some initial implementation using RT to do path planning. This is using RT and the usual metric in configuration space. This is using the new metric, and as you can see, you explore fewer nodes, and you have better connectivity between the nodes, so it seems to work pretty well. but who knows if it will be useful in practice. We thought about this morning when we saw Philippe's talk. What about, does it apply to cars? We don't know if H2 is satisfied for cars. It would be cool. And what would the optimal paths look like, and wheelchairs and all the like. So we don't know. So we thought about it this morning. We should have thought about it before, but we'll think harder. And then we can draw cool balls, and Jean-Paul would have loved that. And since Jean-Paul loved printing balls, we'll print them very soon. And I'm going to stop there. I like this picture. This is a few weeks before we lost Jean-Paul. He had organized a workshop at Agénie-des-Sciences, and he's full regalia, and he's very happy and full of energy, and that's how I like to remember Jean-Paul. And it's Nicola who sent it to me this morning. So thank you very much, and we'll stop there.
Okay, thank you very much. Questions, anyone? Yep.
So it's something that I didn't understood is you talk about the Euclidean space. There is no orientation at all. I didn't see the orientation.
The orientation, but it's the Euclidean affine space, so it's oriented.
Okay, you talk about it's not the R3 is
no, it's the affine
okay.
space. Yeah.
Okay, this is what was not clear to me. Okay, thank you.
Anyone else?
Again, it may be in textbooks, and we don't know. If you know of textbooks that give these results, you'll be unhappy, but will survive.
I have a question. Do you have any idea about the curvature of the space? Like if you were to pick triples of points, look at geodesic triangles, are they thinner or thicker than Euclidean triangles?
I have no intuition in anything, but if we have no...
If they're all thin, then you get unique geodesics. I'm just curious about...
Anyway. I think we get unique geodesics.
Like cat zero space.
Jan, is that true? Or no, we don't get unique geodesics.
Oh, okay.
Jan will know the gory details.
Thank you. Anyone else? Let me let you say that real quick, since it's your work.
No, in this formulation, you do not have the unicity of the geodesics in general. The most example is with the rod motion we saw. You can have a symmetric of the motion which sweeps the same volume, for example. So you have always multiple geodesic, but with some quadratic perturbation, you can transform the Finslerian geometry in a Riemannian one. And here you have on some cut locus area the unicity of the geodesics.
Okay, thank you. All right, with that, I think we should finish. Thank you very much.
Philippe, we are going to say the last words.
So it was a wonderful day. Many talks on different topics showing different facets of Jean-Paul, and all the time the conducting stream of the human relationship, the interest for the machine, the mathematics, and also for humans. So I believe that we can explain to a large audience that robotics is not only the science of building machines. We have to do that. We have to increase the state of the art in this direction. But robotics is also a way of understanding humans. I think we saw that it can be about language. It can be about life science. So it's a way of building a system that is supposed to do a bit of what we are able to do. And I think not a lot of people understand that the robotics that animates us every day in our research is sometimes in that way more than in the fact of finding some industrial solutions to improve the production. Okay, so Jean-Paul was a pioneer, I think, in this direction. So I would like to thank all of you for sharing this day, for all the words that you say and the way you you met Jean-Paul and produced something with him. So, thank you.
And just a last word. So I want to thank again, I did this morning, but I want to reiterate, I want to thank PRAIRIE, and LAS, and Collège de France for having us and supporting us, Paul Jacobs as well. And again, I want to thank Stéphane Mala, Alain Bertos, and Marie-Laine Messon de Rennes, who is there, without whom this thing would have never happened. A last word, I really hope, I mean, just like Philippe, I really hope that especially for me, it has been a blast to see everybody again. It's been a long time. But for the young people, I hope this thing inspires you to follow in the footsteps of Jean-Paul and discover, what it is to look at the relationship between robotics, the world, neuroscience, exactly what Philippe was saying. So I hope it is useful. Thank you very much for coming. Thank you to our speakers and our session chairs. Some of them came from very far, and now we have champagne.